Chapter 0 of The Ocean of Air, Meteorology for Beginners. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. The Ocean of Air, Meteorology for Beginners, by Agnes GIBERNE. Preface by Reverend C. Pritchard, and author's preface. In the year 1879, the proof sheets of a little work entitled Sun, Moon, and Stars, now happily well known, were placed in my hands by a friend who asked me to give a passing glance over their contents. The work appeared to me to be so excellent of its kind, and gave, as I thought, so much promise of public usefulness, that I volunteered gratuitously the offer of a preface, if it were thought that I might thereby contribute to its wider circulation among the intellectual and educated classes, whether older or younger in years. Since then I have been gratified by the fulfillment of this vaticination in the recent appearance of a 13th edition, and I think it will be for the public advantage if it shall be even more extensively read. A few weeks ago, the same authoress sent me the revised proof of the present work on the varied and wonderful properties of the ocean of air which surrounds our earth, and requested my opinion on the execution and value of the contents. I confess, at first thought, I considered that so extensive and complex a subject required an amount of study and of accurate information which could hardly be expected from an unprofessional author. It would, as it seemed to me, tax the cultivated powers even of Sir John Herschel, and, if successfully executed, might take its place alongside his remarkable familiar lectures. After an hour's cursory perusal, I found myself enchained by the multitude of pleasant thoughts suggested by the description of the physical circumstances surrounded by and immersed in which we pass our being, expressed, moreover, in a language at once so graphic and so simple that I offered for the second time to exert any influence which I might possess in the recommendation of the book to the general notice of educated persons. The points touched upon in the course of the work are very multiform, embracing the greater part of the natural phenomena familiar to us in our daily experience: heat and cold, the calm and the storm, thunder and lightning, vapor and cloud, rain and dew, the passage of light and of sound. Each and all of them in their turns receive their share of illustration in the most pleasant of literary styles. Nor does the authoress hesitate to encounter the marvelous conflicts of the molecules constituting the phenomena of atmospheric pressure and of heat and light, while in due course she extends her flight to the regions of the aurora and of the meteoric dust there floating and luminous, then gradually falling on the earth and on the wide surface of the ocean, and ultimately dredged up in the form of mineral nodules from the remotest depths of the Pacific. A pleasant diversion is then made to the flight of the birds of the air, and to the locusts which are driven onwards by its winds. It is by a fascination of this sort that the reader is, almost unconsciously to himself, led to a general conception of the plan and the forces of that part of the course of nature amidst which he draws his breath and lives. There are more aspects than one in which a little work like the present may be intrinsically valuable, and in which that value reaches to young and old alike. As to the young, it cannot fail to excite those facilities of curiosity and imagination which, when restricted to their proper sphere, are among the most valuable of our natural endowments. In most cases, it will probably satisfy the curiosity which it excites. In respect of those who are of an older growth, it must not be forgotten that though most of us are not called upon to become philosophers or experts, still we can, all of us, if we choose, obtain a general and intelligent conception of the nature of the phenomena in the midst of which we live and move and have our being. The amount and the intrinsic accuracy of our conceptions of these phenomena need not be great for the ordinary purposes of life, but to remain willfully and purposely ignorant of their existence and their meaning is hardly worthy of beings who rank themselves among the rational orders of the creation. It will also be found, I think, that very many of our mental enjoyment spring from a knowledge which is far from complete or profound, and that the most pleasant of them are associated with a knowledge which is comparatively superficial. It is in the byplace, the peregrine of the intellect, that the better part of the intellectual enjoyment is found. It is in this direction, I think, that we are to look for the chief recommendations of the little book before us. Beyond this, a casual remark here and there will probably touch chords within the mind, which once so touched will never cease to vibrate and lead to trains of thought and occupation at once harmonious and beneficent. In this way, a few specks of dust swept up from the hearth and placed under a modern microscope have revealed to the instructed eye the wonders of a tropical jungle and the formation of coal fields therefrom, and thereby have fired the mind with a passionate desire for more extended knowledge of the primeval formations of our globe, and of the structure of the grasses which once have clothed them. It is trifles and accidents such as these which not rarely have determined the whole bent and aim of an intellectual life. Lastly, I think there is another aspect under which this unpretending little book may possess a considerable value, and it is this. The education at our great public schools, and even our universities, is yearly becoming more technical, and is falling more and more under the dominion of cram, and of the schedule, and of the syllabus, and of the examiner. The schoolboy is fast becoming hot-pressed. He is urged by considerations which he cannot resist to maintain or extend the credit of his school, either by conventional distinction, in Greek or Latin, or in what is miscalled natural science, or, if he be hopeless in these directions, he must at all events contribute to its fame by athletic feats. Thus, his young life is marked out for him and trammeled within narrow limits, while the actual bent of his mind and the true reach of his natural capacity become ignored or unsatisfied. In the palmy days of the old school life, the boy, who made but a poor figure in his form, might betake himself to collecting butterflies or beetles, or to keeping mice and dissecting them when dead. In this way, the foundations might be laid for pursuits in life leading to eminence and usefulness. As things are, his natural curiosity too often is stifled, that forward-looking faculty, his imagination, becomes atrophied, and his mental endowments molded into a stereotype. From my professional position at the university, it is my misfortune to observe and deplore a very large and mischievous amount of this suppression of curiosity, and a general absence of a knowledge and love of nature, which I take to be the necessary consequence of the modern style of education, when pushed, as it often is, to an extreme. I cannot doubt but that the eminent and highly cultured scholars who adorn the headships of our noble public schools perceive and deplore this result of a system which, through the varied pressures of social life, they are at present unable to control. It is here that I think this little volume, with its multitudinous and interesting peeps into the nature of the things around us, may become signally useful. If I had now the opportunity which I once had, I would place Miss Giberne's little volume in the hands of the boys in the upper forms of the school, and encourage them to read it as an amusement and for a change of pursuit, under the hope that the pleasant and varied information it contains might find a response and a home not reachable by the ordinary routine of school life. What I have here indicated as serviceable for boys is at least equally so for the other sex, nor, as I have already said, do I think its interest or utility is limited to the years of our youth, seeing that it was not without a species of fascination that I read it myself. It is, indeed, but a little book, but it treats of many objects and many phenomena of constant occurrence, and it possesses the great advantage that it can be taken up and laid down again piecemeal, and at fragments of time. Bread thus cast upon the waters will be found hereafter in an abundant harvest of pleasant association for hours of contemplation or of leisure. E.N. C. Pritchard, University Observatory, October 1889. Author's Preface. After the generous words of Dr. Pritchard about my little book, there is small need for me to say much. First and foremost, I must express my hearty gratitude, not only for the warm praise which he has accorded, but also for the infinite trouble which he has taken in reading the revise, pointing out some weaknesses and here and there suggesting improvements. I can never forget what I owe to his kindness, both with this book and with Sun, Moon, and Stars. In writing The Oceans of Air, I have had a wish to make it one of a trio of volumes. It may be said to occupy a position between my two earlier scientific books, Sun, Moon, and Stars, had for its subject the vast realms of space, dotted with suns and worlds. The World's Foundations had for its subject the crust of our Earth and the story of the crust formation. The Ocean of Air has for its subject the expanse dividing the two, that broad belt of atmosphere which rests upon the Earth's crust and reaches upward to surrounding space. I might end with a catalogue of books, encyclopedias, to which I have had recourse for information, but many of them are referred to in the following pages, and the entire list would be cumbrously long. So I will only close with a word of particular acknowledgement to the authors of any extracts which I have ventured to make without writing to ask express leave. I trust that, in such cases, the omissions will be pardoned. Wharton House, Eastbourne, October 1889. End of Chapter 0. Chapter 1 of The Ocean of Air, Meteorology for Beginners. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. The Ocean of Air, Meteorology for Beginners, by Agnes GIBERNE. The Air in Which We Live. Our Earth has many robes. Closely fitting garments come first, of brown soil or gray rock and green grass, with wide, liquid underskirts of deep blue filling up the spaces between. Outside these coverings, more wonderful still, fragile yet strong, transparent, almost invisible, folded around layer upon layer, or as one might say, veil upon veil, each more gossamer-like than the last. These form Earth's surrounding atmosphere, a substance pervading everything, found everywhere. One may travel from the equator to the poles. One may journey by sea or by land. One may soar high in a balloon or descend deep into a mine, but one can never, in this world, go to a place where the atmosphere is not. A substance, for air can be felt. Air has weight. Air occupies space. Air, like any other body, can be made hot or cold. Air is composed of particles of substantial matter. A child, not to speak of a grown-up person, opening a box which holds only air will naturally say, "Nothing here." But something is there, something very definite and real, and of no small possibilities. Those same quiet air particles, actually unfelt by the hand moving gently among them, have strength, when stirred into a hurricane blast, to uproot huge trees, to sweep away vast buildings, to raise ocean waves upon which mighty ships are tossed helplessly about, like eggs in a boiling cauldron. Air may be felt. The faintest breeze cannot stir without a man becoming conscious of the air particles striking against his face. He cannot ride or run through the air without the same sensation. If he even moves his hand quickly enough to and fro, he is aware of something resisting his hand. Air can be made hot or cold. We all know from experience the difference in our feelings when cold air particles on a frosty winter's day or hot air particles on a sultry summer's day strike against our bodies, either giving over to us of their heat or stealing away some heat from us. Air also has weight and occupies a certain amount of room. Just as a mass of iron or of lead weighs so much, a mass of air has its own particular weight. This means that air, like iron or lead, is subject to Earth's attraction, which is only tantamount to saying again that air is a substance. Nothing which is not a substance can possibly be attracted by a substance. If air is a substance, it must occupy space, it must take up room. It may be very light, very slight, very elastic, and very compressible. Other bodies may pass easily among the air particles, pushing them apart, or squeezing them closer together. Yet space it must have. Air, being distinctly a something, has to be somewhere. Air has a faint bluish tint, which on a sunshiny day becomes in the sky a very pure and deep blue. This tint is not believed to be the natural color of the atmosphere. Were it so, the air would merely act the part of a blue pane of glass, rendering the white light of the sun blue as it reached our eyes. But the blue of the atmosphere is known to be a reflected blue. If reflected, there must be something in the atmosphere to reflect it, and such indeed is the case. Perfectly pure air would doubtless be without color, but perfectly pure air we do not find. The whole atmosphere is full of multitudinous minute specks, so small as to be in themselves invisible, so light as to remain aloft. To the presence of these, the blue tint is believed to be due. They scatter the light of the sun and produce the blue effect. A beam of strong white light, caused to pass through a liquid which contains a large supply of minute floating particles, is affected by them in a like manner. The short blue waves are more abundantly reflected than the long red waves, and so the water seems to be blue. This explanation serves for the deep blue color of the ocean, as well as for the blue of the atmosphere. The whole earth is surrounded by this marvelous air ocean, An ocean of gaseous matter, at least 100 times as deep as the water ocean. At the bottom of the gaseous ocean, we small human creatures crawl about, commonly on flat lower levels, the ocean bottom, in fact. Sometimes, with much toil and trouble, we climb the little ridges and mounds, called mountains, little compared with the depth of the atmosphere, though not little compared with ourselves. The highest mountain peaks of even the vast Himalayas lie low down near the bottom of the ocean of air. Our position is, on a bigger scale, much the same as that of the crabs and crayfishes crawling laboriously about at the bottom of the seawater tanks in the Brighton Aquarium. Only they are in a minute world of water, and we are in the large world of air. They have over their heads only a few feet of the fluid in which they live. We have over our heads many miles of the fluid in which we live. Author's note: air and water are both fluids, though different in kind. Also, it seems probable that they cannot see beyond their confined regions of water, while we have eyesight which can pierce far beyond our wide regions of air. But the very extent of the ocean of air adds to our difficulty in studying its nature. All observations that we can make must be limited by the state of the atmosphere just around ourselves. We can never get out of and beyond the atmosphere so as to see it as a whole. At any time, a slight local fog is enough to put a stop altogether to such observations, beyond the unpleasant experience of the fog itself. Just so a crab, wishing to study the general condition of the water in his tank from one corner of it, would be hampered by the stirring up of a little mud or sand in his own neighborhood. In all study of the earth's airy envelope, we have to allow for these difficulties, to confess ourselves apt to, and not to dogmatize hastily upon questions about which we are not well informed. We can never in this life get beyond the ocean of air, for man and beast cannot live without air. To breathe means life. To cease breathing means death. That which we breathe is the air around us, the ocean of almost invisible gases. It used to be supposed that the atmosphere reached only to a height of about 50 miles above the Earth's surface. We are driven here to conjecture, to some reasoning from certain tokens, and perhaps to a good deal of guessing. Being always imprisoned at the bottom of our oceans, we cannot measure for ourselves how far it extends above. Of late years, the opinion has gained ground that the atmosphere reaches to a height certainly of 200 or 300 miles, probably 400 or 500, possibly a good deal more. But the condition of the air far above is different from that of the air in lower levels, where we live and breathe. The higher we ascend, the more thin or rare becomes the air. A less quantity fills a certain space up there than down here. The particles float farther apart from one another. This difference in the density of the air is chiefly due to attraction. Each separate air particle is drawn steadily earthward by the force of gravitation, and that force is stronger on the surface of the earth than at a distance. The closer to the earth, the heavier the pull. The farther from the earth, the less the pull. Besides the actual attraction of the earth drawing the air particles downward, there is the great weight of the whole atmosphere above, caused by the same attraction. Miles and miles of air overhead press mightily downward, packing tightly together the lower layers of air near the earth's surface. If thousands of bales of cotton wool were piled into an enormous heap, the upper layers might be light and loose in their make, but the lower ones would be squeezed into a very small compass by the pressure of the mass above. Without this pressure of the overlying atmosphere, the air down here would not be nearly so dense as it is, and indeed would not be fitted to supporting life. A man ascending a mountain or rising in a balloon leaves heavy layers of air below and has an ever-lightening weight above, so that the atmosphere around him becomes constantly more thin, more difficult to breathe. This difficulty is felt to a severe extent by those who climb the greater mountains. Within certain limits of height, the air is only more light and exhilarating, because a little less dense than on the plain. But as its rarity increases, the breath gets short, the heart's action is quickened, the sense of oppression grows painful. If the ascent could be continued indefinitely, death from suffocation would result. The loftiest mountaintop upon the earth stands only about 5.5 miles above sea level. No man has ever yet climbed to such a height, and probably no man ever will. It might not be impossible to exist for a while upon the summit, but one can hardly imagine any man able to reach any such level by climbing. The thinness of the air must long before have so reduced his powers as to render active exertion out of the question. If some means could be devised for bearing him to the summit of Mount Everest, loftiest of the Himalayan range, he would probably, when there, be fit for little more than to lie panting on the ground. Mount Everest has never yet been scaled by men, though ardent mountaineers long ago reached to a level of over 19,000 feet in the Himalayas. This too has been done with the monsters of the Andes chain, once supposed to be the highest mountains in the world, though now known to be far surpassed by the giants of North India. In the beginning of the present century, Humboldt made a vigorous attempt to scale Chimborazo, one of the loftiest of the Andes. He and his party suffered severely from sickness, giddiness, and difficulty in breathing, and the attempt proved a failure. Not till over 70 years later was the ascent actually accomplished by Mr. Whymper. This time, too, the daring climbers were almost incapacitated by weakness, headache, fever, and breathlessness. Yet with desperate resolution, they held on till the summit was gained. After camping for a night at the level above the utmost height of Mont Blanc, they stood at length victorious nearly 20,000 feet above the sea. The ascent of the last 1,000 feet, we are told, occupied 5 hours, for a large tract of extraordinarily soft snow had to be crossed, and it was found necessary to flog every yard of it down, and then to crawl over it on all fours. Such exertions, at so great a height, and in so rare an atmosphere, speak well for the indomitable spirit of the travelers. De Saussure, ascending Mont Blanc in August 1787, suffered from extreme distress and exhaustion. On the highest ridge, he had to halt every 15 or 16 steps, sometimes even to lie down. And the robust guides with him were in absolute danger of fainting. The same excessive weakness was felt by certain other well-known climbers in 1844. But this experience is by no means universal. The effect of the rarefied air differs extremely with different individuals. Moreover, use greatly modifies and even to some extent does away with these effects. In the Andes, there are cities full of people at heights of 12,000 or 13,000 feet, and no inconceivable results from the thinner air. Carried upward passively in a balloon, without effort, men have risen higher than the greatest mountains. Mr. Coxwell and Mr. Glacier, in their celebrated aerial voyage of 1862, are believed to have mounted 7 miles above the sea. No little peril and suffering were involved, alike from the extreme thinness of the air and from the bitter cold. The wish to fly like a bird is an old wish among men. Perhaps it is a form of the new restlessness, which dislikes to be tied down anywhere. Perhaps it partakes of the excelsior feeling which would fain reach regions inaccessible. Tied down we undoubtedly are to the lower depths of the air ocean, and inaccessible to the higher regions undoubtedly are to us. Various mad attempts at flying have been made from time to time, more or less disastrous to the makers of them. When, however, near the close of the 18th century, a balloon was first made and sent up, men thought that they had at last won mastery of the atmosphere. They did not at once find out that floating is not flying, that the balloon, at its best, is still only an unmanageable despot, a despot over the men whom it carries, and itself a complete prey to the despotic winds and breezes. No means of steering or guiding a balloon has yet been discovered. Author's note: attempts are now being made to construct an airship able to plow its way through the opposing winds. Whether successful or no, time will show. Where the air flows, the balloon goes, fast or slowly, according to the degree of wind. No balloon ever cuts its way through the wind or travels contrary to a breeze. It is simply swept to and fro by the atmosphere, as a cork is borne to and fro by the ocean. The first public balloon ascent took place in June 1783. A fire balloon made of linen and filled with smoke went up from near Lyon, and a fervor of excitement followed. Silk balloons filled with hydrogen gas were made next, and the earliest ascent of man followed. A successful, though perilous, attempt to cross the Channel took place about 2 years later. Many aerial journeys were made, some ending well, some fatal to the unfortunate voyagers. As the dangers of these attempts became better known, and as their comparative uselessness for almost all except scientific purposes grew more apparent, public interest in the matter faded. During the early half of the present century, balloons were little thought of, but more lately there has been a revival of interest. Some very remarkable ascents have been made by the famed aeronauts Mr. Coxwell and Mr. Glacier. One or two of these are especially worth mentioning. In their second ascent from Wolverhampton, the balloon sprang rapidly upwards, and in about 10 minutes was hidden by a cloud. It reappeared, vanished again, was seen at a height of perhaps 3 miles, disappeared anew, then gleamed in the far distance as a transparent ball shining moonlike in the sunbeams. The journey lasted from about 1 o'clock till 4:30, and in that interval the balloon ascended 4.5 miles. The voyagers suffered from severe seasickness, though not from bleeding of the nose or singing in the ears, popularly expected on such occasions. They had enough to bear without these additions. Mr. Glacier held manfully to his task, observing and noting down the state of the atmosphere, minute by minute, despite sickness, brain pressure, violent headaches, and a pulse at 108 per minute, all due to the rarity of the air. The view seen from above must indeed have been marvelous. No veil of intervening clouds shut off what lay below, and the earth was visible, not as a rounded surface, but as a seeming hollow, with a distant horizon raising high all around, like the rim of a saucer or an inverted watch-glass. The intense black blue of the sky, as seen from great altitudes, is well known to mountain climbers. Here, however, the blue seemed to be everywhere. A mighty expanse of pure blue filled the vast hollow, reaching to unlimited depths above. An immense shoreless ocean, the ocean of air in which these daring voyagers floated. A boundless sea of ever-changing clouds, piled in mountain masses, and dazzling the eyes with their snowy glare, followed more or less the lines of the horizon, often closing in below to shut off the solid ground. As the balloon rose higher, the pervading blue grew brighter, and earthly sounds waxed faint. 1 mile high, human voices might still be heard, raised in a shout. 2 miles high, only a dog's sharp bark could be distinguished. Since a balloon moves with the moving air, there are no jars or jolts, no struggles to advance, as with a ship at sea. Nothing resists its passage. The movements of a balloon seem, indeed, to be characterized by a singular quietness, so far as regards the voyager's sensations. When it first rises, the earth appears to drop away. When it descends, the earth appears to rise. There is little consciousness of motion. This delusion was quaintly expressed by a certain American aeronaut. He was, he says, preparing to come down gently when the earth bounced up against the bottom of his car. A more terse description could scarcely be offered. The most remarkable ascent known was that of Mr. Glacier and Mr. Coxwell on the 5th of September, 1862, when they rose 7 miles. If we remember that Mount Everest of the Himalayas is nearly twice the height of Mont Blanc, and that the voyagers were floating 1.5 miles higher than the height of Mount Everest's topmost peak, we shall better imagine the perils of this excursion. No human beings have ever ascended further. The marvel was that they returned to earth alive. In those lofty regions of air-ocean, no living creatures exist. The voyagers passed through the boundless silent solitudes, silent except for the hurried beating of their own hearts, the sound of their own panting breath, and the sharp ticking of their watches, and the clang of the valve door. On leaving Earth, the thermometer stood at 59 degrees. Soon afterward, the balloon passed through masses of clouds, thousands of feet in depth, then came out into dazzling sunshine, with a deep blue sky above and cloudless mountain masses of billowy cloud below. As they rose, they released at intervals a captive pigeon. One set free at a height of nearly 5 miles fell downward like a stone. Of 2 others taken higher, one died of the cold, and the other was stupefied. When they reached 5 miles above the sea, the temperature was below 0. Still upward, further upward rose the resolute pair. Then, blinding darkness and insensibility seized Mr. Glacier. Had he been alone, he would never have revived. With no one to open the valve, the balloon must have carried him onward into yet higher and deathlier regions, where for a lack of air he would have perished. Even then, Mr. Coxwell did not at once give in, but he was strictly on the watch. At the 7 miles level, a tremendous height, he too felt signs of failing consciousness. In a few minutes more, all would have been over with them both, and at last he yielded. It was indeed time that he should. His hands were powerless to act, but he seized the valve rope in his teeth and pulled. The gas rushed out. The balloon steadily sank. Both lives were saved, and a mighty feat had been accomplished. Yes, a mighty feat, and at a tremendous height in consideration of human powers. 7 miles high would seem to be the outside limit at which animals generally can exist, even for a short time. Birds may be, to some extent, an exception. Certain birds are believed to soar occasionally 2 or 3 miles higher still. But what are 7 miles? What are even 10 miles compared with the 400 or 500 miles of atmosphere depth? With all our utmost efforts, we and the birds still find ourselves only able to creep and flutter on or near the floor of the ocean of air. End of Chapter 1.
Chapter 2 of The Ocean of Air, Meteorology for Beginners. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Elizabeth Miles. The Ocean of Air, Meteorology for Beginners by Agnes GIBERNE. What the World Would Be Without Air. Chapter 2. What the World Would Be Without Air. What Earth would be without her surrounding ocean of air, we can scarcely imagine. The atmosphere plays so extraordinary and essential a part in all around that to picture its entire absence is not easy. We see faintly on the moon something of what an airless world must be, yet since we only see from a distance of 240,000 miles, that does not mean much. Imagination has to come in, and imagination is apt to play us curious tricks when running after affairs which lie outside the range of human experience. No man has ever yet been to an airless world. If he could get there, he could not live there 10 minutes. He would be worse off than the aeronauts 7 miles above Earth's surface. They had at least some air, though, but a scanty amount, while he would have absolutely none. Without air, man and beast cannot breathe. Without air, plants and trees cannot grow. Without air, life as we know it, the lower animal life common to man and beast, is a thing impossible. Without air, our world would be, as we suppose the moon to be, a world of lifelessness. Air is the earth's outer robe, for use and for beauty, for use in modes uncountable, for beauty not so much in itself as in the softening, the diffusing, the controlling effects of its presence. Air is a mighty ocean in which all things living must dwell. Even the living things of the sea are not exceptions to this rule, for water itself is pervaded by air. A man going into and under water does not get beyond the touch of air, only not being provided like fishes with breathing gills, he cannot make use of what is there. He cannot separate the air from the water, and so keep himself alive by breathing it. Some animals living in the water ocean are as dependent upon the air ocean as man himself for the breath of life. Whales are a remarkable example of this. They are not fishes, though often mistakenly called so, but belong to the same family of creatures as men and land quadrupeds generally. A whale is warm-blooded, has no gills, and breathes atmospheric air coming to the surface for it. A whale kept forcibly for a long while underwater would be drowned exactly as a man would be. If a whale is thrown upon the shore, it does not die of suffocation, but of inanition. A fish's gills are no more fitted to breathe air in bulk than a man's lungs are fitted to breathe air diffused in minute particles through water. The fish out of water is suffocated by getting air too rapidly, the man underwater by exactly the reverse. A whale breathes like a man, and on land it simply starves fast from lack of the incessant food required by such a huge carcass. There is a difference, certainly, between man and whale in the matter of breathing. A man has to take in fresh supplies of air constantly, and if he is beyond reach of air for more than a few minutes, he dies. A whale comes to the surface for about 10 minutes, spouting out enormous supplies of used-up air and taking in enormous supplies of fresh air, after which it can remain underwater for half an hour or more, some say an hour. Then a fresh bout of noisy breathing becomes an absolute necessity. This, however, is merely a matter of internal arrangement. The whale has an immense reservoir of blood, which, being thoroughly purified by the air during 10 minutes of vigorous breathing, serves slowly to supply the creature's requirements while below. But the need for air and the effect of that air upon the blood are much the same in man and whale. Small creatures as well as big ones, spending much time underwater and yet breathing air, have to come regularly to the surface. The great water beetle, for instance, while able to live on land, is a very incapable being there and seems at home only in the water. Like other insects, it has no lungs and breathes air into its body through tiny holes in its sides. Lungs or no lungs, air it must have, or like man and whale, it must die. So after the fashion of the whale, it rises to the surface to breathe, and not having the happy internal arrangement of the whale, one would expect it to be compelled to bob up incessantly for fresh air. But here we find another provision equally wonderful. The hard, polished wings of the beetle, neatly fitting and fast shut, enclose between themselves and the body a watertight hollow into which the breathing holes open. This hollow is filled with air when the creature comes to the surface of the pond, and while the little supply is being gradually breathed, the beetle may safely remain below. Not till it is used up does a dart to the surface for a fresh supply become necessary. Another such instance is seen in the water spider, a creature again which can exist on land, but is more at ease in water. When the spider dives, it carries downward countless tiny air bubbles, caught and imprisoned among the fine hairs which cover its body. This is not all. The spider has also an extraordinary power of conveying down at will, between body and folded legs, a large bubble of air for a particular purpose, to supply the little home below. The said home is a cocoon spun by the female spider in readiness for eggs. Having prepared a cocoon, the spider dives with a big air bubble and lets it loose within the cocoon, where it remains, driving out an equal quantity of water. Bubble after bubble being carried to the spot, all the water in the cocoon is gradually replaced by air, and the tiny dwelling becomes habitable. So much as to the need of air for living creatures. If our world had no ocean of air, there could be on earth no men, no quadrupeds, no whales or fishes, no birds or insects, no forms of life. Like the ocean of water, the ocean of air knows no repose or stagnation. What we call stillness on the most sultry of summer days does not mean absolute stillness. Though not enough wind may stir to lift a feather, yet the air is in ceaseless motion, to and fro, hither and thither. The whole atmosphere is a vast and complicated system of air currents, and each lesser portion of air has its own lesser circulation. You cannot lift your hand without causing a tiny breeze. You cannot turn a wheel without making a minute whirlwind, and every separate air movement draws other movements in its train. There is water enough on earth for all needed purposes, but we should find ourselves in direful straits if the whole water carrying from lakes and rivers for men and animals had to be performed by human agencies. Far from this, a mighty apparatus is provided. The scanty aid that man can give only shows how little he is capable of. The entire atmosphere is a tremendous pumping engine, an enormous watering machine always at work, always receiving supplies of liquid from the ocean, from seas, lakes, rivers, always showering this water down again upon the land, as needful drink for plants and animals, as needful cleansing for all things. Air, the great carrier of water, in its wonderful strength and restlessness, bears vast layers of cloud to and fro, wafts away superfluous damp, drenches the dry and thirsty earth, fills ponds and lakes, feeds, nay, actually makes, the rivers, never flags in its ceaseless energy. If clouds hang low or fogs arise, we are glad of the moving air which sweeps them elsewhere. If the soil is caked and plants droop, we are glad of the moving air which brings rain. Thus our wants are supplied, and the wide water circulation of earth is carried on. Without circulation, without motion, stir, change, there cannot be life. Stagnation must mean death. Our earth, without her ocean of moving air, would be a world of death. Without air, earth would be in great measure a soundless world. Silence would reign here, as probably it does reign on the moon. Sound, as it commonly reaches our ears, depends for its very existence upon air. Let the concussion of two bodies be ever so mighty, if there were no air to bear away the vibrations of that concussion, there could be no crash of sound. True, sound waves can be conveyed through a liquid or through solid as well as through air, and we might be conscious of the ground's vibrations, but our ears would hear no noise. So an airless world would be a silent world. Without air, supposing we could ourselves exist, we should hear no trickling brooks, no rush of waterfalls, no breaking ocean waves, no sighing of the wind, no whisper of leaves, no singing of birds, no voices of men, no music, no thunder, no one of the 1,000 concomitant sound waves which together make up the babble and murmur of country and town. Those only who are perfectly deaf can know what such silence means. Without air, our world would not be in darkness, for light does not, like sound, depend mainly upon air for its transmission. Light travels through regions where air is not, and if light is communicated by waves, they are not waves of air. But though the absence of air would not deprive the earth of light, it would make a very great difference in the kind and degree of light received. Without air, the blue sky would be black as ink. Stars would glitter coldly in the daytime beside a glaring sun. Deep shadows would alternate with blinding dazzle, and all the soft tints of sunrise and sunset would be wanting. Earth would be like the almost airless moon, all fierce whiteness and utter blackness, with no gray shades, no rosy gleams, no golden evening clouds. Nay, without air there could be no clouds. On the moon is no twilight, for no air particles float about, reflecting the sunlight from one to another and forming a soft veil of brightness, to reach farther than the direct sunlight alone can reach. Sunbeams travel straight to earth, unbending as arrows in their flight, and unaided they cannot creep any distance round a solid body, though they may be reflected or turned back from it. But the air breaks up the sunbeams, bends them, diffuses them, spreads them about, surrounds us with a delicate lacework of woven light. A sunbeam traveling through space is invisible till it strikes upon some object. If that object is solid, the light of the sunbeam is partly absorbed, partly reflected. If the object is transparent, the sunbeam passes through and onward. Few substances, if any, are perfectly transparent. We call air transparent, yet it is so only in a measure. Each sunbeam passing through the atmosphere loses part of its brightness by the way, and so the great glare of the sun is softened before it reaches the lower depths of the air ocean. The sun's rays are rays of heat as well as of light. While the atmosphere softens the glare, giving us shade and twilight, it also modifies the extremes of temperature, from which, without air, we should suffer. When the sun goes down, although we are often conscious of a chill, it is not the instant and overwhelming chill which we should feel but for the atmosphere. All day long the sun has been warming the earth and air. When his direct rays are withdrawn, the warm air for a while keeps its warmth and gives over of that warmth to us. We talk often of warm winds and cold winds from different quarters. By warm winds we mean air that has passed over a warm surface of land or sea, so gathering up and bringing heat to us. By cold winds we mean air that has passed over a cold surface of land or sea, so parting with some of the heat it had in a measure and reaching us in a chilled condition. People in England are very much warmer than their friends across the Atlantic living no further north. Here the weather is mild when there it is bitterly cold. There they are frozen up, when here we have only a little fitful frost and snow. The main reason for this difference is that abundance of soft warm air comes drifting over us from a certain ocean current called the Gulf Stream, flowing northward in our direction from the tropics. Our friends across the ocean receive a like abundance of cold air from a cold ocean current, flowing southward from the frigid zone. All this would be altered had we no enfolding ocean of air. End of Chapter 2.
Chapter 3 of The Ocean of Air, Meteorology for Beginners. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Ocean of Air, Meteorology for Beginners, by Agnes GIBERNE. Chapter 3, The Weight and State of Air. If one would understand the atmosphere as a whole, one must learn something about the laws which govern its movements. That air is a substance, and therefore is heavy like any other substance, has already been explained. We are apt to talk of things as heavy and not heavy, as if some things had weight and some had not, but every substance, without exception, has weight. A certain gas, called hydrogen, does not commonly fall downward, but rises through the air upward. If we wish to send a balloon towards the sky, we only have to fill it with hydrogen gas, and it is sure to ascend. Yet hydrogen gas is a substance, and has weight. Only its weight is so very much less than the weight of common air that the air particles fall naturally below and press the lighter particles of hydrogen upward. This is how a balloon rises, not because it has no weight, but because it weighs less than air. A cork has weight, yet in water it springs to the top, because it weighs less than the same bulk of water. A feather, light as we count it, has weight, and if dropped in a closed vessel emptied of air, it will reach the bottom quite as fast as a lump of iron. From its light and spreading make, it is easily buoyed up and carried along by the slightest breeze. But if the air is still, it soon finds its way downward. Until nearly the middle of the 17th century, nobody so much as suspected the fact that air had weight. When Galileo was an old man of 76, he was the first to gain a glimpse of the long-hidden truth, and his pupil, Torricelli, followed out his experiments, proving him to be in the right. Weight is caused by a wonderful force or power, which holds sway not only on Earth, but in the sun and the planets, and throughout the universe, the force of gravitation. Every substance attracts every other substance towards itself with a greater or less degree of strength, dependent on the size, the make, and the distance of each. If no substance attracted any other substance, there would be no such thing as weight. When we speak of a mass of iron being heavy, we mean that the earth draws it downward. When we speak of the whole atmosphere having weight, we mean that it, too, is pulled earthward. The attractive force which causes all objects to draw nearer together, when not prevented, we know by its effects, and by its effects only. We see what it does, not what it is. That such a force exists, we perceive. That such a law or order prevails, we know. But what the force is in itself, and in what mode one substance influences another, none can tell us. Search as we may, and rightly may, into these things, solving one perplexity after another, we find ourselves surrounded still by baffling walls of mystery. We call attraction one of nature's laws, or one of nature's forces. Either term leaves us where we stood before. The forces of nature are the forces of the God of nature. The laws of nature are the laws of the God of nature. They constitute the plan on which the universe and all that is therein are framed. And because they are His laws, His forces, and because He is our Father, we, His children, may well search into them with the utmost of such powers as He has given us. The air of our almost invisible ocean is often described as an elastic fluid, but this gives no clear idea of its condition. A fluid may be either a liquid or a gas, and liquids are by no means the same as gases. There are three distinct forms known to us of the same substance upon Earth. These three states or forms are called the solid, the liquid, the gaseous. A simple illustration is to be found in the water. Suppose a man should travel to Earth from some far-off region of space, having never seen our common earthly substances, having never come across water in any of its various conditions. He must not, by the by, hail from the planet Mars, since there, at least, we have good reason to believe snow not only exists, but thaws, which means the presence of water as well as of ice. Suppose on arrival he should alight first upon a Greenland glacier, having hard ice all around him. He would naturally describe water as a species of rock, for thus far he would know it only in the solid or frozen form. If he landed first on the border of the ocean, in a temperate climate, he would describe water as a liquid. If his first acquaintance with it were in the shape of steam escaping from a boiler, he would describe it as a vapor or as a gas. He would not at once, without further observation, know that these three are one and the same substance under different forms. He would not yet know that ice can be turned into water, water into steam, steam into water, and water into ice. Nor could he guess that the force by which its presence or absence works these changes is heat. You have a solid block of ice, and a certain amount of heat is brought to bear upon it. Gradually, the ice becomes water. The solid is changed into a liquid, but the substance is the same. The particles which form the water are the same which form the ice, only under altered conditions. Again, more heat is brought to bear upon the water until it boils. Then gradually it changes into steam. The liquid has become vapor, but still the substance is the same. The particles which form the steam are the identical particles which form the water, and before that the ice, only a change has come over them. If the steam is not allowed to escape, but is kept in a confined space and cooled down, the particles will draw together again, and the steam will once more become water. If the cooling is continued, more heat being taken away until the freezing point is reached, it will turn again into ice. To the same ice which it was originally. The particles of matter are the same. The substance is not altered. It has merely passed through a series of changes of form. All solid substances are formed of minute particles, more or less closely bound together by a certain mutual attractive power, which we call the force of cohesion. Cohesion means sticking together. When we speak of the force of cohesion, we simply speak of the force of sticking together. But to speak of the parts of a substance sticking together is by no means to say why they stick together. And to talk of the cause as a force is not at all to tell how it acts. The how of this matter is again beyond us. For the attraction of cohesion is even more mysterious than the attraction of gravitation. We see both by their effects, but we do not know in what manner these effects are brought about. In a general way, when we speak of a law, we mean a command which has to be obeyed. By a law in nature, we mean rather a rule of action constantly followed by certain bodies under certain conditions. The word signifies not that the divine ruler has given definite commands which the world of matter obeys, but that the divine creator has impressed or endued each particle of matter with certain characteristics which, under the same circumstances, always result in the same modes of action or work. We speak often of substances obeying certain laws, but since the word obey implies choice and a possibility of disobedience, it is hardly a correct term. Each particle of substance merely does in each set of circumstances, and does inevitably that which is its nature to do. But how and why one minute particle of matter should differ so utterly in its nature from another is a profound mystery. Author's note. Since writing these chapters, I have come across the following sentence in a letter of Charles Kingsley's. Everywhere, skin deep below our boasted science, we are brought up short by mystery impalpable, and by the adamantium gates of transcendental forces and incomprehensible laws, of which the Lord who is both God and man alone holds the key, and alone can break the seal. Life of Kingsley, 2:7. In addition to the force of cohesion, which holds together the particles of any substance, there is another and opposite force, sometimes described as the force of repulsion, or the force of driving away. It seems singular that two such opposite forces should be at work in one lump of iron, or one piece of wood, that the very particles which are trying to get closer to other particles should also be trying to get farther away from them. Many things in nature are, however, brought about by such working of opposite powers. We are well able to see a need in the present case for both, if our world is to remain in its present form. Without the force of cohesion, there would be no solid substances at all. The whole earth and all it contains would be a scattered mass of loose, impalpable dust, too fine for the human eye to see. There would be no shapes or forms of separate bodies were it not for the force which binds their particles together. If, on the other hand, there were no check upon cohesion, changes of an exactly opposite kind would come about. The particles of each lesser substance and of the earth itself would shrink closer and closer together till the entire mass would have grown inconceivably small and hard. This shrinking and hardening would include the ocean of air. It is what we call repulsion among the air particles which keeps them apart. If the particles of any gas are forced close together by cold or pressure, it becomes a liquid. If they are forced still closer, it changes into a solid. Probably all earthly substances are capable of taking these three forms under certain conditions, though man has not always means at his command to work the changes. There are solids which have not yet been made liquid, and there are gases which remain persistently gases. For a long while, atmospheric air resisted all efforts, but at length, under intense pressure and cold, it was liquefied and even rendered solid. So if no force of repulsion existed to counterbalance the force of cohesion, Not only would the whole Earth become amazingly small and hard, but the whole ocean of air would be transformed into a solid harder than iron. It is through the opposite workings of these two forces that we have the three forms of matter: solid, liquid, and gaseous. In a solid, the cohesion is said to be greater than repulsion. In a liquid, the cohesion and repulsion are said to be equal. In a gas, the repulsion is said to be greater than the cohesion. The particles of a gas struggle to get far apart from one another. Unless confined on all sides, they fly away and are lost. This would happen with our entire atmosphere if it were not for the controlling power of gravitation. The ocean of air is tied and bound to the Earth by gravitation alone. In upper layers, where both the attraction of the Earth and weight of the overlying air are lessened, the separate air particles float much more widely apart, yet even there, even on the outmost limits of the atmosphere, they are still under the restraint of gravitation. At the level of sea, the atmosphere presses upon each square inch of the ground, and of every creature and thing upon Earth, with a weight of about 15 pounds. The whole atmosphere, all around the whole Earth, is said to weigh about 11 millions of pounds. So really, it is not astonishing that the lower layers of air should be packed tightly together. It seems extraordinary that we do not ourselves feel the pressure, since it is upon us as well as upon the Earth. On each square inch of our bodies, the atmosphere bears hard with a force of 15 pounds weight, which means over 2,000 pounds upon the square foot, and something like 30,000 pounds upon the whole body of an ordinary-sized man. Try to lift a load of 100 pounds, then think what it would be to have 20 times that weight lying upon your chest. You could only expect to be crushed and killed. Some such result would doubtlessly come about, but for the fact that the pressure existed everywhere. Air is not only outside, but also inside us. It not only surrounds, but pervades our frames. We, it is true, are in the air, and no less truly, the air is in us. Pressure from without is counterbalanced by resistance from within. This fact of air pressure can be shown by an ordinary air pump. Before the air is pumped out of the bell-shaped glass, it may be lifted by a finger, but when the air is gone from within, the outside air bears upon it so heavily as to make the glass immovable under one's utmost efforts. It is literally jammed down upon the wooden stand. If the glass were not very strong and shaped for resistance, it would be shivered into pieces. Atmospheric pressure, acting equally in all directions, is due to its make as a gas. The particles of gas are in a state of ceaseless unrest, forever hurrying to and fro one among the other with immense speed, perpetually striking against each other and against the sides of any vessel in which the gas may be confined. Each particle of air is always on the rush, always striking and rebounding from its neighbors, and any solid or liquid substances which lie in its path. If a tumbler is filled to the brim with water, and a piece of blotting paper or other soft paper is laid over it, the glass may be carefully turned upside down, and the whole body of water will be borne up by the wet paper. That which keeps the paper in position is neither more nor less than the ceaseless cannonade of invisible air particles, millions of minute pellets of air banging upwards each instant against the paper from outside and holding it up. It is this incessant battery of air particles which constitutes the pressure of air against the sides of a vessel, upward, downward, within, without, and always. It is this which, as above stated, when acting within a closed box or within the limits of the human frame, is sufficient completely to counterbalance the outside pressure. It is in this way, through the unceasing hail of innumerable air particles on the basin of a barometer, that the mercury is held up in the barometer tube. The same explanation serves also for the rising of water in a pump. Moreover, the degree of pressure varies at different times and in different places. A cubic foot of common air near the surface of the earth generally weighs a little more than 1.25 ounces. In other words, it generally presses with a degree of force not downwards only, but in all directions. Generally, not always. The degree of pressure is proportional to the number of air particles within the cubic foot of air. The more dense a certain portion of air is, that is to say, the more closely its particles are packed together, the heavier its pressure. Thus, the weight of the atmosphere, generally caused by gravitation, increases the density of air near the surface of the earth, and thereby increases its pressure. The amount of pressure is also increased by heat. If a cubic foot of air is enclosed in a vessel of the same size and is then heated, The pressure against the top, bottom, and sides of the inside of the vessel becomes greater, because heat increases the energy of the air particles and so adds to the force of their battery. End chapter 3.
Chapter 4 of The Ocean of Air, Meteorology for Beginners. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Elizabeth Miles. The Ocean of Air, Meteorology for Beginners by Agnes GIBERNE. Air as a Mixture. Chapter 4, Air as a Mixture. The air breathed by us and by all living creatures upon earth is not a simple gas, but a mixture of gases. Now, there are more ways than one in which different substances can be mingled together. You may put a lump of sugar into a cup of tea and stir well. The sugar vanishes, yet it is still there. The separated particles float in the liquid, sweetening it. Though not seen, they may be tasted. No chemical change has taken place, no real union of two substances into one. The tea remains tea, the sugar remains sugar. Or you may mix together a small quantity of powdered iron with powdered sulfur. Mixed thus, they are not united. The iron is iron still, the sulfur is sulfur still. But push the mixed powder into a little heap and touch it with a lighted match. A red glow will creep through the hole, and an entirely new black powder will be the result, formed itself out of iron and sulfur, yet in itself neither iron nor sulfur, but an utterly different thing. The iron is gone, the sulfur is gone, and something else has sprung into being. This is chemical change. It is the combining of the two or more separate substances into another and different substance. It is not the mere mixing together of two substances, which remain still the same that they were before. Every substance that we see or know is either simple or compound. If simple, it consists of one original substance, which, so far as we at present know, cannot be broken up into other substances. If compound, it is formed out of the union of other substances, and therefore it can, by one mode or another, be broken up. Iron is a simple substance. A mass of pure iron cannot be divided by the chemist into any other substances. It can be melted into a liquid and transformed into a gas, but the liquid and the gas are iron still. Gold is another. It can be melted, and with enough heat it might be vaporized, but the gold always remains gold, undergoing no real change. The chemist can split up or analyze many things, but when he comes to a simple substance, he has reached a shut door and can make no further advance. It would not be safe to assert that all so-called simple substances are absolutely simple. They may be compound, though man has not yet discovered the fact, but in relation to our knowledge they are, at least for the present, simple. Water is a compound substance. It is made of two gases, oxygen and hydrogen. The two gases, separate, are each invisible. When united, they are seen and known as the liquid substance water, the solid substance ice, the gaseous substance steam or vapor. Simple substances are also called elementary substances or elements. About 67 are known. A few among the 67 are enormously abundant, while others are scarcely ever met with. They fill much the same place in the world of matter as the alphabet fills in the world of literature. All words are made out of the letters of the alphabet variously put together. All substances are either simple, that is, they are single letters of the alphabet, or else they are made up out of simple substances variously combined. The air of the atmosphere is a simple mixture of two simple substances, nitrogen gas and oxygen gas. A mixture, not a chemical combination. The two are mingled together much as tea and sugar are mingled, floating in close companionship without becoming one. No change has passed upon the nature of either, and no third substance is formed. Each gas keeps its own character. Oxygen is rather heavier than nitrogen, so one would expect the oxygen sometimes to sink, the nitrogen to rise. But this is not the case. Almost invariably, air is found to be a mixture of the two gases in the same proportions. No doubt this is more or less due to the ceaseless movements of air, the perpetual mixing by winds. Whether a portion of air is examined from a mountaintop, from a level plain, or from a deep mine, the mixture is almost exactly the same. Variations there are, enough to tell upon man's health, yet they are at most extremely slight. The amount of nitrogen in the air is always about 4 times as much by measure, footnote, by measure, not by weight, since oxygen is the heaviest, end of footnote, as the amount of oxygen. If one should divide a certain quantity of air into 5 almost equal parts, separating the two gases, 1 part should be oxygen, 4 nitrogen. Or, to put it differently, suppose you have 4 gallons of nitrogen gas and you wish to transform it into common air. You must add 1 gallon of oxygen gas and shake them well together. Besides the 2 chief gases of which air is made, a small quantity of carbonic acid gas and a still smaller quantity of ammonia gas are also to be found in it. If you had 10,000 gallons of air, 1/5 of which would be oxygen and 4/5 nitrogen, only about 1 gallon of carbonic acid gas would be distributed thinly through the whole. As for ammonia gas, only 1 gallon in amount is spread among 1 million gallons of air. So we can hardly speak of these two as having a large share in the make of the atmosphere. They are rather a slight addition to it, a kind of flavoring, if one may so express it. Yet carbonic acid gas, despite its comparatively small amount, is of the greatest possible importance, and indeed, though the quantity may seem slight viewed beside the other gases, it is by no means slight as a whole. The entire mass of carbonic acid gas always present in the ocean of air is simply enormous. Beside the gases, there is invariably more or less water in the atmosphere, hidden away in the form of vapor. If you had 1,000 gallons of air, you would find spread through them from 4 to 16 gallons of invisible water gas, or vapor. The amount of carbonic acid gas and of water vapor is not constant, but varies incessantly at different times and in different places. There are also countless specks of matter floating through the air ocean, especially in its lower regions. But the amount of these specks I cannot give in gallons. Probably no one has ever even tried to reckon their quantity. We have now found in the air we breathe these things: nitrogen gas, oxygen gas, carbonic acid, ammonia gas, vapor of water, floating dust. End of chapter 4.
Chapter 5 of The Ocean of Air, Meteorology for Beginners. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by John Brandon. The Ocean of Air, Meteorology for Beginners, by Agnes GIBERNE. Chapter 5, Air as a Part of Earth. Most people know that the Earth is not at rest, but is in perpetual motion, spinning like a huge top, and also rushing like an enormous ball round the sun. I want you now to think steadily about the spinning movement of Earth, about her daily whirl, top-like, round and round, upon her own axis. If you stick a knitting needle through an orange and spin the orange upon the knitting needle, keeping the needle itself fixed, this will help you to see the daily rotation of Earth. The Earth is a huge globe, about 8,000 miles straight through, from the North to the South Pole, and from the equator on one side to the equator on the other side. The movement of Earth's surface as she spins is very little indeed near the poles, while on the equator the surface travels round at the rate of over 1,000 miles an hour. A man standing on the equator is carried along at that rate always without the slightest effort on his own part, borne onward irresistibly by the rush of the solid ground on which he stands. But suppose he gets into a balloon and rises into the air 1, 2, 3 miles upward, what happens then? Why then, of course, as the earth whirls away from beneath him, he will be left behind, floating in the still atmosphere. What more simple? Well, yes, it sounds very simple. The most natural answer. There was a time when it would have been counted entirely correct. Yet the consequences of such a state of things would be by no means simple. We know a little more about the matter now. Suppose the balloon to start from the island of Sumatra, exactly on the equator, to the south of Siam. The solid ground there spins perpetually round the center of the earth at the rate of 1,000 miles an hour. The balloon rises upward in the calm air, on a still day, towards the blue tropical sky. As the surface of the earth below rushes from west to east at this tremendous speed, more than 14 times as fast as the fastest express train, you would expect the man in the balloon to be left behind. I do not mean that he would be blown by winds in any particular direction, but merely that as the earth rushes away, the balloon would be stationary, floating placidly at rest. If this were the case, and the balloon could remain undisturbed by currents of air, the man would only have to float reposefully in the same spot, and in the course of 24 hours, the whole circle of the equator would pass beneath him. He would see in succession the Indian Ocean, Africa, the Atlantic Ocean, South America, the Pacific Ocean, and lastly, the islands from which he started. A wonderful vista indeed. But practically, a man in such a position has no such magnificent diorama presented to him. He rises from Sumatra, and the earth's surface is spinning at the rate of 1,000 miles an hour, spinning along but not spinning away. For as he rises, he looks down upon Sumatra still. If the air were perfectly breezeless, he might rise to any height at which he could breathe, and Sumatra still would lie outspread below. If the wind were easterly, he would find himself soon looking down on the Indian Ocean. If the wind were westerly, he would travel towards the Pacific Ocean. The explanation lies in the fact that the atmosphere is attached to the earth and whirls with the earth. Air, remember, is a material substance, not solid, but formed of particles of matter. It is held fast to earth by the force of gravitation. Each particle of air has its share in the motion of the solid body to which it belongs, to which it is tied by its own weight, that weight being due to gravitation. Earth and atmosphere are practically one, and they act as one in the daily whirl. I do not say that there is no lagging behind of upper layers of air anywhere upon Earth, but taking the matter generally, the entire atmosphere spins with the spinning Earth. The air in any one part has precisely the same motion as the ground on or near where it rests. So a balloon or a bird in the air is carried with the air in its daily rush around the Earth's axis. Imagine what the results would be if things were otherwise, if the air remained fixed while the surface of the Earth whirled away beneath. We all know the effects of a high wind or a hurricane. Now, wind is simply air in motion. If the air were utterly at rest, you may say that at all events we could then have no wind. But the effects of wind may be brought about in two ways. One way is by the motion of air against still objects. The other is by the motion of objects through still air. Whether the air rushes fast against a man or whether a man rushes fast through the air makes no real difference. In either case, the effect is the same. In either case, he is struck with the same degree of force by the resisting particles of air. If the atmosphere were at rest, there would perhaps not be a wind, strictly speaking. Nevertheless, if you on the equator were careening at the rate of 1,000 miles an hour through still air, the effects upon yourself would be precisely the same as if you were at rest, and the wind were careening past you at that rate. A powerful hurricane travels at the rate of 90 miles or more an hour, and the most solid buildings often cannot stand against it. The heavy pressure of air particles crowding one upon another in their frantic rush will level massive walls, tear off roofs, lay trees flat. You may suppose, then, the destruction that would be wrought by a hurricane blowing not at the rate of 90 miles, but of 1,000 miles an hour. The results must prove equally overwhelming, whether caused by the rush of air past us or by our rush through the air, for in either case the fierce resistance of air particles would be the same. A man standing on an engine going at the rate of 60 miles an hour has a powerful wind in his face. The air may be equally still, no breeze stirring it, yet his steady advance along the motionless air particles will cause him to have exactly the same sensations as if he were at rest and a strong gale were blowing. To all intents and purposes, it is a gale. The pressure of air resisting his passage is in no whit different whether his movement or its movement be the cause. In the case that we have supposed of the solid earth revolving while the atmosphere above remains at rest, the resistance of the air in equatorial regions would be tremendous, past imagination. Nothing loose or movable on Earth's surface could stand against it. Men and animals, trees and buildings, rocks and stones, boats and ships, nay, the whole mass of ocean water itself, would be kept back by the enormous pressure of the atmosphere, acting as a terrific hurricane, and would be swept in one rushing pell-mell torrent of ruin over the revolving surface of the earth, in the contrary direction to Earth's whirl. Complete chaos and destruction could alone ensue. This widespread destruction is prevented by the simple fact that as the earth whirls, her enfolding vesture of air whirls with her. Practically, indeed, things not only are so, but must be so. The atmosphere, weighted by gravitation, clinging to Earth, must move with the Earth. That the Earth should revolve, and the atmosphere not revolve, is an impossibility. The layer of air lying close to Earth's surface is dragged round by the Earth, and drags round the layer above, which in its turn does the same for the next, and so on upward. Or rather, if the atmosphere were by any possibility at rest, it would in this manner be speedily set going. Once made to revolve, it is certain to go on revolving until stopped by some other force. Yet so calm, so soft, so steady is the motion, despite its great speed, that we upon earth carried smoothly along by the solid ground and the elastic air are not conscious of it by sensation. This same partaking of the motion of another body may be seen on a smaller scale in common life. Suppose a ship to be sailing over the sea and a man standing on the deck. That man is borne onward by no exertion of his own. He remains perfectly still. He makes no effort to advance. With relation to the ship, though not with relation to the sea, he is at rest. He does move, but only as a part of the ship, as sharer in the ship's motion. A man seated in a train has a motion in common with the train. As the train travels, so he travels. and so the air in the closed compartment travels. Outside, the particles of still air strike the moving train with sharp resistance. Inside, both air and man are borne along as part of the train. The resistance of air particles to any body passing among them may appear a slight matter, yet it works a weighty part in the affairs of this world, not to speak of other worlds, where also enfolding atmospheres exist. End of Chapter 5. Recording by John Brandon.
Chapter 6 of The Ocean of Air, Meteorology for Beginners. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Elizabeth Miles. The Ocean of Air, Meteorology for Beginners by Agnes GIBERNE. The Resistance of Air. Chapter 6. The Resistance of Air. If you draw your hand quickly through water, you are aware of a counterpressure. The water seems trying to hinder or push it back. A man swimming in the sea or rowing a boat is keenly conscious of this. The same resistance, though not to the same extent, is found in the ocean of air. The particles of a gas are less densely placed, less close together than those of a liquid. Therefore, a body moving in their midst can more easily thrust them aside to make way for itself. Still, there always is a measure of resistance. This fact of air resistance is a serious item for consideration in the matter of motion generally. There are many bodies on Earth at rest and many in motion. Those at rest have usually to move sooner or later. Those in motion come, as a rule, sooner or later to rest. Two main rules govern the condition of objects in motion or at rest. One is well known, the other not so well known. They are these. 1. A body at rest is never set in motion except by force. 2. A body in motion is never brought to rest except by force. The first of the two everybody will assent to at once. We all know that a ball does not set itself rolling, that a train will not start itself, that a cannon cannot fire itself off. A certain amount of power or force must be exerted upon a body from outside to make it move, and it must always be enough force to cause the particular movement required. A man's hand can throw or roll a ball of India rubber, but a man's hand cannot start a train. Even in the case of a man walking, though in a sense he does set himself going, yet this only means that his will takes the place of the outside force and causes his muscles to act. But to say that a body in motion can only be stopped by force, that is another matter. Do we not all know that nothing on earth continues moving forever? Do we not all know that everything inevitably stops sooner or later? Have we not seen for ourselves how the swift cannonball, the whirling grindstone, the spinning top, the swinging pendulum all come to repose? Did not our ancestors search in vain for perpetual motion, wasting time and money in a hopeless quest, because no motion of bodies on earth ever is perpetual? Yes, true enough all this, yet none the less true is the rule given. Motion is never stopped but by force. No single body will ever move unless it is made to move. Once set going, it will never cease moving unless it is brought to rest by the exercise of a counterforce. For motion is as naturally permanent as rest. Rather difficult to believe, is it not? Yet this is a fundamental fact. You see a big rock lying on a mountainside, and you are quite ready to ascent, when somebody remarks that the rock will not stir without being made to do so. There is a certain reluctance to change its present condition, a stubbornness or inertia about the rock. This inertia chains it to the spot where it lies, until some outside force shall be exerted to set it going. But suppose such a force is exerted, and the great rock is sent rolling, leaping, crashing fiercely down the steep mountainside. We have now a new state of things. The rock is no longer at rest, it is in motion. The stubbornness, the reluctance to change its present state, a state of motion, The inertia, in short, of the rock continue as before, though manifested differently. Then the rock was at rest, and it would not move without being made to move. Now the rock is in motion, and it will not stop without being made to stop. Not stop! You are hardly so ready to assent to this as to the former statement. Of course it will stop, so soon as it reaches level ground. Yes, of course. Concussion with the level ground will prove to be a sufficient checking force. I did not say that the rock would never cease to move. I only said that it would not stop without the exercise of force. No doubt a sufficient force will be exercised by the resisting ground. In this world there always is a sufficient checking force to bring all moving bodies to rest. That fact does not in the least detract from the truth of the opposite fact that, if no checking force existed, the body would not cease to move. Take a tennis ball in your hand and fling it high. That tennis ball will go on forever unless stopped. Fire a bullet from a rifle. That bullet will speed onward forever unless stopped. Set a grindstone whirling fast. That grindstone will whirl forever unless stopped. Make a top spin steadily. That top will spin forever unless stopped. These things always are stopped, but they do not stop themselves. They do not come to rest of themselves. Always, invariably, sufficient force is used by something or somebody to bring them to a state of repose. The great checks to continued movement on earth are commonly reckoned as two: friction and the resistance of the air. These two may almost be reduced to one, for the resistance of the air is really only a delicate form of friction. It means simply the striking and rubbing of the tiny particles of air against anything passing through the midst of them. The attraction of the earth is another great hindrance to motion, but this also comes under the head of friction. The earth draws the moving or falling body downward, then friction against the ground, rocks, or water causes it to stop. So by friction we mean the touching and rubbing of other substances. If you touch a spinning top ever so lightly with your finger, you will see at once how great is the checking power of a touch to anything in motion. As a rule, the word is used with reference to solid bodies, but the resistance of water particles and air particles practically amounts to the same thing. A great cannonball is dispatched from the mouth of a huge cannon, whizzing, whirling, tearing along, ready to destroy aught that may lie in its path. The force which has started the ball is the gunpowder explosion, the sudden change of a solid into a gaseous form, and the consequent tremendous pressure of gaseous particles fighting to escape, thus overcoming utterly the stubborn inertia of the ball at rest. But when once the ball is off, some other force equal in degree is needed to overcome the stubborn inertia of the ball in motion before it can be brought to rest once more. Only instead of being a single sharp exercise of power, pent up in a tiny space and in one moment, it may be a slow and continued exercise of force, gradually acting. If no such force is exerted, the ball will rush on forever, always in a straight line, always at the same speed. First, the air particles begin. It is wonderful to think that such weak, floating, infinitesimal specks of matter can have the smallest effect upon a mighty cannonball. Perhaps you have never been underneath a cannonball fired from a large gun, and so have not heard the furious rush and whiz of its passage among those air particles, sounding like a small express train careering over your head. If you had, you would realize that the opposition which they offer is by no means contemptible. Singly, they are soft and weak, but banded together, acting in concert, they are strong. From the moment that the ball leaves the cannon, they are at work. Each air particle which lies in the path of the ball, only to be fiercely thrust aside, only to seem an utter failure, has done its tiny task. The air particles alone, unaided, would in time bring the great ball to rest. But something else is at work also, in conjunction with the struggling particles of air. Earth is dragging at the ball with her ceaseless pull. The force of the explosion may send it far upward, yet soon the pull of earth tells, and a downward curve begins which presently lands the ball upon the ground. For a while still it may leap and bound forward, but with every crash of contact a further check is given, and at length the moving body is at rest. Yet remember, the cannonball would never of itself have traveled in a curved path or with slackening speed. It would have gone on interminably, always straight forward, always at the same speed. Without the resistance of the air, the attraction of the earth, and the friction of the ground, it would not have stopped. So there was a sufficient cause for the starting of the cannonball. There was a sufficient cause for its moving in a bent path. There was a sufficient cause for its going more slowly. There was a sufficient cause for its coming to a standstill. There is always a sufficient cause for every movement, and for every change of movement in a moving body, just as much as for any movement at all in a body hitherto at rest. We thus see distinctly that it was the inertia of the heavy cannonball which made a strong explosive force needful to start it in swift career. Once started, it was the very same inertia, differently shown, which made the continued resistance of air and earth needful to bring it to repose. A curious calculation has been made illustrating how great is the resistance of air particles to a body moving with great rapidity. A cannonball is fired off and travels, let us say, some 6,000 feet before touching the ground. If the air offered no resistance, it would have sped to a distance of over 20,000 feet in one unbroken rush. The nearest approach to unceasing motion on Earth is to be found in a pendulum hung in a vacuum from a hard, fine point. There, no soft, elastic atmosphere checks the steady swing. Nothing checks it except a very slight degree of friction at the point from which it hangs. Still, some amount of rubbing always does and must exist at that point. The pendulum may swing for hours, even through a whole day, but sooner or later it has to stop. The only apparently perpetual motion of which we can speak with confidence is that of the heavenly bodies, the whirling and revolving suns and worlds. Our Earth is one of those worlds. Her movements have lasted through ages unchanged, since the hand of God sent her forth upon her celestial pathway. How she was first set going we do not know, and how long she will continue to move we do not know. All we know is that sufficient force must have been exerted to set her whirling and revolving, and that no sufficient force has ever since been exerted to bring her to a standstill. In the wide regions of space, no air exists to check her movements. The earth carries the atmosphere with her as she rolls onward, a soft surrounding vesture, a deep translucent ocean, a very part of herself. There is no vast ocean of air throughout space. The stars and planets roll unhindered through centuries of centuries with calm, continuous whirl. Something, indeed, there probably is, though not air, something unspeakably thinner and lighter than our atmosphere, something so rare and fine that we can scarcely more than guess at its existence. But if this something which we call ether does indeed extend through space and can exercise any checking force upon the heavenly bodies, it is a force so slight, so slow in action that no results are yet apparent. To man, watching with dim eyes from the lower levels of the air-ocean, the motions of the suns and worlds through thousands of years show no change. End of chapter 6.
Chapter 7 of The Ocean of Air, Meteorology for Beginners. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by John Brandon. The Ocean of Air, Meteorology for Beginners by Agnes GIBERNE. Chapter 7. The Uses of Oxygen. We must now learn a little more about the separate gases which, mixed together, make our ocean of air. Wherever atmospheric air is found, it consists, as explained earlier, of about 4/5 by measure of nitrogen to 1 of oxygen. Though the quantity of nitrogen is so much greater than that of oxygen, yet the oxygen may well claim our chief attention. Oxygen is the great life-supporting power on Earth. Without oxygen, plants could not grow. Without oxygen, animals could not exist. Also without oxygen, fire could not burn. Nitrogen does little positive work in comparison, but rather fills the humble office of a make-weight and a drag upon the intense activity of its companion. One of the compounds of nitrogen, from which indeed comes its name, is nitre. Another is nitrous oxide, well known under its old name of laughing gas. If breathed under particular conditions, it causes a kind of intoxication, and when in that state men act in a strange and laughable manner. It is now much used by dentists and also by surgeons in smaller surgical cases for the deadening of pain. As its name tells, it is formed of nitrogen and oxygen. Nitrogen is found in the solid earth, as well as in the ocean of air. It has a share in the make of plants and animals. No unimportant share in the case of animals, for without nitrogen, neither blood nor muscle could be formed. Pure nitrogen is colorless, tasteless, and scentless. It is called inert or slow and heavy from its seeming reluctance to unite with other substances. It does unite with some, but not readily. Oxygen, on the other hand, seems always to hold itself open to combine as fast as possible with almost any other substance. One might liken these two gases, with their opposite characteristics, to two opposite characters often seen in men. The first, dull, slow, holding aloof from other people, cautious and cold, rarely making friends. The second, eager, sparkling, warm-hearted, prepared to rush into enthusiastic friendship with nearly anybody who may come in his way. Nor is it difficult to understand how, if these two lived and worked together, the slowness, caution, and coldness of the one would act as a check upon the eagerness of his impulsive companion, just as nitrogen does upon oxygen. Suppose you have two closed jars, one full of pure nitrogen gas, the other full of pure oxygen gas, and also a little wax candle, like those which are used for Christmas trees. If you light the candle and lower it into the nitrogen gas, not letting the gas escape, and not letting any air get in, the flame will at once go out. But if you put the lighted candle into the jar of oxygen gas, it will burn much more quickly and brightly than in common air. Nitrogen gas cannot support combustion. In common air, oxygen does all that work, and nitrogen only hinders it. Pure oxygen apart from nitrogen is a tremendous quickener of fire. Suppose, instead of putting a lighted candle into either of the closed jars, you were to put a poor little mouse into each. I'm not advising this act, for if needless, it would be cruel. But suppose it had to be done. The mouse in the nitrogen would quickly die of suffocation. He would not be poisoned, for strictly speaking, nitrogen is not poisonous. The little creature would simply die from lack of oxygen, would die because the nitrogen is dull and powerless to do for his little frame what is needed to keep it going. Nitrogen can no more support life than it can support fire. The mouse placed in pure oxygen would not be suffocated, but it too would die, though not so quickly, of the too strong oxygen. We all know the effects of a very strong pure air, that is, air which has rather more than the usual quantity of oxygen. It excites and exhilarates the whole frame. To breathe perfectly pure oxygen for any length of time would have the same effect, but in a very intense degree. It would be an extreme case of what is called overstimulation. If our atmosphere could get rid of all its nitrogen and consist of oxygen alone, the whole of mankind would be speedily laid low, or driven mad with desperate fevers, burning away their strength. And if any building in a town caught fire, the whole town would be ruined, the flames spreading with such ruthless fury that all efforts to check them would be in vain. Thus we find the need of the dull, deadening nitrogen to control the too exciting oxygen. The oxygen has, in fact, to be weakened for our use, just as many a strong medicine has to be diluted with water before we can safely drink it. Nitrogen gas has been changed by chemists to a liquid, and even to a solid, described as a snow-like crystalline mass. Oxygen gas also has been liquefied and is capable of becoming a solid. In other words, of being frozen. Both these are always gases on Earth in their natural state, great cold or great pressure being needed to change their state. When either is combined, however, with other substances, the result is often a liquid or a solid. Like nitrogen gas, oxygen is colorless, invisible, tasteless, and scentless. There are enormous quantities of oxygen on Earth, apart from what is constantly flowing free in the ocean of air. The rocks of Earth, piled often to mountainous heights, are in their make nearly 1/2 oxygen by weight. The stones, big and little, which lie scattered by millions on Earth's surface, are in their make nearly 1/2 oxygen by weight. The soils of Earth, from which sprout grasses, plants, and trees, are in their make nearly 1/2 oxygen by weight. The waters of Earth, seas and rivers, ice fields, clouds, and vapor, are in their make not only 1/2, but 8/9 oxygen by weight. And when we come to examine the bodies of living things, both plants and animals, we find them also to contain in their make a goodly amount of oxygen. In fact, if the whole of our solid globe were broken up into all its component parts, that is, into the separate substances of which it is composed, each different substance being placed alone, the heaviest supply of all would be the oxygen supply. Nearly 1/2 by weight of the entire mass would be pure oxygen. I say distinctly by weight and not in size. Oxygen might be far the heaviest heap without being the biggest. Many light substances take up more room than heavy ones. If you have a gallon of water, that water has in its make 8 times as much oxygen as hydrogen by weight. Yet if the water is divided into the two gases, it will be found that the hydrogen takes twice as much room, or is twice as big as the oxygen. For hydrogen is light and oxygen is heavy. So we see that oxygen is one of the most important elements on Earth, and also that we have a very large supply of it. But if questioned what oxygen really is, I can only answer that it is, or appears to be, a simple substance. It will unite with or separate from other substances, yet in itself it remains unchanged. It can never be broken up into other substances. Seeking to analyze the make of oxygen, we come to one of those fast shut doors spoken of earlier. Thus far seems to be uttered, and we can go no farther. By and by, it is true science may find a mode of opening that closed door and getting through. If so, the mystery will only be pushed a little farther back. Another closed door is sure to lie not far behind. This is always the case. With our present powers, we never do or can get to the end of anything, with no mystery lying beyond. One might almost say that if we could, that would be the greatest mystery of all. At present, oxygen is, as to its real nature, a shut door. We know of its existence, we see what it does and what it cannot do. We are acquainted with its peculiar characteristics, its especial modes of action. We are aware what we expect from oxygen in particular circumstances. That is about all. Oxygen is by no means stationary, fixed in certain positions through countless ages. Portions of oxygen may remain very long fixed in such solid bodies as rocks and stones, though even they are subject to waste. But oxygen in general is remarkable for its activity, its love of change. A perpetual intercourse is kept up between the oxygen of the earth, of the sea, and of the air, between the oxygen of living creatures and of things without life. Oxygen is forever passing into structures and out of them again, becoming part of organisms and leaving them, uniting with other elements and breaking loose from them, entering into the make of liquids, only to separate itself anew, feeding flame and life and growth, but in the very act finding renewed freedom, ready always to be caught and fixed by the next substance which may come in its way under the right conditions, yet seldom content to stay long in any combination where escape is possible. Thus a ceaseless circulation of oxygen is kept up. There are other circulation systems to be noticed later. There is the circulation of blood in a living animal. There is the circulation of air. There is the circulation of water. But this circulation of oxygen is not the least remarkable of them all. Almost all substances will unite with oxygen to form fresh substances. These others, springing from the union, are called oxides, and the act of combining is called oxidation. To cause such union, a certain amount of heat must be brought to bear upon the different substances, and not always the same amount. Some substances require more, some less, before they will unite. Whenever chemical combinations take place under the influence of heat, there is also a giving off of heat by the bodies as they unite. This is the invariable rule, though the heat may not always be felt or seen by us. If the union takes place very slowly, as in the forming of iron rust, the heat given out will be gentle and imperceptible. If the union takes place fast, as in the burning of a piece of wood, there will be sensible warmth and a red glow, perhaps flame. If the union takes place with extreme suddenness, as in a gunpowder explosion, there will be great heat, a bright flash of flame, and a loud noise. End of Chapter 7. Recording by John Brandon. Chapter 8 of The Ocean of Air, Meteorology for Beginners. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by John Brandon. The Ocean of Air, Meteorology for Beginners, by Agnes GIBERNE. Chapter 8, What is Meant by Burning? Something is meant by burning which has a great deal to do with the ocean of air around us. For if there were no air, there could be no combustion. On a cold winter's day, there's a fire in the sitting room. The flames play around the coal, and gradually the lumps of coal grow smaller, till they disappear. If more coal is not heaped on in time, the fire goes out. What becomes of the coal? It is burnt, of course, Any child could answer that question. But what does being burnt mean? Suppose we have an iron ball in the grate, lying among the burning coals to fill up some of the space. This ball gets red hot, like the coals, though it does not, like them, pass out flames. Heat is very catching and passes readily from one object to another. The iron ball seems to burn like the coals, yet, unlike the coals, it shows no tendency to disappear. It does not even get perceptibly smaller. When the fire dies out and the red-hot ball grows cool, it is seen to be unchanged. If the one burns and vanishes, why does the other burn and not vanish? This question is easily answered. The iron ball does not burn. Some substances burn easily and some not easily. Some will burn at any time in common air, and some only under particular circumstances. Iron is a substance which will stand fire. It can be made red-hot or white-hot, melted, and even turned into a gas, but it will not burn in common air. So becoming red-hot or white-hot is not necessarily the same as burning. But though iron will not burn in air, it can be made to burn, really to burn, lessen in size, and disappear like wood. If a piece of iron wire is placed in a vessel filled with pure oxygen gas, it can be set alight and will burn away as easily as a wooden match. In the end of the last chapter, I spoke of fast and slow combining and mentioned iron rust as an example of slow combining. Now, iron rust simply comes from the union of iron with oxygen, generally at a slow rate in a damp place, and it is called oxide of iron. But this same oxide of iron, or iron rust, can also be produced quickly by burning a piece of iron in oxygen gas, as above described. Then again, the iron unites with oxygen, and iron oxide or rust is formed. Only as the union takes place fast, much more heat is given forth in a few seconds. The more rapidly heat is sent out in burning, the more intense it is. Whether the rust is formed fast or slowly, the actual process is the same. It is oxidation. We call the one a case of burning and not the other. Yet the only real difference between the two is in respect of temperature and speed. The common rusting of iron in a damp place really is a species of very slow and languid combustion. What becomes of the coal in the grate when it burns and diminishes in size? The coal is divided and goes three ways. Part rises up the chimney as smoke or soot. Part falls below as ashes. Part unites invisibly with oxygen from the air, causing heat and flame in the act of union. You have seen that iron can unite quickly with oxygen by burning, as we usually understand the term, only when it has to do with pure oxygen unweakened by nitrogen. But coal or wood, when sufficiently heated, can take the oxygen out of the air, leaving the nitrogen behind. So we say they burn easily. If the fire has been allowed to get too low, and fresh coal put on will not catch, what then? Why, then we use the bellows, and pour a supply of fresh air in gentle streams upon the reddest spot remaining, in the hope that a new and abundant supply of oxygen gas will awaken the half-dead embers and revive the flame. The oxygen gas in the air lying close to the coals has been pretty well used up, but a fresh supply will give what is needed. Coal alone, without oxygen gas, cannot give us flame and heat, for oxygen is the great quickener and supporter of fire. If we could banish all the oxygen gas from the room, keeping only nitrogen gas, any amount of paper, wood, and coal might be put into the grate, and the bellows might be used to any extent, yet to no avail. The fire would at once die out. Nitrogen is powerless to keep it alive. So now we see the object of bellows to wake a dying fire, just that a fresh supply of the needful oxygen may be given. Wisdom is profitable to direct, saith the wisest of kings. One cannot but remember these words when watching an uneducated maid puffing away at a lump of black coal without the slightest result. A very little wisdom would teach her to direct the stream of fresh air towards a red spot where alone it can take effect. If bellows could be made as to feed the fire with pure oxygen gas, then at any time the last spark of a dying ember might be roused with ease into fresh life. Such bellows would also have a curious effect on the red-hot iron ball. Under a steady play of oxygen gas, the ball would begin to waste away like burning coal. When anything burns, it not only gets red-hot, but also there is a rapid loss of material. It grows smaller and smaller, and almost or quite disappears. Either part or the whole of its substance unites with the oxygen of the air and passes out of sight into the atmosphere. This is what we mean by a body burning or being in combustion. To make a body red-hot is enough often for combustion without flames. Where inflammable gas exists, that is, a gas which will unite quickly with oxygen, there will be flame. Usually flame arises not from a solid or a liquid, but from a gas in combination. When flames play around a burning lump of coal, they are caused by the escaping hydrogen. Some substances will grow only red-hot and waste, but will not show flame. Any body intensely heated and glowing, not yet lessening in size, losing weight, or uniting with oxygen, does not burn. The heated object is then said to be ignited or incandescent, but not in combustion. If a piece of magnesium wire is held in the flame of a gas burner, it'll take fire, burn brightly, and waste away, growing shorter. If a piece of coiled platinum wire is held in the flame, it will become hot and glow brightly, but there will be no perceptible loss of material. So the magnesium wire is said to be in combustion. The platinum wire is said to be in a state of incandescence. We see an instance of the latter in many of the new electric lamps. A thread of carbon is shut up in a glass bulb from which all air has been expelled, and it is then made red or white hot by a stream of electricity. But it does not burn. It only glows. It cannot burn, for there is no oxygen within reach, and the burning of a substance means its union with oxygen. Another instance is known to us in the glowing gases, which play fiercely over the sun. In common speech, we talk of the burning surface of the sun, yet the term is wrong. The gases which send out so intense a glare are, it is believed, only glowing, not burning. They give forth heat and light, but they do not unite with oxygen and waste away. To speak of flames on the sun is equally incorrect. Flame is gas in combustion, and the gases of the sun are believed to be only incandescent, not in combustion. For true burning, the presence of oxygen is generally needful, and the presence of some other combustible substance to combine with the oxygen is equally needful. We can no more make a fire of oxygen without coal than of coal without oxygen, for both are required. Having both, we must bring them together, and must place them under the touch of sufficient heat. When this is done, and the union of the two is started, enough heat will be given out for carrying on the work and for warming the room. In the lighting of an ordinary fire, heat is first applied by a lighted match to the paper or shavings. Some of the paper or shaving substance at once unites with a little oxygen in the air. In that act, the breaking loose of particles from the solid substance to join with particles of oxygen causes a setting free of fresh heat. This heat spreads to the wood. Another union then takes place, particles of wood breaking loose to form a combination with more oxygen. Further heat is again given out, which spreads to the coal, which in its turn catches fire, entering on a course of union with the ever-ready oxygen. Thus heat both causes and springs from combustion. Now, what of the new substances formed by these various combinations? The particular substance which is formed must depend in each case upon the particular substance which is burnt. As a matter of fact, in the common everyday burnings around us, two special substances are by far the most common as the second party in this union. They are carbon and hydrogen. When a lump of coal is burnt, part goes up the chimney as soot, part falls below as white ash, part vanishes. So, with the burning of a wax candle, part passes away as soot, while the greater part slowly disappears. Yet, though the coal and the wax pass out of sight, their substance is not destroyed. So far as we can tell, no matter once created is ever put out of existence. We cannot say that it never will be, for the future of the universe of matter is utterly unknown to us. But man has no power to destroy a particle of it. True, he can, by using the forces of nature, break up many materials, change their form, cause them to vanish, yet the vanished particles may reappear. The old form may be restored. There is no real destruction of the tiniest atom. In the case of burning coal or wax, each particle exists still, afterwards, somewhere, and in some shape. Part of the coal drops below as white ash. This is the mineral substance which cannot burn. Part escapes as soot, or unburnt carbon. The great mass of the carbon, which is the chief portion of the coal, unites itself with oxygen and forms a new combination. This new combination, called carbonic acid gas, floats away invisible, joining the hot smoke in its passage up the chimney. Meanwhile, the hydrogen gas held in the coal also joins itself to oxygen, causing bright flames as it does so. The result of that union is water in the form of vapor. The same takes place in the burning of a candle. Some of the carbon escapes as unburnt soot, while the greater part unites itself to oxygen, and those two, losing their separate individuality, pass away into the air as carbonic acid gas. The hydrogen combines with surrounding oxygen, and these also float off as invisible vapor of water. If a clear coal tumbler is held over a candle flame, it will grow dim with fine moisture. This moisture is some of the newly made water, condensed into a tiny fog by the chill of the glass. The bright light given out by a candle flame springs mainly from the glowing of fine carbon points, which float within the flame. Where any of the carbon is within touch of the air, it unites with oxygen and goes off as carbonic acid. Inside the body of the flame, the air has no excess, and there the carbon specks can only glow. For lack of oxygen, they cannot burn, so they pass away as smoke. If the whole of the carbon contained in the wax could be at once burnt up as the flame creeps down the wick, there would be no smoke and very little light, but there would be much more heat. Hundreds of tons of coal are daily consumed in every great English city, especially in winter. It is a wonderful fact if we consider what is meant by burning. A mighty mass of solid black coal is in 24 hours utterly disposed of by the soft, translucent air, not swept aside in one mighty hurricane blast, but gently lifted particle by particle, carried off and hidden away by the busy oxygen. End of Chapter 8. Recording by John Brandon. Chapter 9 of The Ocean of Air, Meteorology for Beginners. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by John Brandon. The Ocean of Air, Meteorology for Beginners by Agnes GIBERNE. Chapter 9. 3 Forms of Carbon. Before going into the carbonic acid gas of the atmosphere, we must think a little about carbon, from the union of which with oxygen springs carbonic acid. Carbon is another simple substance, another of those mysterious shut doors beyond which, at present, we cannot pass. It cannot by any means yet discovered be split up or divided into other substances. We have had so far to do with simple substances, which in their ordinary free state on Earth are gases such as nitrogen and oxygen. Carbon in its natural earthly state is a solid, and not only so, but it is one of the most stubborn solids known. For a long while it resisted all attempts to thaw it into a liquid. When united with other substances, carbon appears in multifarious forms, the names of which are legion. It is a most abundant material, and it enters enormously into the make of all vegetable and animal bodies, of all organized bodies, or creatures with life. Without carbon, our Earth would be an uninhabited desert. Without carbon, we should have no grass, no plants, no corn, no trees. Without carbon, we should have no birds or beasts. Without carbon, there could be no men, as now constituted. For men are built up of carbon, of course, with the addition of other ingredients. In charred wood, charred meat, charred human flesh, the underlying black carbon is plainly to be seen. If the wood, meat, or flesh is entirely burnt up, then no carbon remains. The whole has united with oxygen and has vanished as carbonic acid gas. White loaf sugar is a compound substance being formed of carbon and water, for sugar is a vegetable product. If sulfuric acid or oil of vitriol is poured upon thick sugar syrup, the mass blackens and swells upward into a large quantity of loose charcoal. Carbon is abundant, too, in many rocks, such as marble and limestone, also in chalk, coral, and shells, which are largely of animal make. But while all this is true, while numberless forms of vegetable and animal substance are composed in a great measure of carbon, yet in its most pure form, free from combination with other substances, carbon appears mainly in 3 distinct characters. The first form of pure carbon is charcoal. Perfectly pure charcoal is not common, any more than perfectly pure aught else in this world. Everything gets mixed up more or less with other things, but if wood is slowly burnt in a vessel nearly closed, tolerably pure charcoal will remain. A far more important form of carbon, very nearly allied to wood charcoal, though less pure, is coal. What the world would be without coal, we can only imagine by looking back in fancy to those times when coal had not been discovered. All modern life, modern comforts, modern appliances, modern discoveries, modern experiments, and inventions seem to depend upon the existence of coal. Without coal, unless something else should take its place, England would sink back into a kind of semi-barbarism. Coal is a form of carbon. It is made from wood, which consists largely of carbon, since trees, like men, are very much built up of carbon. Coal fields are the buried remains of mighty ancient forests, and the structure of wood can often be traced in a piece of coal. But this structure has generally vanished, for a change has passed over the woody substance, transforming it into the fossil substance called coal. The change has been brought about by an underground operation, which is in fact much the same as that by which a log of wood is transformed into charcoal. Only in the one case the action has been very slow, in the other it is quick. The transformation of those buried forests into not very pure charcoal has really been through a course of exceedingly slow combustion or oxidation spread out over ages. Coal is the charred remains of a former vegetation. Combustion, as we have seen, does not always mean becoming red hot, though it always means some amount of union with oxygen. Is it not wonderful that all this preparation of fuel was going on through long ages, man never dreaming of any such merciful provision for the future of his race? So charcoal, coke, or coal is one form of carbon in its natural state. The second form of pure or nearly pure carbon is graphite or plumbago. We all know graphite as black lead, wrongly so called, the soft black substance used in pencils. Curiously, unlike hard porous charcoal or shining coal, graphite is found in granite rocks and elsewhere underground. It has other uses besides that of lead for pencils, not needful to be considered here. Charcoal and graphite are not so very startlingly opposite in appearance and character, but it is when we come to the third form of carbon that we find an astonishing difference. The third form of pure carbon is diamond. Certainly, no one would ever dream at first sight of putting the brilliant rare diamond under the same head as common black charcoal and graphite. Yet the three are the same, absolutely identical in nature. Each is carbon, carbon in its natural free state, uncombined, or very nearly so, with any other substance. Unlike in color, unlike in shape, unlike in hardness, unlike, we should say, in every single particular. They are one in nature, formed of the same simple substance. So we see that charcoal is carbon, plumbago is carbon, diamond is carbon. If each of the three were formed of carbon united with other materials, we should think nothing of it. The extraordinary thing is that each of the three is carbon only, carbon throughout. How and under what conditions carbon takes that particular form, becoming a translucent flashing gem, we do not know. The formation of the diamond is still a mystery. We can only assert that as the black lead of a pencil is carbon, as lampblack is carbon, as coke is carbon, as charcoal is carbon, so diamond is carbon. Charcoal, plumbago, and diamond, however, unlike in appearance, are one in nature. They are all three merely different developments of the one simple substance, carbon. Thus vast quantities of carbon are present on Earth, floating through the atmosphere in union with oxygen as carbonic acid gas, lying underground in rocks and coal, residing in the bodies of plants and animals. Moreover, as we shall see, a perpetual interchange is kept up between the carbon of the atmosphere and the carbon of living bodies dwelling in the ocean of air. Carbon is incessantly passing from the air into living structures, and out of these structures into the air again. Nay, the very carbon which ages ago passed into living forests of trees is in these latter days poured back into the atmosphere whenever coal is burnt. So there is a circulation of carbon in the world, as well as a circulation of oxygen, not less active, not less constant, not less widely extended. The whirlpool of life and change knows no cessation. By means of the spectroscope, we know that this same substance, carbon, which is so abundant on Earth, exists also in the stars and comets of distant space. End of Chapter 9. Recording by John Brandon. Chapter 10 of The Ocean of Air, Meteorology for Beginners. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by John Brandon. The Ocean of Air, Meteorology for Beginners by Agnes GIBERNE. Chapter 10, The Perils of Carbonic Acid. Carbonic acid gas is being perpetually made, perpetually poured into the atmosphere, and perpetually broken up once more into the carbon and oxygen of which it is formed. The quantity of it present in the air at any one time or place varies exceedingly. At some times, and in some places, a much larger supply is being made and is sent floating through the air-ocean than elsewhere, and on other days. There are certain special modes through which this gas comes into existence. Carbonic acid gas is found wherever any substance burns which is partly made of carbon. Part or the whole of that carbon unites itself, in the act of burning, with some of the oxygen round about, so forming carbonic acid gas. One of the chief perils of a house on fire arises from the above fact. The carbon of the great mass of burning materials combines rapidly with oxygen, and large quantities of carbonic acid gas are poured forth. Many a human being unable to escape is mercifully stifled by the deadly fumes long before any flames can reach him. If the wind blows, so much the worse, for the moving air brings constant fresh supplies of oxygen, and as these sweep over the house, the making of carbonic acid gas goes on more rapidly. In common speech, the wind fans the flames, and the house burns faster. When a haystack or a bonfire is alight, and we go to the side where the wind bears down upon us, we are speedily aware of the overabundance of carbonic acid gas, whether or no we can tell its name. The fact is apparent by the choking, stifling rush which drives us from the spot. The same danger exists in the burning of a charcoal brazier in a room which has no fireplace. Terrible risk to life is involved here, for as the charcoal wastes, it gradually unites with oxygen to make carbonic acid, and this gas has no escape except into the air of the room. Many a solitary being has gone to sleep in such a case, enjoying the warmth, and has been stifled in his sleep, never waking again. A sad instance happened not many years ago in Paris. A young English girl had gone there in quest of work, a quest which long proved fruitless. Success at last came, and she went joyously to tell her friend, an English clergyman, who had kindly helped in the search. Returning to her lonely room, she lit a little charcoal fire, feeling in delight that she might now indulge herself, and never dreaming of danger. Full of hope, the poor girl went to bed, leaving no outlet for the deadly gas. And when morning came, a hasty messenger summoned the clergyman. He arrived only to find a dead body lying in the small room. All had been over hours before. The danger is greater at night than in the day, because one is taken unawares in unconsciousness, because too of the recumbent position of a sleeper. Carbonic acid is a heavy gas, much heavier than oxygen or nitrogen. Except when stirred up by air currents, it always sinks downward, and it will remain so, distinct from the other gases, that the lower part of a room may be full of it, while the upper part has comparatively pure air. Through this heaviness it can, with care, be poured from one vessel to another. Carbonic acid gas is made in the fermentation of wine. The sugar contained in the grape juice is broken up by the fermenting process, and fresh substances are formed from it, one of those substances being carbonic acid. A rapid fermentation first takes place, the liquid needing to be occasionally stirred up. For this purpose in olden days, and in some countries, it was customary for a man to enter in bodily. the warmth of his frame was supposed to be advantageous by promoting quicker fermentation. It was, however, a perilous business for the man himself, on account of the large quantities of carbonic acid gas escaping, and several lives were thus lost at different times. When the more rapid fermentation is over, the wine is moved to other barrels, and the slow after fermentation begins, lasting for months. Here again the same danger attends those who have to visit the wine vats. As a rule, the escaping gas lies low, and a man may walk safely upright, where a dog would fall senseless and die. But if he stoops to care for the dog, he too may be overpowered. Sometimes the gas collects and rises to such a height as to imperil men also. Too hasty an entrance into the place may mean no less than death, and fatal results have come about not seldom. The following memoranda are of a visit paid by my father to a brewery many years ago. I was taken over one of the largest breweries in London in company with friends. The thing that struck me most was the large fermenting vat, of the size and form of a small room, in which the fermentation of wort was proceeding at a rapid pace. The liquor was some feet in depth, and on the surface of it floated a dense body of clear, bright carbonic acid gas, which overflowed at the gangway where I was standing like a waterfall, some 12 or 15 inches deep. On looking upwards through the bright, colorless gas fall, it was very curious to see the dingy, dirty London air resting upon its surface, and gently waving along when set in motion by blowing or fanning. I stooped down and ventured to take a small breath of the gas fall, but I did not attempt to take a second. It was like a sword passing down my throat. Subsequently, I inquired the cause of the pain given by inhaling the carbonic acid gas given off by fermentation, whereas that given off by burning charcoal is only stifling in its effect. I was told that there is no pain in inhaling dry carbonic acid gas, but when mixed with damp, it has the effect I experienced. Carbonic acid gas formed by the burning of coal would, if we had no chimneys, be poured into our rooms to the detriment of health, if not to the destroying of life. Where a chimney fails to draw well, that is, when the upward draft is not sufficient to carry away all the gas with the smoke, we are soon conscious of stinging and choking sensations, extremely unpleasant in kind. Long ago, English fireplaces boasted no chimneys. The fire was made in the middle of the room, and the smoke and newly formed gases had to meander about till they found their way out through a hole in the roof. But since glazed windows were in those days unknown, the absence of chimneys mattered less, for there would always be a plentiful supply of pure air pouring in below. As cold air is the heaviest, while hot air is light, the fresh cold incoming air would speedily drive upward and outward the dangerous gas. Most of us have felt more or less the ill effects of burning gas in a closed room. Gas, like coal, contains much carbon, and when it burns, supplies of carbonic acid gas are being steadily poured into the air. Unless there is a way of escape through open door, window, or ventilator, the air of the room changes fast from good to bad. Some people are very sensitive to this, suffering even in the earlier stages from headache, faintness, and other trying sensations, while some can endure an extraordinary amount of bad air without being aware of it. Sooner or later, however, the hardiest and most insensitive frame must suffer, the condition of things produced being one in a succession of stages on the high road towards suffocation. Carbonic acid gas is found wherever living creatures are. No need to say living creatures which are largely made of carbon, for all living creatures are largely made of carbon. From them is poured out a regular, intermittent stream of carbonic acid gas with every breath. This is why a room containing human beings, if no fresh air is allowed to enter, becomes close and unhealthy. Burning gas would make matters worse by hurrying on the evil. But without any burning gas or lamp or candle, we have still the same result. It is no rare spectacle to see a church or a room in cold weather full of men and women having every door and window fast shut from dread of the slightest draught. Elderly people and nervous people are often afflicted with an almost morbid horror of moving air, while they are placidly indifferent to poisonous air. The fact is curious but common. Now, the air of any closed place, steadily breathed by men or animals, becomes gradually transformed to a slow poison, nay, in time, to a quick poison, though affairs are seldom allowed to go quite so far. People are usually content to give themselves and their children over-pale or over-flushed faces, sickly sensations, and bad headaches, without advancing to actual suffocation. We hear a great deal of ill health among the poor, of stunted frames, pallid cheeks, and constant suffering. Of course, much of this in certain cases may be due to scanty food or to overwork. But it is a grave question how much of it is not owing to the habitual breathing of air, which has been allowed to gain too much an amount of carbonic acid gas, simply from the lack of an open window. There is a wonderful carelessness among the poor as to fresh air. True, the fresh air at their command is not always of the purest, yet it is better than none. Nor is it in town alleys alone, but also in country cottages, that windows are built up with plants never to be opened, and that frequent airing of a room is a thing unthought of. It would be hardly fair, however, to speak of this indifference as a characteristic of the poor only. There are houses in a higher station of society, houses inhabited by the cultivated and refined, where the window of a much-used sitting-room is closed before breakfast and is never opened again before night. Naturally, by evening, the air of that room has grown into a most undesirable compound. The mixture of little oxygen with much carbonic acid is rendered not more pleasant by various floating vapors and particles of matter given off in the course of many hours from the lungs and skin of human beings present. A sharp current of air between window and fireplace or window and door would speedily expel them all, bringing a sufficient supply of fresh oxygen. But no, that would be too much trouble, or nobody thinks of it, or somebody might complain of cold. So the unhealthy mixture has to be patiently breathed by the unfortunate individuals assembled there. However, as already said, many people are not sensitive. In the space of 24 hours, a man not especially exerting himself takes into his system about 18 cubic feet of oxygen gas. He also gives off from lungs and skin about the same amount of carbonic acid gas. Suppose a man were in a room 7 feet high, 7 feet wide, and 7 feet broad, shut up completely with no opening to admit fresh air. The whole mass of air in that little room would in 24 hours have passed through his lungs. Of all the oxygen originally held by the air, 1/4 would have disappeared, its place being filled by about the same amount of carbonic acid gas. Suppose no air were then admitted, but the same state of things were continued for another 24 hours. By that time, half the oxygen present would have been exchanged for carbonic acid gas. Following out the same idea, we may say that in 3 days, 3/4 of the oxygen would have given place to carbonic acid gas, while in 4 days the oxygen would be all gone, and only carbonic acid mixed with nitrogen would remain. Of course, this experiment could never be really tried, because long before the close, the man must, after great suffering, have died of suffocation. By burning charcoal continuously in a shut room, from which all fresh air is shut off, the result described could be actually brought about. But through a man's breathing, only the earlier stages are possible. Not far from the middle of the last century, a terrible deed was worked in Calcutta by the guards of the so-called Nabob, Saruja Dowlah, upon his English prisoners. No more awfully forcible illustration can be found of the desperate need for fresh air to keep human beings alive. The story may well be given in the vivid words of Macaulay. Then was committed that great crime, memorable for its singular atrocity, memorable for the tremendous retribution by which it was followed. The English captives were left to the mercy of the guards, and the guards determined to secure them for the night in the prison of the garrison, a chamber known by the fearful name of the Black Hole. Even for a single European malefactor, that dungeon would, in such a climate, have been too close and narrow. The space was only 20 feet square. The air holes were small and obstructed. It was the summer solstice, the season when the fierce heat of Bengal could scarcely be rendered tolerable to natives of England by lofty halls and by constant waving of fans. The number of the prisoners was 146. When they were ordered to enter the cell, they imagined that the soldiers were joking, and being in high spirits on account of the promise of the Nabob to spare their lives, they laughed and jested at the absurdity of the notion. They soon discovered their mistake. They expostulated, they entreated, but in vain. The guards threatened to cut down all who hesitated. The captives were driven into the cell at the point of the sword, and the door was instantly shut and locked upon them. Nothing in history or fiction approaches the horrors which were recounted by the few survivors of that night. They cried for mercy. They strove to burst the door. Holwell, who even in that extremity retained some presence of mind, offered large bribes to the jailers, but the answer was that nothing could be done without the Nabob's orders, that the Nabob was asleep, and that he would be angry if anybody woke him. Then the prisoners went mad with despair. They trampled each other down, fought for the places at the windows, fought for the pittance of water with which the cruel mercy of the murderers mocked their agonies, raved, prayed, blasphemed, implored the jailers to fire among them. The jailers, in the meantime, held lights to the bars and shouted with laughter at the frantic struggles of their victims. At length the tumult died away in low gaspings and moanings. The day broke. The Nabob had slept off his debauch and permitted the door to be opened, but it was some time before the soldiers could make a lane for the survivors, by piling up on each side the heaps of corpses on which the burning climate had already begun to do its loathsome work. When at length a passage was made, 23 ghastly figures, such as their own mothers would not have known, staggered one by one out of the charnel house. A pit was instantly dug. The dead bodies, 123 in number, were flung into it promiscuously and covered up. Dead for lack of air to keep them in life. The small amount of air within, breathed by 146 pairs of lungs, grew rapidly worse and worse as oxygen gave place to carbonic acid, and the small window openings were blocked up by the struggling mass of human beings fighting in the agony of gradual suffocation for one breath of air. The marvel was not that 123 died, but that so many as 23 outlived the horrors of that awful night. Carbonic acid gas is found abundantly in many coal mines. Everybody has heard of the terrible fire damp and choke damp of mines, but many would be at a loss to define the difference between the two. Fire damp, wrongly known among miners as sulfur, is a gas made of carbon and hydrogen. It contains no sulfur whatever, and the word damp is a corruption of Dampf, the German for vapor. In many coal mines, especially in many English ones, large quantities of this gas often collect amid the coal seams, and when released by a stroke of the pickaxe, it flows out in streams. By itself, it is not a dangerous gas. It'll burn if lighted, but quietly with a blue flame. Once let it become mixed, however, with a certain amount of common air, and it becomes at once tremendously explosive. If it comes in contact with any flame, an explosion instantly follows, rendering rocks and dealing death to miners within reach. Usually, there are many men in a mine where such an explosion takes place, beyond touch of the actual flames. But though not burned to death, another danger, not less terrible, awaits them, and this is from the choke damp or after damp. The gas called fire damp is made, as we have seen, of carbon and hydrogen. When that gas takes fire and burns in a great outburst of flame, large quantities of carbonic acid gas spring into being through the union of carbon with oxygen, and the dangerous carbonic acid gas, or choke damp, flows through the passages, searching out the miners in their retreats. If overtaken by it, they are soon overwhelmed. A few breaths of the deadly gas, and they fall in unconsciousness, unless speedily rescued, never again to wake. In the great Hartley Collyer disaster, more than 200 men died of the choke damp who might otherwise have escaped. The coal gas which we burn in our houses, though not quite the same in make as the fire damp of mines, is very likely it in one respect. Coal gas, properly managed, is harmless enough, but when mixed with a particular amount of atmospheric air, it becomes explosive. If a little air gets into a gas pipe, or if the gas escapes and mixes with air, there is likelihood of an explosion. Gas as used in private houses under the control of people who do not in the least understand it is a perpetual danger to mankind. The one real safeguard lies in its unpleasant smell, for when gas escapes, it always makes its presence known. Still, even this is not enough. Uneducated persons will take a candle or light a match to examine the source of the odor. About the maddest feat they can well perform. The wonder is that more lives are not lost thus, and indeed gas explosions on a small scale are by no means uncommon. Carbonic acid gas is found wherever volcanoes exist and fiery underground forces are at work. In such regions, great outpourings of it are wont to take place alike from open craters, from springs of water, and from casual cracks and splits in the earth. Herein lies one peril of volcanic districts. A man carelessly approaching a crater or leaning over an open fissure may be choked by the rising fumes, while in no peril from flames or hot lava. Miss Bird, describing the fiery lake of Kilauea, writes, "At times the level of the lava in the pit within a pit is so low, and the suffocating gases are evolved in such enormous quantities that travelers are unable to see anything." And again, at a later date, the whole region vibrated with the shock of the fiery surges. To stand there was to snatch a perfect joy out of a pain and terror which was unendurable. For 2 or 3 minutes we kept going to the edge, seeing the spectacle as with a flash through half-closed eyes, and going back again. But a few trials in which throats, nostrils, and eyes were irritated to torture by the acid gases convinced us that it was unsafe to attempt to remain by the lake, as the pain and gasping for breath which followed each inhalation threatened serious consequences. The same abundance of escaping carbonic acid gas is found near Vesuvius, Etna, and other volcanoes, and also in the neighborhood of extinct craters, in lands where eruptions are no longer known. Carbonic acid gas is found wherever decaying herbage exists or dead bodies of animals lie. The carbon of which both plants and animals are largely made, it gives back to the atmosphere when they decay. It unites with the oxygen of the air, and again carbonic acid is formed, by a slower process indeed than that of burning, but with consequences no less deadly. Herein lies one danger of living among or near great masses of dying or dead vegetation. The fall of the leaf in a wooded country is counted unwholesome. Every fallen leaf in its decay sends forth a little stream of carbonic acid gas, and the many small streams join to cause a serious total. The evil would be greater yet, but for the busy worms who work so hard, drawing the dead leaves underground. There they decay still, but not injuriously, helping to form new mold to feed plant life, instead of helping to poison the atmosphere for animals and men. Still, despite all that worms can do, a good deal of unwholesomeness does exist in such places, even in England. More markedly it is seen in the swampy lands round about tropical rivers covered with luxuriant vegetation. Also, the presence of dead bodies in or near human dwellings is a danger to life. Besides sending out germs of disease, their decay produces a large amount of this gas. Carbonic acid gas is the precise opposite of oxygen gas. The latter is life-supporting, the former is life-destroying. Whether it is in any sense an act of poison has been questioned. If the amount of it in common air is increased and the amount of oxygen is increased in the same proportion, the carbonic acid seems not to be hurtful. So it appears that a man who dies from breathing carbonic acid, like one who dies from breathing nitrogen, dies not from a poison, but from a want. He dies not because he has taken in too much carbonic acid, but because he has not taken in enough oxygen. Under great cold and pressure, carbonic acid can be liquefied and has even been solidified to a light snow-like substance. Generally, however, as it floats in the ocean of air, we know the said substance only as a gas. In taste, it is slightly acidic. End of Chapter 10. Recording by John Brandon. Chapter 11 of The Ocean of Air, Meteorology for Beginners. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by John Brandon. The Ocean of Air, Meteorology for Beginners by Agnes GIBERNE. Chapter 11. What is meant by breathing? Something is meant by breathing which has a very close connection with the atmosphere in which we live. For if there were no air, how could any creatures breathe? But before going into what is meant by breathing, we must have a few words about the right balance between exertion and food. If a man takes an hour's sharp walk, at the end of the hour he's not in all respects the same as when he started. He has lost weight. He has paid away in active effort some of his substance, both solid and liquid. The former has gone off in clouds of carbonic acid gas, the latter in clouds of steam or vapor. This loss of substance means a pressing need before long of something to take the place of that which is gone. So long as the furnace fires of an engine burn, there is the constant need of fresh coal to feed the flames. Otherwise the fire will die out, and the engine must come to a standstill. So long as the fire of life burns in a man, there is a constant need of fresh fuel to support it. Otherwise, life will fail and the man must die. While life lasts, perpetual waste goes on, but the rapidity of waste depends upon the amount of effort and exertion used. An engine traveling at the rate of 60 miles an hour uses up coal much faster than an engine traveling at the rate of 30 miles an hour. If a man had sat still in his chair or had loitered lazily about, there would still have been loss of substance, but not nearly so much as in his hour's brisk walk. If instead of merely taking a brisk walk he had climbed fast up a steep mountainside, the loss of substance would have been yet greater. Active exertion quickens the breathing, the heart's action, the circulation of the whole frame. It means the more rapid using up of material, and the greater need of fresh material in place of that which is used. The same result would be brought about if the man stood still and lifted a succession of heavy weights. There would again be exertion, quickened waste, increased need of renewal, as compared with when he stands still and does nothing. The supply of fresh material can come only in 3 ways. 1 as food, 2 as drink, 3 as air. Every human being, every kind of animal requires these 3 and requires them imperatively. He must have air always. He must have food and drink at regular intervals. Just so, the engine must have food and must have air to keep it going. If the carbon of the coal or the oxygen of the air is cut short, then the engine fires die out. Many people take too much food, and many others take too much drink for their requirements, while some take too little food and others too little drink. With each human being, there is a certain exact amount of both needed, just enough, in fact, to balance the amount of exertion and of bodily waste. Less exertion means less waste and consequently less need of renewed supplies. More exertion means more waste and consequently more need of renewed supplies. The food and the drink taken are too much if they are not balanced by a sufficient amount of exertion and of resulting waste. They are too little, if not enough, to supply the amount of waste caused by exertion. So the more a man does, the faster he loses substance, and the more food he requires to make up for the waste of his frame. This rule is, of course, modified by particular conditions in particular cases. What seems a slight exertion to one person may be a severe exertion to another, and certain states of illness may induce as much waste as any amount of active exertion. The very same results are seen, strange to say, in the matter of thought and brain work as in bodily effort. The harder a man thinks, and the more intensely his brain is exerted, the greater is the animal waste. Therefore, the greater is the need of sustenance. Now, the renewal of lost substance, the sustaining of the fire of life, takes place, as already said, in 3 ways, more strictly by 2 modes: 1, feeding, 2, breathing. The food includes both kinds, solid and liquid. Of these, too much or too little may very easily be taken. But there is no fear of a man breathing too much or too little air, since his body settles that matter for him independently of his own will. All that his will can do in the matter is to choose a place where he is surrounded by good air containing enough oxygen and not too much carbonic acid. Everybody breathes as a matter of course, not at all as a matter of choice. Men breathe, beasts breathe, birds breathe, insects breathe, whales and porpoises breathe. Even fishes breathe, and breathe air containing oxygen, though they get it out of the ocean of water in which they live, and do not need, like whales and porpoises, to come to the surface. That a man cannot live without breathing is patent to everybody. He may cease eating or drinking for a while, even for days, though not without much suffering. He cannot cease breathing for more than a few minutes at the most, or he will die. As he moves to and fro on the floor of the air ocean, he draws every few seconds into his lungs a certain amount of air, and as regularly sends at least a portion of it out again. This we know for ourselves from actual experience. We may not be able to explain how or why we breathe, but that we do breathe and must breathe, we know well. There are many things in this world which we feel to be true, with a knowledge which amounts to absolute certainty, while yet we are not in the least able to explain why they are so, or from what causes they spring. Even the lower animals are aware of the need of air. An experiment was once tried of putting a cat into an air pump enclosure, and pumping out the air. Poor pussy felt it going, and she had the sense to try to cover with her little paw the hole through which the air was withdrawn, seeking thus to hinder the escape of any more. It is to be hoped that those who tried the experiment were content with so much, and did not put her to further needless suffering. Of course, the cat could not have told why she needed the air, and by what particular process the air entering her lungs kept her in life and health. She only knew her own need, and knew what met that need. Without any theories and without any definitions, she was aware, and many human beings no wiser scientifically than was pussy are aware too, that not to have air for breathing means death. Some higher needs of our nature are, after the same mode, felt and met without clear understanding on our part either of exactly what need we feel, why we feel it, and how that need is supplied. A grown man of full ordinary height and size, sitting still, breathes on an average about 18 times each minute if he walks fast, still more if he runs, mounts a steep hill, or lifts a heavy weight. His breathing is quickened. Each time that he breathes, he draws into his chest about 20 cubic inches of air, perhaps somewhere about 3/4 of a pint, and sends out again almost as much. In so doing, he does not empty his lungs, for the lungs of a man contain usually between 1 and 2 quarts of air. The whole amount is undergoing change constantly but gradually, and not at every breath, since a good deal of air always remains behind. Now, the air which a man breathes out is markedly different from the air which he breathes in. There are 4 main points of difference. It is much hotter, it is much damper, it contains much less oxygen, it contains much more carbonic acid. The day may be ever so cold, the water may be frozen into ice, the ground may be hard, the air that he breathes in may be down in temperature as low as the freezing point. All this makes no difference. The air which he breathes out will be up to nearly 100 degrees, or almost as hot as his blood, oppressive summer heat. The day may be ever so sultry, the ground may be caked and hard, little moisture may be floating in the atmosphere, the air breathed in may be dry as air can be. All this again makes no difference. The air breathed out will be soaked with vapor of water, turning rapidly in the cold outside air to a little fog of visible water droplets. Does not a child know this when he breathes on his slate, that he may be able to rub out faulty figures? In the course of 24 hours, nearly half of a pint of water is commonly given off from a man's lungs, but the amount varies much. Whatever the day may be, hot or cold, dry or damp, the air breathed into a man's lungs is simple atmospheric air. It is the usual mixture of oxygen and nitrogen, with a slight addition of water gas, and so minute an amount of carbonic acid as to be hardly worth thinking about. But when the air is poured out again from the lungs, an extraordinary change has passed upon it. The quantity of nitrogen alone is almost unchanged. The quantity of oxygen has run down to only a little over 3/4 as much as it was. The quantity of carbonic acid has shot up to almost 1/4 of the former amount of oxygen. In other words, the lost oxygen is nearly replaced by carbonic acid. If a pint of air, as breathed in, were divided into 10,000 tiny equal portions, the gases being separated, nearly 8,000 of them would be nitrogen, more than 2,000 would be oxygen, and only 3 would be carbonic acid. a pint of air being not very much more than the quantity drawn in by a large man. The same amount breathed out would contain about the same amount as before of nitrogen, only about 1,500 portions of oxygen, some 470 portions of carbonic acid gas, and a greatly increased amount of water vapor. Where has the oxygen gone, and where has the carbonic acid come from? The answer is very simple. It is a case of combustion. When a lump of coal or a candle burns, do you remember what happens? There is a waste of a substance. There is a giving forth of heat. The hydrogen in the coal or wax unites with oxygen from the air and makes vapor of water. The carbon in the coal or wax unites with oxygen from the air and makes carbonic acid gas. That is a case of combustion, of rapid burning. Combustion is not always rapid. It may be very gradual indeed, as we have seen in the case of coal fields. There, buried forests of trees were slowly transformed by a kind of underground combustion into a species of charcoal. In the case of a man, we have slow combustion again. Not nearly so slow as the combustion of buried forests, but not nearly so fast as the combustion of a burning candle or a piece of coal. It is rapid enough for the giving off of a great deal of heat, which heat is borne by rushing streams of blood to all parts of the body. It is not rapid enough for the burning parts to become red hot. Combustion is, or at least includes, the union under a certain degree of heat of a substance, such as carbon with the oxygen of the air. That is just what goes on night and day in the body of every man, woman, and child living, not to speak of lower creatures. The carbon of which they are largely made unites perpetually with oxygen drawn into the lungs by breathing, and the two united are given off as carbonic acid gas. In the burning of a piece of wood, the carbon of the wood is needful, also the oxygen of the air, also enough heat to cause their union. In the slower combustion of a man's body, these three are equally needed: the carbon of his body, the oxygen of the air, and sufficient heat to make them combine. Something else is necessary also, before burning can begin. The carbon and oxygen must touch, and the heat which is applied must reach them both at the point of contact. We see easily how this comes about in the matter of a burning candle or a lump of coal. The air flows over and around, so that fresh particles of oxygen are constantly running against particles of carbon in the wax or coal, while heat spreads to other parts. But in the case of animal combustion, the matter is not so simple. The mass of carbon helping to compose a man's body is chiefly inside him, and the mass of oxygen in the air is chiefly outside him. So how are the two to come together, and how is sufficient heat to be brought to bear? With regard to the heat, one can say little. The high, steady temperature of a man's frame is still in great measure a mystery, partly accounted for by the combustion always going on within that frame, but connected with the greatest mystery of all, the life which reigns there. It is easy to see that the right measure of heat once given, the combustion once started, burning will go steadily on, whether in a fire of coal or in the fire of a man's body, so long as favorable conditions last. That is to say, it will continue until either the supply of fuel, of food, or the supply of oxygen shall run short. But how the fire which set that combustion going in man was first applied is another question. I know no answer to it except in words familiar to us from infancy. God breathed into his nostrils the breath of life, and man became a living soul. Now about the needful contact of carbon and oxygen in a man's body. More than one great and worldwide circulation has been spoken of in earlier chapters. In the frame of a man we have a yet more wonderful circulation, though on a smaller scale than that of gases. It is more wonderful than the circulation of any mere material substances, for this is a circulation on which life hangs. Night and day, day and night it goes on. Hour by hour, minute by minute it continues. Rivers of blood rush at full speed through the larger vessels of a man's body, thence dividing into smaller streams. These career through lesser vessels, subdividing again and yet again, till the tiny capillaries, the most minute vessels of all, countless in number and reaching everywhere, are filled with infinitesimal rivulets. From the capillaries the streams meet, converging into larger and yet larger vessels, till once more they reach their starting point and begin the round anew. Through all the round, as the stream flows onward, it is incessantly leaving part of itself behind, and incessantly taking up something new on its way. Two kinds of vessels carry the blood. These are called arteries and veins. The arteries bear blood away from the heart. The veins bear it back to the heart. The arteries contain bright scarlet blood. The veins contain dark purplish blood, often called black blood. Between the two kinds there is a marked difference. In most respects, except coloring, they are much alike as to make. In one respect they are gravely unlike. The red blood of the arteries has in it plenty of oxygen and very little carbonic acid. The purple blood of the veins has in it much less oxygen and much more carbonic acid. When the stream starts from the heart, it is red and pure. But as it passes through different parts of the body, it incessantly parts with its oxygen for the needs of the body. Not only this, it incessantly takes up and carries away useless particles of matter, waste materials no longer needed there. So gradually the pure red blood loses its purity and brightness, getting overloaded with carbonic acid and other hurtful matters. By the time it has worked its way back through the veins to nearly its starting point, it is in dire need of being charged anew with oxygen. But how? By being brought into touch with the outside atmosphere, taking therefrom new supplies of oxygen and giving off superfluous supplies of carbonic acid. A certain amount of this has taken place already. Whenever tiny streams have flowed in minute vessels close under the skin of the body, where the air could reach them, their carbonic acid has been given off. But much more is required, is indeed an absolute necessity. If the dark blood flow again and again through the man's body, he must die. The blackened stream reaches the lungs and is there spread out over a wonderful network of tiny vessels, all enclosed in a skin so delicate that air can pass through it without the least difficulty. And then, those tiny vessels are met by pure air from outside, atmospheric air laden with oxygen, rushing in with every breath. Each breath drawn in brings fresh supplies of oxygen, and each breath poured out gets rid of new supplies of dangerous carbonic acid. So very soon the blood is sent careening on its way, no longer purple, but bright red, no longer laden with bad materials, but full of good gas. Once more it hastens through the man's frame, leaving more oxygen on the road, carrying away more evil things, which, if left, must endanger the man's life. Now, what is the direct object of all this oxygen? Why such constant supplies of it, carried into the lungs by breathing, borne from the lungs by the blood to all parts of the system? To support combustion. Simply that. The man is slowly burning. If he is to live, he must burn. Combustion is life. Stagnation is death. So long as the fires are kept alive in him, he lives. Let them die out, and he dies. Combustion means the union of oxygen with other substances. For instance, with carbon to make carbonic acid gas, with hydrogen to make water gas. Both these processes go on constantly inside a man. Burning means burning away, not simply glowing with a changeless heat. Man burns away as distinctly as a candle burns away. The more energetically he lives, the faster he burns away, and the greater his need for fresh air and food. If food ceases, he dies soon. If air ceases, he dies immediately. Whatever else he has or has not, he must have sufficient air perpetually to overmaster and carry off the superfluous carbon of his body. Otherwise, the carbonic acid will speedily overpower him. Second in importance to this is the keeping of a just balance between exertion and food. The more exertion, the better, so long as the amount of waste can be always and steadily repaired. Life means the putting forth of energy, of heat, of force. Life means incessant waste and incessant renewal. Life means perpetual circulation and perpetual need of fresh purification. Life means unceasing combustion, by which I mean simply animal life, the life of the body. There is a life above this which does not depend on movement of gases, liquids, and solids within and without the human frame. Yet even in the higher spirit life of man, it seems as if somewhat the same laws prevailed. There, too, stagnation means decay. Absence of energy means death. There, too, without circulation, without perpetual renewal, without incessant taking in and giving out, a healthy existence is not possible. End of Chapter 11. Recording by John Brandon.
Chapter 12 of The Ocean of Air, Meteorology for Beginners. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Giordano. The Ocean of Air, Meteorology for Beginners by Agnes GIBERNE. How Plants Work. But if from the burning of every substance which contains carbon, if from the breathing of every creature which has life, streams of carbonic acid are being perpetually poured into the atmosphere, how is it that the whole ocean of air has not by this time become unfit for mankind? A room filled with people and having no outlet would after a while be incapable of supporting life. What should prevent the entire atmosphere, once a healthy mixture of gases, from changing in the course of ages to a noxious and deadly mixture? There are enormous quantities of carbon upon earth. If this great mass of carbon, through burning by fire, through breathing of animals, through decay of dead vegetation and dead bodies, became gradually united to yet greater masses of oxygen drawn from the air, and remained permanently in that condition, what other result could follow? Exactly that which takes place in a fast-shut room, containing an open pan of burning charcoal and no chimney. Exactly that would take place with the ocean of air. The amount of oxygen would grow steadily less and less. The amount of carbonic acid would grow steadily more and more, till all living creatures on earth would die of suffocation. Things would inevitably be so, but for the antidote provided. This antidote is found in the green vegetation of earth. Plant existence is not less wonderful nor less mysterious than animal existence, though different in kind. Plants live, grow, take in food, give out vapor, breathe, digest, even work and sleep, alternately, as animals do, only not after the same modes. A plant can no more live and grow, can no more keep in health and do its rightful tasks, without a sufficient supply of light, of air, and of food than a man can. Plants, by which I mean grasses, herbs, shrubs, and trees, as well as all small garden and field plants, are fed in more ways than one. Through their roots they suck up liquid out of the earth, not pure water, but water containing many different kinds of substance in the liquid form, drawn by the water from various kinds of earth through which it has filtered. This liquid food passes slowly upwards through the slender channels of the stem or trunk, spreading through countless tinier vessels, like the capillaries in a man's body, till it reaches the minute veins of the leaves. There much the same takes place with the sap of the plant, as we have seen to take place with the blood of a man on reaching the vessels in his lungs or close to his skin. It flows in little vessels made of so thin and delicate a membrane that gas can easily pass through, and thus the sap comes into contact with the outer air. But the sap is exposed to light as well as to air, which is not the case in the man's lungs. The leaves of a tree are often, and justly, called the lungs of a tree. In some way a strange change is worked in the sap when it reaches the green leaves, or probably this change has begun in its upward passage through the stem and branches, to be perfected in the leaves. A change of some sort always, but by no means always the same change. For when the sap has passed through the tiny leaf veins, and slowly returns into the twigs, the boughs, and the trunk, traveling downward, it is no longer the same liquid that first rose from the roots into the stem, traveling upward. What it has become depends upon the kind of tree. In one tree or plant the sap has become sweet, like sugar. In another it has become acid. In another sticky, like gum. In one it is wholesome and good for food. In another it is rank poison. How these different results are brought about no man can explain to us. We do not even know what causes the sap to rise upward through the tubes of a tall tree. Still less can we describe the manner of its transformation into such different liquids. Some plants will grow in certain soils, and will not grow in others, doubtless because the particular food that they need is not to be sucked out of all soils. Each particular kind of tree, wherever it may grow, always produces or secretes, as it is called, the same particular kind of sap or juice. The deadly nightshade can never, in any soil or climate, be made to secrete harmless sugar juice. The orange tree can never be induced to secrete lemon juice. The gum tree can never be trained to secrete aught else but gum. The mysterious power which we call life dominates the whole existence of the plant. It controls the form and manner of growth, forces the rejection of some materials and the choice of others, uses the selected materials after a definite mode. How and why each plant should follow its own mode, not some other mode, it is impossible to say. Certain characteristics are stamped upon its being, and it acts in accordance with those characteristics. This is all we know, and that is no explanation. The gardener may modify these natural tendencies by training, but the gardener's power is limited. Do what he will, the deadly nightshade is deadly nightshade still, and the orange tree never becomes a fig tree. Plants have another mode of taking in food, as well as through the roots. This is through the leaves. The leaves are not only a perfect laboratory, with the most delicate appliances for the manufacture of various juices out of crude material. In addition to this, they have another work to carry out, a work of worldwide importance to the human race. They have to act as the antidote of which I have spoken. They have to undo that which men and beasts and burning substances are always doing on earth. The leaves of a plant or tree have an extraordinary power of sucking carbonic acid gas out of the atmosphere, and drawing it into themselves for the use of the plant. It is an absolute necessity that every plant and tree should have a goodly amount of carbon from somewhere for growing purposes. Plants, like men, are built up of carbon. Some may be obtained through their roots out of the earth, but by far the greater part is gained by the leaves straight from the air. For men, as for plants, carbon is a necessity of growth, but a man cannot receive it straight from the air. He gets his share in quite another way, through those very plants which have first secured and made it ready, fitting it for his use. Every time a man feeds upon vegetable food, or upon animals which have fed upon vegetable food, he takes into his frame carbon prepared by plants for his use. Footnote: Plants, therefore, are the hewers of wood and drawers of water for other living things, and this property which they so largely possess, of constructing from materials not directly available for animal nutrition substances which are so, is found to be uniformly attended with the presence of a peculiar green coloring matter known as chlorophyll. Huxley and Dyer, Encyclopaedia Britannica. End of footnote. You have seen already that animals do in breathing exactly what is done by burning coal or wood. They carry on a work called oxidation. They unite some of the carbon in themselves to some of the oxygen out of the air at a certain degree of heat, and send forth streams of carbonic acid gas. The plants of earth, large and small, by means of their delicate green leaves, do precisely the opposite of this. They seize upon the carbonic acid gas, which, ever growing in amount, threatens in time to fill the air ocean, and stifle every living creature. By some mysterious means, helped by the sunlight, they separate the carbon and the oxygen of which it is made. They hold the carbon fast, and send it down little channels for the use of the growing plants. Lastly, they pour back into the atmosphere the pure, life-supporting oxygen, broken loose from its union with the carbon, and once more fit to be breathed by man. See what an extraordinary contrast between animals and plants. Suppose you have a shut room containing several people, and containing also in a bow window, where the sun shines brightly, a mass of plants. Each person there is stealing oxygen from the air and sending out streams of carbonic acid as fast as he can. Each plant there is taking in carbonic acid from the air and sending out streams of oxygen as fast as it can. So the man undoes the work of the plant, and the plant undoes the work of the man, each counteracting the other. If you have exactly the right number of plants to balance the people present, if the plants are all in a healthy condition, and if there is plenty of sunlight, then there is no fear that the air of the room will become too full of carbonic acid gas. For just as fast as the people breathe it out, the plants will take it in, supplying its place with oxygen gas. But such a balance could only be secured in daytime. The leaves have no power to carry on the work of which I am telling except with the help of sunlight. So markedly is this the case that plants are sometimes said to be made of carbon and sunlight, and when coal is burnt, it is said to be giving out in heat the bottled-up sunlight of past ages. Not long ago, it was customary to say that plants breathed in a mode exactly the reverse of our mode, that while man in breathing kept the oxygen and got rid of the carbonic acid, plants in breathing kept the carbonic acid and got rid of the oxygen. Now, however, scientific men do not as a rule regard this operation as the breathing, but rather as the digestion of a plant. So if the leaves act the part of lungs, in exposing to outside air the sap or blood of the plant, they also act the part of his stomach in digesting the food obtained from the air. Plants, like animals, do breathe, and must breathe, at least when actively living and growing, not only in the day, but also at night. Plants, like animals, must have oxygen. They, like ourselves, breathe in air, keeping the oxygen and getting rid of the carbonic acid. This goes on constantly. Digestion does not go on constantly. It ceases at night, for leaves can only digest in sunlight. So by the breathing of a plant is meant something analogous to the breathing of an animal. By the digestion of a plant is meant the peculiar work done by green leaves, and breaking up carbonic acid under sunlight, keeping one part, getting rid of the other. It has been long known that plants send forth oxygen by day and carbonic acid at night. If they breathe like animals, they doubtless give forth carbonic acid both night and day. That, however, which escapes in the daytime is at once caught up again and digested as food, only the oxygen being freed. So practically no carbonic acid is added to the atmosphere by a plant in daylight. At night, when digestion stops, it is able to escape. For this reason, plants in a bedroom at night are not wholesome. In any case, and whatever be the precise explanation of these processes, there can be no doubt that the great work of green leaves upon earth is that of air purification. The work must of necessity be fitful and intermittent in such a climate as ours. In the tropics, the luxuriant masses of vegetation carry it on with ceaseless vigor, month after month, so long as the blazing sun is above the horizon. There is the real safeguard for the life of mankind in the ocean of air. There is the mighty antidote to carbon burning, to animal breathing all over the world. Thither relays of air are borne from north and south in ceaseless streams for perpetual repurification. End of Chapter 12. Recording by Greg Giordano, Newport Richey, Florida.
Chapter 13 of The Ocean of Air, Meteorology for Beginners. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Ocean of Air, Meteorology for Beginners, by Agnes GIBERNE. Water in the Atmosphere. Air is never perfectly dry. We talk of damp air, or dry air, and of very dry air, but the dryness is at most only comparative. Atmospheric air is not found utterly devoid of moisture. The use of the word very shows this. If the air were absolutely dry, we should not call it very dry. A perfect square is not very square, but simply square. If something is spoken of as very square, we understand that the said thing is not usually square, and that for once it nearly approaches squareness. So when we talk of air that is very dry, we only mean that it approaches more nearly than usual to complete dryness. The ocean of air which surrounds our Earth is commonly spoken of as the atmosphere. More strictly, it consists of two atmospheres, each separate from the other. There is the atmosphere of dry air, formed of oxygen and nitrogen mixed together, and there is also the atmosphere of water vapor. The atmosphere of dry air remains always gaseous, except when locally interfered with for the moment by burning and breathing operations. It also remains the same in quantity and quality. The atmosphere of vapor is in a state of perpetual change. The amount of vapor present in any one place is always varying. These two atmospheres float together, intermingled in the closest companionship. The particles of each lie among and between the particles of the other. This is a common state of things with gases, because gas particles are far apart. Two solids or liquids cannot occupy the same spot, but two bodies of gas or vapor do so without difficulty. Strictly speaking, the loose floating particles of one slip freely among the loose floating particles of the other. As the atmosphere of dry gases is very much the more abundant of the two, we usually speak of it as the atmosphere par excellence, and of the floating moisture as an important and changeable ingredient in the atmosphere. Enormous quantities of watery vapor float at all times in the ocean of air, for the air is incessantly at work, hiding away supplies of vapor in its secret recesses, giving forth fresh supplies for the use of the world. You have watched the long cloud of white fog pouring from the funnel of a steam engine. Not smoke, for smoke is unburnt carbon, and not steam, for real steam is invisible, but white fog or mist springing from steam. You have noted how quickly it vanishes. That fog is made entirely of water. When it disappears, the water has passed into the atmosphere, there to float as invisible vapor. You have observed a similar white fog pouring from the spout of a kettle. More correctly, from the stream of invisible steam which issues from the spout when the water boils. If you look closely, you will notice a little space between the end of the spout and the beginning of the small white cloud. This little space, apparently empty, is filled with real invisible steam. That cloud is all made of water, and it too passes rapidly away as vapor into the air. You have seen how a wet cloth hung before a fire or placed with warm sunshine will gradually lose its dampness and become dry. All the water which soaked that cloth and made it wet has passed into the air to float as water vapor in the atmosphere. You have known ponds and rivulets shrink and lessen, perhaps quite dry up, in a spell of hot weather. The whole body of pond or rivulet water has been, so to speak, drunk up by the thirsty air. No longer visible as liquid water, it wanders free and unseen as vapor through the ocean of air. This passing of water into the atmosphere is called evaporation. Water, as already explained, may be at any time in any one of the three forms of matter: the solid, the liquid, and the gaseous. It is solid as ice. It is liquid as water. It is gaseous as steam or vapor. That which causes it to pass from one state to another is increase or decrease of heat. The effect of heat upon almost all substances is to make them expand or grow larger. The effect of cold is to make them contract or grow smaller. Suppose you have an iron ball which will just drop through a ring, with no spare space left. If you heat the ball, it will grow larger, and will rest upon the ring, instead of falling through. The heat has expanded the substance, driving farther apart the minute, separate particles of which it is made, so that as a whole it must take up more room. When a solid substance is melted or thawed into a liquid, the liquid, as a rule, occupies more room than the solid did. It has expanded or grown larger. Its particles are farther apart. There are a few apparent exemptions to this rule, owing to the manner in which solids are formed through crystallization. When water freezes into ice, the minute ice needles cross one another in a peculiar method of arrangement, by which large unfilled gaps are left in the midst of them. Thus, ice is really larger and occupies more space than the same quantity of water, even though the tiny particles of each ice needle have actually drawn more closely together. The same thing is seen with the solid and liquid forms of iron, of bismuth, and of antimony. Well for us that it is so with water. If water, becoming a solid, shrank in size and increased in weight, results would be disastrous. Every water surface, in the winter of temperate regions, would form, on the first frosty day, a layer of ice. The ice would shrink and remain at the bottom, another and another ice layer forming above, and shrinking to bear it company. In this manner, every pond, every lake, nay, even ocean waters not far north, would become dense masses of ice. No moderate summer heat would suffice to thaw these masses. That iron and bismuth follow the same rule is interesting, but comparatively unimportant to mankind. That water should do so does appear to be a most merciful provision for the world generally. When a liquid substance is changed into a gas or vapor, the gas or vapor takes up always a great deal more room than the liquid did. How much more depends on its degree of heat. In any case, it expands enormously, the particles floating far apart. This change of size or volume goes on to such an extent that 1 cubic inch of water will spread out into nearly 1 cubic foot of steam. A solid substance is of a certain definite shape and occupies a definite amount of room. The amount varies slightly, since even a solid swells and shrinks a little by being made hotter or colder. The gold ring, which just fits your finger on a cold day, will probably be rather tight on a very hot day, for your finger is apt to swell with the heat and to shrink with the cold to a greater degree than the gold of the ring. Still, the variation with a solid is at its most slight. The shape, and generally speaking the size, are constant. If put into a large empty box, it will not alter its shape or grow larger to fill the box. A liquid substance has no definite shape of its own, but flows easily into the outlines of any vessel that may contain it, while it too occupies a definite amount of space. A pint of water, poured from a pint measure into a quart measure, will not swell out to fill the bigger vessel. It will only spread to cover the bottom, remaining in quantity 1 pint still. Most liquids, like solids, gently expand with heat and shrink with cold, but to no great extent. As gas or vapor has no particular shape and occupies no particular space, we may talk of a cubic foot of steam, referring to the stream as it first springs from boiling water, or to a cubic foot of air at a certain distance above Earth's surface. In reality, the amount of steam or vapor, gas or air, which fills a small vessel, will also fill a large one. Gas is so elastic as to be able to stretch itself to any extent. In the matter of compressing gas into a smaller space, there are early limits, for a gas will by no means endure any amount of squeezing. The separate particles of gas, more especially of a heated gas, are always striving to get farther apart. To give them extra room is to fall in with their inborn tendencies. To press them closer together is to go in the teeth of those natural tendencies. Suppose you have a pint measure full of gas, of any gas you choose, or if you like, of common air, and a quart measure emptied of air. You pour the contents of the pint measure into the quart measure, taking care to let none escape. The pint of gas will at once expand to fill the quart measure. You then pour the contents of the quart measure into a gallon measure, with the same precautions. The gas will instantly expand to fill the gallon measure. In thus expanding, the gas or air grows thinner. If you pull out a piece of elastic, it becomes thinner as well as longer. The particles of gas move farther and farther apart. A less and less number of them are to be found in each cubic inch of space. But however large the containing vessel may be, there is always as much gas in one part as in another part. The gas is always equally distributed through the whole. It always accommodates itself to the size and shape of the vessel, stretching out in every direction so as to pervade the entire space. It is more or less dense according to the space it has to fill. The density of the air in the lower levels of the air ocean is much affected by heat. One cold morning, we will suppose, a man encloses exactly 1 cubic foot of air and weighs it. He weighs not the vessel containing the air, but the air itself, just that amount of it which will fill, without stretching, a measure 1 foot high, 1 foot broad, and 1 foot deep. There are delicate instruments made for such delicate weighing operations. The weather changes and becomes much warmer. Some hours later, the man does the same again. He encloses another cubic foot of air and weighs it. He finds that the second supply, being warmer, is lighter in weight than the first supply. The reason why is not distant. Increased heat has driven the particles of air farther apart. The number of floating particles in a cubic foot of air is not so great as a few hours earlier. Something more than a cubic foot of air would now be required to weigh the same as a cubic foot of air did in the early morning. For the material of which it is made is stretched out more widely. Therefore, it has grown thinner. If we knew exactly how many air particles were in the cubic foot of cold air, and if we could now enclose a supply of warm air containing just that number of particles, it would weigh the same as the cubic foot of cold air. But it would not be a cubic foot of air. It would be larger. Warm air near the level of the sea is always lighter than cold air. Warm air swells, occupies more room, and is disposed to flow upward. Cold air shrinks, takes up less room, and is disposed to flow downward. This is equally true of the two interwoven atmospheres, that of dry gases and that of water vapor. In the higher levels of the ocean of air, a somewhat different state of things is found. The density of the air is mainly the result of the Earth's attraction, though also affected by heat and cold. If it were not for the changing power of gravitation, each particle of air would rush as far as possible from all other particles of air till the entire atmosphere had melted away into distant space. This binding power steadily lessens, mile by mile, with greater distance from Earth's surface, and the weight of the down-pressing air above lessens also. So in upper regions of the atmosphere, air expands, not from heat, but from lessened weight and attraction. The cold in those higher levels is intense. Nevertheless, the air particles spring farther apart, and the air grows thinner. The atmosphere of vapor reaches to a great height, but, like the atmosphere of dry gases, it is far less dense above than below. End of chapter 13.
Chapter 14 of the Oceans of Air, Meteorology for Beginners. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Elizabeth Miles. The Oceans of Air, Meteorology for Beginners by Agnes GIBERNE. About evaporation. Chapter 14, About Evaporation. If there were no water vapor hidden away in the secret recesses of the ocean of air, we should not only have no dew, no clouds, no rain, we should not only see all green things wither for lack of moisture, but also the sun would shine down upon us with a fierce and glaring heat, such as now we can hardly even imagine. The veil of floating moisture in the atmosphere acts in two ways as a protection. It shelters us from excess of heat and also from excess of cold. It keeps off some of the sun's burning glare from us, and it also keeps in a great deal of the earth's warmth for us. As a screen, it gently dims the glare and steals some of the heat from the traveling sunbeams. The tiny particles of invisible water help greatly to tone down the fierce straight radiance of the king of day, but perhaps the work which is done by the vapor at night is even more important. All day long the ground gathers heat from the sun's rays as they beat downward, and when the sun disappears, the stored-up warmth begins at once to pour itself out into space. If there were then no floating vapor above to act as a sheltering screen, the ground would lose its heat with very great speed, and the suddenness of the chill would be fearful. The shielding vapor prevents this, like a soft, unseen blanket holding in the earth's warmth. We all know how much warmer we feel on a cloudy night than on a clear night. The clouds act as a visible blanket or counterpane, radiating back to earth its escaping heat. If there are no clouds, the ground loses warmth far more rapidly, though even then there is always the soft, fine veil of vapor, one of Earth's outer garments. A man walking up a mountain or rising in a balloon will find certain differences in the ocean of air as he ascends, if he has with him the right instruments for testing the state of the atmosphere. He will find that the air has grown more thin or rare. He will find that it has grown colder. He will find that it has grown drier. On the summits of great mountains, the glare of sunshine is often almost overpowering, even while the frost is so intense that the sun's rays are powerless to melt the snow. One reason for the dazzling glare is that the air contains there much less vapor than at lower levels. The shielding screen of vapor has grown thin and poor. The floating vapor is not only more in amount below than above, it also varies exceedingly in different places, and it keeps on varying. Sometimes the air around us is damp, sometimes dry, sometimes it is wringing wet, sometimes parching. These changes we know from our own sensations. Everything wet or moist on earth gives off gentle streams of vapor into the air, more or less abundant streams according to its degree of warmth. Day and night, summer and winter, the air is at work, receiving or drinking up water from seas and rivers, ponds and streams, clouds and fogs, earth and grass, plants and animals. In short, from all damp surfaces of every imaginable kind and description. There are a few solid substances which steadily give off their material somewhat after the fashion of liquids. A lump of camphor, for instance, wastes slowly away, growing smaller as its particles pass into the air. All liquids dry up, slowly or fast. If there were no air, they would still dry up at the same rate or even more rapidly. We may talk, and talk truly in a sense, of the air taking in or drinking up moisture, but the air does not cause evaporation. A damp surface evaporates of itself, and the air receives the particles of water as they leave the damp surface. This is constantly going on. Where water is to be found, there, as a rule, a soft vapor creeps gently away into the atmosphere. The same thing happens, though this is less generally known, with water in the solid form. Both ice and snow evaporate, creeping slowly away particle by particle. Sometimes a whole slight fall of snow will vanish thus, without any apparent thaw. More commonly, the fall is too heavy or the thaw comes too soon for this gentle drying up to be noticed. So the air is ever at work, taking in moisture from every possible quarter, until full. Only until full. Air will not hold unlimited supplies of hidden vapor. It will only hold a certain amount, just so much and no more. Directly, air is well soaked. Saturated is the right word. It refuses to take in another particle. Then evaporation grows languid and perhaps even ceases. A laundress knows well, from sad experience, the difference between drying her clothes on a fine day and on a wet day. She may be ignorant of the scientific cause, but she is aware of the fact. One week she hangs out her rows of wet garments, and a soft, dry wind sweeps past, stealing all the moisture out of them with delightful rapidity. Another week she leaves them to hang for hours, and the damp, motionless air has almost no effect, except indeed to hinder evaporation. After hours of exposure, the clothes are scarcely less wet than when first put out. As she tersely expresses it, they won't dry. But the garments are not willful. The cause lies in the overladen condition of the air, already so full of vapor that it can receive no more. A wind is always good for drying purposes. The air around the wet clothes takes in some of the moisture, becomes saturated, and declines any more. If no breeze stirs, the soaked air remains hanging about the clothes, and drying is at a standstill. But if a wind blows, the wet air passes on, and fresh, dry air comes to carry off further supplies of vapor, and to be in its turn speedily replaced. Thus the work proceeds merrily. If you hold a sponge over a basin of water, letting it touch the surface, the water will soak upward into the sponge till the latter is full and can hold no more. Just so with the atmosphere. It hangs like an enormous sponge over all water surfaces, and the moisture soaks upward into the air till it is full. There is, of course, a difference. A sponge draws the water up into itself by means of what is called capillary attraction. The air does not draw up vapor, but merely receives the vapor which passes off from water. Still, there are points of resemblance. For instance, the drier a sponge, the more water it can hold, and the drier the air, the more rapid evaporation is found to be. This drying process goes on over the whole world, even in the far north and the far south, where ice and snow reign supreme. The same continues. The surfaces of ice and snow are passing slowly away into the atmosphere. In our temperate regions, we are perpetually aware of the fact of evaporation. More particularly, it is apparent in hot and dry summers. Then streams vanish and rivers fall low, ponds disappear, and springs fail. But it is in more southern lands and seas that evaporation is seen in full vigor. The Mediterranean Sea is almost enclosed by land, having only one narrow opening into the outside ocean through the Straits of Gibraltar. The whole of South Europe and the whole of North Africa are drained into the Mediterranean, countless streams and rivers pouring thither by day and night their volumes of water gathered from surrounding tracts of country. Under these circumstances, when we picture to ourselves what is meant by such a watershed, we should certainly expect to find a current flowing from the Mediterranean into the outer ocean through the Straits of Gibraltar. But no, the drying up of the surface of the Mediterranean is so enormous that apparently it more than balances the mighty influx of rivers from north and south, east and west. A steady, sometimes a very powerful, current sets in from the Atlantic through the straits to keep the Mediterranean surface level with the ocean outside. Water always seeks persistently to maintain everywhere the same level. It can never rest for an instant with a slanting surface. The smallest inequality means an immediate flow of water from the higher to the lower part, and the greater the inequality, the more rapid will be the balancing rush. So long as the Mediterranean is joined to the ocean, though by only one inlet, its surface must be level with that of the ocean. If its river and rain supply is greater than its drying up, a stream must pour out to the ocean. If its drying up is greater than its river and rain supply, a stream must flow in from the ocean. If the two are exactly equal, no stream need pass either way. Since we find a stream setting in from the ocean, we judge that more water dries up from the surface of the Great Sea than is supplied by all the vast expanse of land and rivers to north and south, not to speak of the rainfall on the sea itself. There may be, however, a further complication in the shape of a probable undercurrent flowing outward as the upper current flows in, so we must not speak too positively. Along the shores of India, careful experiments have been made to test the amount of evaporation. It is found that about 3/4 of an inch in depth daily passes upward from the whole sea surface. This, if carried on equally all the year round, would give an annual drying up of over 21 feet in depth. Even if, allowing for inequalities, we put the quantity at 15 or 18 feet, it is startling enough. Some mighty power must be at work to lift this tremendous weight of water out of the ocean. When one pictures what is meant by a mass of water 15 feet in depth and hundreds of miles in extent, one gains some dim idea of the force which is needed to bring about such a result. On Earth, no such force exists. If our Earth stood alone in the universe, this vast upheaving of ocean waters into the atmosphere would not be accomplished. When we see the steam which pours from a kettle or a boiler changing fast into white mist, we know well enough what force is at work. It is the force of heat. The glowing fire has caused the water to boil, driving it forth as steam into the air. In the drying up of waters upon earth, in the evaporation of ocean surfaces, heat is again the working power. The sun is the fire which supplies the needed heat. The heat supplied by the sun enters into the water, drives its particles farther apart, and causes it to rise gently as invisible vapor into the air. The heat which works on earth as fire all comes from the sun. If no sun had ever shone in the heavens, we could have on earth no burning coals, no flaming gases. In earlier chapters, it has been explained how combustion may be either a quick or a slow process. Quick, giving out much heat in a short time; slow, giving out the same amount gradually in a longer time. When combustion springs from earthly fire derived from the sun, it is generally more sharp and quick. When the sun acts directly, the combustion is more usually calm and slow. The same difference is seen in the changing of water into vapor. It may be a quick or a slow process, giving out much heat or little heat in a short time. If the transformation is brought about by earthly heat derived from the sun, but acting by earthly methods, it is short and sharp, much heat is given out, and the water rushes away in scalding steam. But if the great sun himself does the work, acting directly on the water, he does it softly, calmly, with no fuss or flutter. The transformation takes place in silence, and the giving out of heat is gentle because gradual. End of chapter 14. Chapter 15 of the Ocean of Air, Meteorology for Beginners. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Elizabeth Miles. The Ocean of Air, Meteorology for Beginners by Agnes GIBERNE. About condensation. Chapter 15, About condensation. Just as a sponge will hold a certain quantity of water and no more, so the air will hold a certain quantity of vapor and no more. But the sponge will hold the same amount of water at all times. The air will not hold the same amount of vapor at all times. Whatever supply may be hidden in the air at any particular moment, one never can be sure how long that supply will be able to stay there. For the question, how much water can the air contain, hinges on another question. How warm is the air? Warm air can hold more vapor than cold air. Hot air can hold more vapor than warm air. The carrying capacities of air for vapor depend upon its warmth or coldness. Happily, the very warmth which makes water to evaporate more quickly also makes the air able to hold a larger supply of vapor. So, in the long run, though not instantly, a change of temperature tells in both ways. Suppose a layer of cold air lies over a lake, receiving more and more vapor until it is quite full. The drying of the lake then grows very languid from the fact of the saturated air weighing down upon it and refusing to take in any more vapor. Perhaps it may even stop altogether. If by any means you could suddenly make the cold mass of air warmer, it would be full no longer. It would receive from the lake fresh vapor supplies until again saturated. Another rise of temperature would bring about the same result. These variations of temperature do in fact happen constantly from different causes. Now let us view the question the other way. A layer of warm air floats over a pond, and water as vapor passes freely into the air till the latter is, in childish parlance, as full as it will hold. Then a current of cold air from elsewhere comes creeping into the warm air, gaining some heat for itself and also cooling the warm air rapidly down, perhaps 2 or 3 degrees. What is to happen next? Cold air cannot possibly hold so much vapor as warm air. The warm air, having been saturated to its utmost extent, must, now it has grown colder, be more than saturated. If you have a large sponge full of water, as full as it will hold, and you give it a slight squeeze, what happens? You make the sponge smaller by your squeeze. Consequently, it is unable to hold so much water. Consequently, a few drops are pressed out. Something analogous to this happens with the atmosphere. The current of cold air acts upon the warm as your hand acts upon the sponge, giving it virtually a gentle squeeze. Thereupon, some drops of water are pressed out. Occasionally, no doubt, the new current of air, though cold, might be so dry as to have power to drink in all the moisture which the other air could no longer hold. In that case, no change would be apparent. Very often, however, the results of the squeeze are plainly manifest. Manifest how? As already said, by drops of water being squeezed out. The analogy of the sponge, however, fails us here, for the drops from the sponge are large and they fall to the ground. The drops pressed out of the atmosphere are extremely small and light, so much so that they float in the air like very fine water dust, as one has said. All of them, so floating in close company, make a mist or fog. This is how the mist comes from the steam which pours from the funnel of a steam engine. The heat of the engine fires turn the water in the boiler to steam. When the steam first rushes out into the air, it is invisible, but the air outside, already more or less laden with vapor, cannot in one moment receive such a quantity of vapor. So a good deal of it has to turn hastily into tiny floating drops of water, streaming like a white cloud from the engine. As fresh relays of unsoaked air come in contact with this cloud of fog, the minute drops are sucked up and soon the whole vanishes. Whether the mist vanishes slowly or fast depends on the kind of day. If the air is dry and thirsty, the newly made fog seems to melt away as if by magic. But if the air is nearly saturated with damp, the tail of fog from the engine hovers a long while in the air before it can be hidden away. On a dry day by the seaside, one may see the funnels of distant steamers carrying a short banner of steam which fast evaporates. On a damp day, long trails of white or gray fog from those same funnels will lie far round the horizon. We have already learnt that the passing of water into vapor is called evaporation. The passing of vapor into water is called condensation. These two, evaporation and condensation, are exactly the opposite each of the other. If a tumbler of water is emptied through drying up, all the water passing into the air is vapor. That is evaporation. If the escaping vapor were all caught as it left the tumbler, were imprisoned, and through the power of cold were restored as water to the tumbler, that would be condensation. Evaporation is caused by heat. The greater the warmth of a liquid, the more quickly it evaporates. Condensation is caused by cold. The greater the cold of a vapor, the more quickly it condenses. When water is evaporated, not one particle of that water is destroyed. It has only changed into vapor, vanishing from our sight. When vapor is condensed, not one particle of that vapor is destroyed. It has only changed into water, returning to our sight. No fairy tales or conjuring tricks were ever so truly wonderful as this disappearing and reappearing of water. We are all so used to the everyday marvels of nature that we forget to be surprised. Yet if this were less common, if we had never known or heard of the transformations of water until today, if we suddenly were to see, for the first time, the whole circle of water changes acted out, they would be to us a series of miracles. It was explained earlier how by the burning of a candle, water is formed, not liquid water, but invisible vapor slipping away silently into the atmosphere. Also, it was explained that if a cold tumbler is held over the flame, the glass is dimmed by a soft mist made of tiny water drops. This is a case of condensation. The cold glass acts like the cold breeze, cooling down the warm air and pressing out a little of its moisture. On a frosty winter's day when we take a walk, a tiny fog or a cloud rushes from our lips with every breath. Warm air laden with moisture pours from the lungs. Meeting the cold air without, it is abruptly chilled and has to part with some of its vapor, which changes into a mist of water drops. The mist floats for a second till the dry surrounding air has had time to drink it up. Here again is condensation, followed by renewed evaporation. In a railway train compartment filled with people, if both windows are shut, the glass will become thick with haze. This haze is formed of water, and the colder the outside air, the more rapidly it forms. Within the compartment, the air grows warm and damp, though heat and moisture poured from several throats. Being warm, it has no difficulty in carrying the supply of vapor, but the cold air outside chills the windows, and the cold glass chills the layer of air next to it. Then, some of the vapor is pressed out by the shrinking air and is laid upon the panes as a collection of minute drops. If this goes on, one layer of air after another making its deposit, for where several people are breathing and moving, the atmosphere cannot be at rest. The tiny drops become presently so abundant as to run one into another, joining to make big drops which flow downward. When the windows are thrown open, the moisture on the panes soon vanishes. The outside air may be cold, but unless extremely damp, it will be able to receive so small a quantity of additional vapor. There, once more is seen condensation, followed by evaporation. The two are perpetually at work on earth, alternating and in opposition, neither knowing repose. The amount of vapor in the air at any one place is always changing, rarely for 2 minutes precisely the same, unless we accept the dead level of dryness attained to by a tropical desert. All over the whole earth, water is vanishing and reappearing, going out of sight into the air and coming into sight out of the air, being evaporated and being condensed, passing from the liquid to the gaseous form and from the gaseous to the liquid form. Evaporation and condensation work in apparent opposition, yet each works into the other's hands, so to speak. Between the two is a perfect balance, which results in order and beauty, circulation and life upon our globe. When through condensation actual drops of water appear, whether as mist or fog, dew or rain, the process is also described as precipitation. The vapor-laden air gives out or drops or precipitates some of its surplus moisture. End of chapter 15.
Chapter 16 of The Ocean of Air, Meteorology for Beginners. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Ocean of Air, Meteorology for Beginners by Agnes GIBERNE. Chapter 16 Dew, Mist and Fog. On a fine autumn day, the sun beats down for hours, warming the earth and the atmosphere, and the warmed air drinks steadily at every damp surface within reach, till by evening it is well filled with moisture. Then the sun sets, and there are no sheltering clouds to hold in or reflect back the heat of the ground. It pours out fast into space, despite all that the soft veil of floating vapor in the air can do. As the ground cools, it helps to cool the layer. Footnote. When I speak of a layer of air, I do not mean to imply separate layers in the atmosphere, like rows of bricks or sheets of cardboard laid one over another. Air has no such divisions in its make, but any substance may be pictured as divided into possible sections, and, in speaking of the air, it is convenient to imagine successive layers. End of footnote. Layer of air next above it. The touch of cold acts as a squeeze, and immediately drops of water are pressed out, minute floating drops borne up by the air because they are so small and light. Thus an evening mist is formed. Light as the floating drops of a mist are, it is questionable whether even they would be supported by absolutely motionless air, since they are not actually lighter than air. But motionless air is a thing almost unknown. On the stillest day imaginable the air still moves. We often have such mists towards night, after sundown, more especially when the ground is low and damp, where therefore the air has been well soaked. Mists and fogs are much alike, being both neither more nor less than ground clouds. A mist is commonly distinguished from a fog as being made of rather larger drops, therefore feeling more wet. Mists are often seen in the evening or early morning lying over rivers, sometimes most sharply divided in their outlines, scarcely reaching beyond either bank, but piled up within like a pack of cotton wool. Water will not part quickly with its heat like the solid ground, and long after the earth and air have cooled down, the river water keeps moderately warm. Being warm, it continues to part with a good deal of vapor, more than the chilled air is able to take in. So then a little bank of mist or fog is formed, all along the course of the stream, more or less dense according to the warmth of the water and the coldness of the air. The river keeps offering water to the air, and the air keeps refusing to drink because it is not thirsty. Between the two, the rejected vapor turns into a cloud, and hovers in a waiting attitude till air and water shall come to a definite conclusion. This patience is generally rewarded after sunrise by the warmed atmosphere drinking up the fog with eagerness. Sea fogs are brought about in much the same manner as meadow mists. The air which lies over the sea, having a free water surface to feed on, gets well filled with vapor. Then a cold breeze from some new quarter blows into the warm air, chilling it, and at once the hidden supply of vapor becomes too great. A wet mist or fog is quickly developed, thickening the atmosphere and blotting out the horizon. The perils of such a fog are sharply felt by those at sea, and were sharply evidenced lately by a collision between the Ostend and Dover mailboats in mid-channel. Suddenly and without warning, the passengers of the lesser boat saw a great steamer burst through the gloom close at hand, bearing down upon them at full speed. There was no time to get out of the way, no time to evade the peril, and the worst that any man expected was not worse than the reality. For the heavier vessel struck the other full amidships, and cut clean through her as with a knife, so that the two halves of the stricken vessel fell away from the bows of her assailant, as a divided bank of snow before the snowplow. Strange to say, one of the severed halves floated for hours after the collision. Sea fogs are often swept by a wind a short distance inland, but over the dry ground they soon die away. London fogs, too, spring into being after much the same method. Two currents of air meet and mingle, one warm and moist, the other cold. If the cold current is dry enough to receive all the superfluous moisture of the warm current, no marked effect is seen. At the most only a slight haze is formed, rapidly to be dissolved. But if, as is often the case, the cold air already has its full complement of moisture, then, when by contact it cools the warm damp air, a fog must be the result. The water of the Thames there is often warmer than the air above it, and the same effect is produced as elsewhere by the sudden cooling of the ground after sunset. In town, however, an additional and very unpleasant element is found, from which country and ocean are free. The air of London is always more or less full of countless floating black specks, minute portions of carbon dropping from the smoke which thousands of chimneys are ever pouring into the atmosphere. Innumerable water drops, squeezed out of the cooling air, form around or cling to these tiny specks, and they lend to the fog its peculiarly thick and yellow or black look. Once let a fresh breeze sweep over the city, bringing fresh supplies of unsaturated air, able to hold more moisture, and the fog quickly vanishes. It is sucked up drop by drop into the interstices of the atmosphere. But if no such breeze comes, and the air remains at the same temperature, the fog may linger long, growing probably worse and worse as more smoke is weighed down by the heavy damp air, to supply fresh carbon centers for new little drops. Sometimes an unhappy variety for the Londoner occurs, in the shape of a fog overhead, not resting on the ground, but most effectually cutting off the sun's rays. It is a little startling for a country cousin, running up to town for a few hours, out of a clear atmosphere, to find the mighty city plunged at midday into Egyptian darkness. This was my own experience one April morning of the current year. To reach the city proved not difficult, though the outskirts looked murky, but during a 2 hours business interview the air grew darker and yet more dark. Gas had to be resorted to, and by 1 o'clock it was, to all intents and purposes, absolute midnight. No fog worth mentioning was in the streets, and the lamps gave out their light well, but a dense pall overhead shut away all daylight. It was as easy, no doubt, to go about as in any gas-lighted winter night, only it was not exactly what one expected on an April day, and there was an unpleasant consciousness that the overhanging pall of fog might at any moment descend to the level of the pavement, putting an end to traffic. It seems not at all improbable that even with country and sea fogs, the floating drops of water always form around light specks of solid substance borne up in the air, too small and light to be perceived. Some maintain that no fog, no mist, no cloud can ever be condensed out of the vapor in the air without the help of these minute particles for the water drops to cling to. If so, The floating dust of the air has a great and important part to play in the vast water circulation of Earth. It is only in large cities, however, that these specks are so considerable in size and number as visibly to thicken the fog and to endow it with color. As London waxes yearly bigger, as chimneys grow yearly more multitudinous, as fogs become yearly more dense and overpowering, the future of the city has a serious look. No doubt, however, when things have reached such a pitch of misery that human nature can endure it no longer, Englishmen will at length put their heads together, and will devise some method for burning instead of breathing their smoke. One might well ask, why wait so long? But the average Londoner is a much enduring individual. There is another kind of evening condensation of moisture often seen, and none the less singular because common. This is the dropping of dew. Dewdrops have something about them very pretty and poetical. They arrive so softly, without stir, not pattering like rain, or clattering like hail, or accompanied by rough winds. Dew comes on warm and still nights, creeping gently into existence under cover of the dusk and fading quietly out of existence under the early sunshine. Dew does not fall from clouds overhead. It is commonly formed only when no clouds are there. Clouds act as a blanket, holding in the warmth of the earth, reflecting that warmth to the ground, and for dew the quick cooling of earth is needful. It comes into being much after the same fashion as a meadow mist. Sometimes the two are found together, dew dropping out of the lower layers of air close to the ground, and mist being formed out of the next layers of air above. Properly speaking, dew is hardly dropped, since that would imply the falling of the drops, for at least a little distance, and it appears that they do not fall. The moisture is rather placed or deposited by the air on any surface ready to receive it, much in the same fashion that moisture is deposited upon the window of a room or a railway carriage, when the air within is warmer than the air without. The sun having set, the ground cools fast, if there are no clouds. The air also, lying on the earth, is quickly lowered in temperature. On a still evening, when it does not move on, it reaches presently a stage called dew point. By this is meant that no dew has yet been formed, but that the air can endure no further cooling if it is to hold still all the vapor it now contains. It is in fact completely saturated. If the cooling continues, the next step is the appearance of dew. Drops of water, larger and smaller, are squeezed out of the air and cling to grass blades, leaves, twigs, spiders' webs, and aught else in their way. The dewdrops are by no means equally distributed over the ground. They favor most those substances which part with heat most readily, which therefore grow cold most quickly. Grass and plants lose heat much faster than paving stones or the road. So dew is to be seen clothing grass and leaves with shining drops, while pavement and road are still dry. Sometimes the dew point is down below the freezing point. Then the air, instead of depositing drops of water, dresses fields and hedges, perhaps even the whole landscape, in a coat of white hoarfrost. Hoarfrost is not, as many suppose, dew first dropped as water and then frozen. It is deposited at once in the frozen and solid form. Like dew, it clings most readily to those objects which part most quickly with their warmth. Hoarfrost is often seen on lawn and bushes, when the gravel walk is free from it. Generally the coating is slight, but sometimes it may be seen so thick as to look like a fall of snow. On the shutters of the observatory at the top of the Puy de Dôme, it was on one occasion actually 3 feet thick. In tropical countries, the amount of dew formed is greater than anything we ever see in temperate climates. Travelers have found it possible, by pouring the dew from one large leaf into another, to obtain water enough for washing their hands. Much of this abundant moisture sinks into the earth and feeds the thirsty roots of plants. When once the tropical sun rises, all the dew which has not soaked downward vanishes into the atmosphere like a dream. In certain American forests, dew is sometimes formed at the level of the treetops. The abundance of it is extraordinary, owing to the quantity of vapor in the air and the rapid changes of temperature. It is said that an actual shower of dew, like a shower of rain, is occasionally felt below. This no doubt results from the running together of the drops when formed, as moisture deposited on a window will run together and flow downward. The slow heating and cooling of water has been alluded to in this chapter, and it will be repeatedly spoken of again, in connection with winds, climate, and weather. That peculiar characteristic of water, which is known as its great specific heat, in other words, the fact that water requires more heat to raise it to a certain temperature than perhaps any other known substance, has widespread results. The touch of an overruling and all-wise providence may be seen here. If water could be warmed and cooled with the ease and rapidity of other substances, the climates of many parts of earth would be in consequence so changed that lands, now more or less densely inhabited, would become almost uninhabitable. End of chapter 16.
Chapter 17 of The Ocean of Air, Meteorology for Beginners. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Elizabeth Miles. The Ocean of Air, Meteorology for Beginners by Agnes GIBERNE. The Mountains of Cloudland. Chapter 17, The Mountains of Cloudland. Wonderful scenery is found in Cloudland by those who love to study it. Vast mountain masses and jagged peaks alternating with lakes and hills dressed up in glowing sunlight. Yet the solidity of Cloudland exists only in our imagination. Clouds are, as a general rule, neither more nor less than masses of wet mist or fog, floating in the atmosphere, perpetually forming, diminishing, vanishing, reforming, growing, lessening again, never remaining for any length of time in the same shape or the same place. Evaporation and condensation are unceasingly at work in Cloudland. Every mist cloud that we look upon is either growing or melting away. It is never a fixture. True, some clouds seem to us to remain long in one position and to keep long one shape, if a few hours or less can be called long. But in reality, there is not even that small amount of fixity. When they seem to be at rest and changeless, it is only because they are so far away that we cannot in a short space of time detect the movements going on. Or else it is because the whole sky overhead is shut off by a gray pall of cloud, which may move or grow or lessen without our being soon conscious of it. Like fog and mist upon Earth's surface, clouds are commonly made and dispersed through the meeting of two currents of air, one warmer than the other. If, when the two currents mix, the air of the warmer is so much cooled down that it cannot carry all its moisture, while the air of the cooler is unable to take in more moisture than it has already, then a new cloud is formed, or if a cloud is already there, it grows bigger. But if, when the two currents mix, the air of the colder gains so much warmth that it can receive more vapor than it already has, then any cloud floating there will be partly or wholly sucked up so as to lessen in size or to disappear. This is the manner in which clouds often vanish. Sometimes the wind carries them onward out of our sight. Quite as often they evaporate or are dried up by the air, vanishing exactly as the fog cloud from the funnel of a steam engine vanishes. On a tolerably fine day, when there is a fresh breeze and many small clouds lie rather low down, the changes in the form and position of these clouds are astonishingly rapid. Anyone may test the truth of this for himself by watching with steady attention during 20 or 30 minutes, but few people will take so much trouble. All clouds are not formed of mist or tiny water droplets. There is every reason to believe that some are made of ice. Clouds float at very different levels in the atmosphere. Careful observations have been made in several places with varying results. When at a great height, it is believed they are formed not of fog or mist, but of tiny interlaced ice needles. They are, in short, frozen. 2 facts bring us to this conclusion. One is that some curious effects, such as halos and mock suns, are occasionally seen through high-level clouds and never through low-level clouds. These effects are, in all probability, caused by the refraction of light through ice, since they could be thus produced, while they could not be produced by the passing of light through mist. The other fact is that at so great a height the cold is very intense, and water must almost of necessity become ice. If a fog cloud were there, it probably could not remain a fog cloud, but would have to become an ice cloud. On Earth, at a certain temperature, we always have hoarfrost in place of dew and snow in place of rain. Just so in Cloudland, at a certain temperature, there would be frozen clouds in place of mist clouds. Clouds, as already stated, commonly spring from a cold current of air meeting a warm current, but this is not the only mode in which they are formed. A high mountain may often be seen capped by a cloud of a certain well-defined shape, and this shape will perhaps remain for hours almost without change. Sometimes, if the wind is high, a long, slender ribbon or tail of cloud will stream persistently from the top of a lofty peak. The warm wind of the lower country, carrying plenty of moisture, suddenly reaches the mountain and has to rush upward. It cannot stop, for the pressure of air behind forces it on. As it rises, it grows colder, and the chill of the icebound peak adds further cold, compelling the air to part quickly with some of the vapor so easily carried below. Thus a cloud is formed. We may learn something more from this fog ribbon flowing from the peak as to the nature of a cloud. If you watch carefully the slender cloud from a distance, you will find it keep the same shape for a good while, unchanged, perhaps for hours. Then, drawing nearer, you will find that, while the cloud as a whole remains unaltered, the particles of which that cloud is made are never the same for 2 minutes together. The strong wind brings perpetually fresh supplies of moisture-laden air pouring up the mountainside from below, and the surplus moisture is perpetually being condensed into fog by the cold peak. Yet the cloud grows no larger, for the wind perpetually carries away the fog to be evaporated anew into the atmosphere. At one end of the long cloud ribbon it is born into existence out of the air, and at the other end, indeed along its whole length, it dies out of existence into the air. The cloud as a whole remains, but fast as it is formed, so fast the air all around dries it up. The water particles of which it is composed are whirled onward unceasingly, like the waters of a river. The same thing on a small scale may be seen in the little cloud which forms outside the spout of a boiling kettle. The cloud keeps the same shape, remaining intact while the particles of which it is composed are in ceaseless motion. Fresh particles rush momently out of the spout to take their place in the cloud. Then, in their turn, they are swept along and vanish from sight. This, in a greater or less degree, is the character of all clouds, at least of all lower-level mist clouds. The higher-level snow clouds no doubt evaporate more slowly, just as ice and snow evaporate more slowly than water. Clouds are commonly divided into different classes, reckoned according to their form and appearance, as seen by us from the bottom of the ocean of air. The 3 leading kinds are, first, the mare's tail cloud, known as cirrus; second, the ground fog, known as stratus; third, the woolpack cloud, known as cumulus. But as we seldom find a perfectly pure specimen of any simple substance, so we seldom come across perfectly pure specimens of these 3 simple types of clouds. Far more commonly, we see clouds which are a mixture of 2 or 3 simple types, which therefore we may call compound clouds. The mare's tail cloud is usually regarded as a sign of coming wind. Pure mare's tail, or cirrus, is feathery and streaked and lies always at a great height. A balloon floating over 4 miles high seemed to approach no nearer the distant cirri than when it first left the ground. Clouds which are a mixture of the mare's tail and ground fog lie not quite so high, though still at a level which probably means that they are formed of ice, not of mist. It is through them that mock suns are seen. Mackerel sky clouds are a mixture of the woolpack and the mare's tail. These two lie lower than the pure mare's tail. It is often difficult, looking up from the floor of the air ocean, to decide with any certainty which class each particular cloud may belong to. Even practice eyes are frequently at fault. Ground fogs lie much lower in the atmosphere and much nearer to us than those of the mare's tail type. Therefore, they have not such sharply defined outlines, but appear more hazy, more like masses of gray fog. Because this kind is never found at any great height, and because it often forms over low lands before night to vanish in the morning, much like the evening mists of marshy and damp places, it has been named the ground fog. But it is distinctly a cloud far above our heads, not to be confounded with mere fogs and mists which rest upon the ground. Sometimes the ground fog clouds spread over the entire sky, shutting off all sunshine, while the air below is foggy and dull. As a rule, however, they do not mean rain. Another kind of cloud, which often overspreads the whole sky, occasionally ushering in a storm, is a mixture of the ground fog and the woolpack. The genuine rain cloud, more or less a compound of 3 simple types, is simply that which the name implies, the bringer par excellence of rain. Still, it must not be supposed that every cloud which pours drops upon earth is necessarily a nimbus cloud. The woolpack cloud is usually formed of rounded, mountain-like masses, more or less white and woolly, and often very beautiful in sunshine. It is commoner in summer than winter. Piled-up heights of snowy brightness, softened by gray shadows, are visible against the blue sky on many a fine day. The base of the mountainous pile is frequently a sharp horizontal line, from which the fairy-like heights spring upward. This is the view which we have of woolpack clouds lying at some distance from us between the zenith and the horizon. If such a cloud mass is exactly overhead, we look up at a flat gray base which cuts off the sunshine. There may be splendid piles of white cloud above, but we can gain no glimpse of them. A man who would see mountain peaks must be outside and away from them, not under the mountain's base. Woolpack clouds are produced by a steady upward current of warm air carrying abundance of vapor. As the air is cooled in its ascent, great quantities of the vapor are fast condensed into masses of mist or cloud, which collect into rounded shapes. No doubt the most wonderful views of Cloudland are to be obtained from balloons. I cannot better close this chapter or introduce the next than by quoting from the vivid descriptions given by Mr. Glacier of what he and his companions saw on 2 occasions. The first extract relates to an ascent in fine weather, the second to an ascent in wet weather. On the morning of August 21st, by 4:30, my instruments were replaced and we again left the earth. The morning was warm but dull, the sky overcast with cirrostratus cloud. The temperature was nearly as high as 61 degrees. We at first rose very slowly. By 4:38 we were 1,000 feet high. At 4:41 there was a break of clouds in the east, and a beautiful line of light was seen, with gold and silver tints. We were then still only at 1,000 feet. Here and there, dotted over the land, the morning mist was sweeping. At 4:51 the temperature was 50 degrees. Scud was below us, and the night cloud was in a transition state, forming into the cumulus at the same level as we were, about 3,500 feet. Black clouds were above, and mist was creeping along the ground. At 4:57 we were in cloud, surrounded on every side by white mist. The temperatures of the air and dew point were alike, as both the dry and wet bulb read 39 3/4 degrees. The light rapidly increased, and gradually we emerged from the dense cloud into a basin surrounded with immense mountains of cloud, rising far above us, and shortly afterward we were looking into deep ravines, bounded with beautiful curved lines. The sky immediately overhead was blue, dotted with cirrus clouds. As we ascended, the tops of the mountain-like clouds became silvery and golden. At 5:1 we were level with them, and the sun appeared, flooding with golden light all the space we could see for many degrees, both right and left, tinting with orange and silver all the remaining space around us. It was a glorious sight indeed. At this time we were about 8,000 feet high, and the temperature had increased from 38.5 degrees in the cloud to 41 degrees. We still ascended, rather more quickly as the sun's rays fell upon the balloon, each instant opening up to us ravines of wonderful extent and presenting to our view a mighty sea of clouds. Here arose shining masses of silvery heaps, there large masses of cloud in mountain chains rising perpendicularly from the plain, dark on one side, silvery and bright on the other, with summits of dazzling whiteness. Some there were of a pyramidal form, and a large portion undulatory or wavy, in some places subsiding into hollows, and in one place having every appearance of a huge lake. Nor was the scene wanting in light and shade. Each large mass of cloud cast behind in its shadow, and this circumstance, added to the very many tints, formed a scene at once most beautiful and sublime. So much for Cloudland in fair weather. Now for the contrast in a June ascent from Wolverton, with concomitants of rain and high wind. We were released by the simultaneous yielding of men, and in a minute were 4,000 feet above the earth. At this elevation we were chilled by the clouds which we entered, but cheerfully looked forward to emerging on the other side into the region of pure sky and brilliant sunshine. On the contrary, all was gray, colorless, and gloomy. At 9,000 feet the air was filled with a moaning or sighing, like the wind previous to a storm. This was our first experience of the sound, and we listened to identify it with the cordage of our machine working in the air, but it was the sound of conflicting currents meeting and opposing each other in the wilderness of space. Now we were 2 miles high, with faint gleams of the sun, expecting him momentarily to appear. Instead, we entered a fog, and then into a fine and wetting rain, afterwards a dry fog, and then again a wet fog, and that was again repeated. Then we were mocked by gleams of sun, and found that we had ascended 3 miles high. At 17,000 feet there was no change. At 4 miles high, dense clouds were still above us, and for a distance of 2,000 or 3,000 feet we were free from fog. To our surprise, at this elevation, more than 4 miles above the earth, there were dark masses of clouds, 2 layers one above another, with fringed edges, unmistakable nimbi, without doubt, clouds of rain. At 23,000 feet, Mr. Coxwell, who had been examining his ballast bags, decided that we must not only descend, but descend at once. To my great regret, I was therefore compelled to content myself with a searching look of general observation, but one momentary glance was sufficient to impress it forever on my mind, and were I an artist, the impression was so vivid that I could portray it in all its details. Above, below, all around, the sky was nearly covered with dark clouds of stratus character, with cirri above and faint blue sky between, not the blue of the morning or of a dry atmosphere, but as seen when the air is murky and the clouds confused. The sense of storm and adverse weather generally, which gave character to the scene, marked it forever as a memorable experience among many others. As we passed down on our descent, at a height of 14,000 feet, we encountered a snowstorm extending through nearly 5,000 feet. There were no flakes, only speculae and hexagonal crystals of distinct and well-known forms. Below the snow, and almost 10,000 feet from the earth, we entered again an opaque atmosphere, which continued till we reached the ground. This summer afternoon had exhibited many vicissitudes of weather and offered to the observer a fine and comprehensive study of meteorological influences at work, removed from the immediate surface of the earth. End of chapter 17.
Chapter 18 of The Ocean of Air, Meteorology for Beginners. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Ocean of Air, Meteorology for Beginners by Agnes GIBERNE. Chapter 18 Rain, Snow and Hail. Thus we see that a cloud, like a mist or fog, is pressed by a cold air current out of a warm one, to hang suspended as a countless multitude of minute floating water drops. Sometimes through a change of wind or temperature, these drops are drawn anew into the air, and the cloud vanishes. But sometimes they go on increasing. More and more vapor is turned into mist, and the cloud spreads over a wider and wider extent. Then the tiny drops get more and more crowded together, till they begin to run into one another, and so bigger drops are formed, which again join and make still larger ones. Now, though the air can hold up very tiny drops of water, it cannot for any length of time support large and heavy drops. Naturally, when they get beyond a certain size, they can be buoyed up no longer, but must fall to the ground at the shower of rain. It should, however, be understood that this certain size is by no means always the same size. Moving air can support a heavier weight than still air. A gale of wind could keep floating above us drops which a gentle breeze would have no power to hold up. This may help to explain the difference in the sizes of raindrops. There are often strong winds blowing in the higher regions of the atmosphere when we have a calm below. Sometimes the same thing is seen in a fog, which after all is merely a cloud resting on the ground. The tiny water drops become so abundant that they run together and form bigger drops, which fall to the ground like rain. But all this is a very partial explanation. There is much that is mysterious in the formation of raindrops, and other forces, such as electricity, have a hand in the matter. Rain, briefly, is caused as mist and fog are caused, by the meeting of two currents of air, one warm, one cold. The moisture of the warm air is condensed into a cloud, and in many cases rain follows. Rain is also caused by the rushing of warm lowland air up a mountainside. Some of the heaviest rains known in any part of the world are on mountains, especially on mountains which lie not far from the sea. The air over the ocean gets thoroughly soaked with vapor, which, while warm, it can well carry. Then suddenly it comes against the mountain range, and has to pour upward, losing heat as it does so. Becoming fast colder, it can no longer contain its supplies of hidden moisture. Then clouds of floating mist are formed, and torrents of rain are poured down. Air hurrying up a mountainside loses heat in two ways. The coldness of the mountain takes effect, chilling down the warm air. Also, in rising to a higher level, it expands, becomes more thin or rare, spreading out its particles over a larger space because of lessened pressure. This expansion of air, or of any gas, always means increase of coldness, heat being given out in the act of expansion. Increase of coldness means lessened power to carry moisture, which means nearer approach to saturation, and therefore increased dampness. Therefore, too, it means often heavy downfalls of rain. So no wonder high mountains in hot countries are often famous for the deluges with which they are favored. The amount of rain which falls in different places varies extremely. Taking all the year round, we have a moderately abundant supply in the British Isles, but nothing like what is known in tropical countries. The fall of rain in London, except on rare occasions, seldom exceeds an inch, measured by means of a rain gauge. A gallon of water weighs 10 pounds, and if spread out in a layer 1 inch thick will only cover an area of 2 square feet. An inch of rain gives 100 tons of water per acre, or 60,000 tons per square mile. Scott. End of footnote. In 24 hours, but in other places this amount is enormously increased. At Joyeux in France, 30 inches have been known to come down in less than 24 hours. If the whole amount which falls on the east coast of England during a year could be carefully collected on a level surface, no running away or sinking into the earth, or drying up being allowed, we should have at the year's end a layer of water about 20 inches in depth. If the same were done on the west coast of Ireland or Scotland, the supply of water at the year's end would be 6 or 8 feet deep. So even in the British Isles there is a very marked diversity between different places. But if this same course were followed at a certain hill station in India, named Cherrapunji, a much greater result would be obtained, in the shape of a large lake, at the very least between 30 and 40 feet in depth. Cherrapunji enjoys the far from delightful eminence of being one of the wettest spots on the face of the earth. Sometimes in cold weather we have snow instead of rain. Snow is not frozen rain. It falls directly as snow from snow clouds. In winter the frozen clouds lie at a much lower level than in summer. Snow clouds, like mist clouds, when they grow too heavy, have to part with some of their substance, which falls to the earth in white flakes instead of water drops. Much more than mere weight, however, is involved in the fall of snow. Snowflakes are made of the most exquisite ice crystals. The minute needles group themselves in beautiful star-like shapes, always six-pointed. Many substances, when changed from a liquid into a solid, will crystallize into delicate and beautiful forms, and it is notably so with water. When under free conditions, water freezes into snow. The snow crystals are always formed of six-pointed stars or plates. That it is so we can see with the microscope, but why it should be so we do not know. If very large flakes come down, they are caused by the union of smaller flakes. The drier the air, the smaller and harder will be, as a rule, the flakes, for they cannot stick together unless a little damp. Snow in England comes fitfully and seldom lasts long. Skaters have scarcely time to learn the use of their skates before the opportunity is gone. Yet even in England we have our exceptional winters of really hard frosts and deep snows. Towards the end of the 7th century, for instance, the Thames was completely frozen over for nearly 3 months, so that, according to an old chronicle, it became a small city, with booths, coffee-houses, taverns, glass-houses, printing, bull-baiting, shops of all sorts, and whole streets made on it. Food was scarce, prices rose, and the birds of the air died numerously. Another such winter seems to have recurred about 25 years later, and again after an interval of nearly 50 years, each differing from the others in details, but all alike in severity. In the present century the mightiest snowstorm yet known was that of December 1836. Many lives were lost, and business generally came to a standstill for nearly a week. The actual snowfall was said to be from 4 to 9 feet in depth, and snowdrifts were piled to a height of 20, 30, 40, even 50 feet. After all, the most excessive of English snowfalls are but a child's play, seen side by side with that awful visitation to which parts of America are subject, the blizzard. To constitute a true blizzard, writes Miss Gordon Cumming, the whole atmosphere must be full of the finest, most cutting ice dust, sharp as powdered glass, mingled with very small, three-cornered frozen snowflakes, driven with appalling swiftness by a rushing mighty wind, while a sudden fall of the temperature, from comparative warmth to 30 or 40 degrees below zero, produces an intensity of cold which is altogether unbearable, as we may well imagine who deem ourselves frozen should the thermometer fall 2 or 3 degrees below zero. The blast sweeps on with irresistible velocity, so densely charged with pulverized snow and ice, as fine as flour, that it obscures the air with what is described as white darkness, rendering large objects totally invisible at the distance of 2 or 3 yards, and accompanied by such a roaring and tumult that the human voice can scarcely make itself heard within a few feet. The luckless traveler who is caught in such a blast runs every risk of suffocation, the action of the lungs being stopped by the swiftness as well as the intense cold of the wind, while the ice dust, which penetrates the thickest clothing, is more choking than the sand of the simoon. Moreover, in the anguish of suffocation, the victims of the blizzard seem occasionally to become insane before dying, in some cases tearing off their clothes as if thus to gain relief. One of the worst blizzards ever known raged through several of the states on and after the 11th of January, 1888, an ice-laden hurricane awful in its power. Within 24 hours the temperature dropped from 74 degrees above to 28 below zero, and in a single hour blue sky was replaced by a wild storm of powdered snow. People were taken utterly unawares. Children died by the roadside on their way home from school. Farmers died in the fields before they could get to their houses. A woman stepping outside her front door to watch for her husband perished there and then, probably so numbed and bewildered as to have neither power nor sense to turn back. Some even under shelter succumbed to the overwhelming cold and were literally frozen to death, but the greater number, at least of those exposed to the blast, seem to have died of suffocation, fighting for breath, often baring their throats in the terrible struggle for air. Others again were found dead, stripped of their clothes, which lay scattered piecemeal, as if flung away one by one, under the influence of madness. Such dying madness in its victims is a well-known occasional feature of the blizzard. This great storm lasted unbroken for 60 hours, 3 long days and nights of horror, of white darkness, of a ceaseless hurricane roar, of fearful cold, of a stifling rush of ice and snow. After such an account, one can hardly say much about English winters. Another form of frozen water descending from the clouds is hail, and hail may fall in summer as well as winter. Hailstones are not made, like snowflakes, of delicate ice needles, but neither are they shapeless lumps of ice. If the formation of snowflakes is mysterious, the make of hailstones is not less so. They too are usually crystallized in beautiful shapes, so quite differently from snowflakes. The manner of crystallization is often so complicated as to render it almost impossible that they should have sprung into being instantaneously, or as the hailstones fell from the clouds. Probably each hailstone begins with the freezing of a drop of water through a sudden rush of ice-cold air. Round this central ice particle, other particles of ice form in succession, taking curious shapes according to certain laws of crystallization. All this must occupy time. It could hardly be accomplished in a single second, possibly not in many seconds. Yet how heavy growing hailstones, not light and feathery like snowflakes, but solid and firm, can be borne up in the air while their formation goes on, is no easy problem. In a high wind, doubtless, they could be carried aloft much longer than in still weather, and hail is usually accompanied by a gale. Moving air, as already said, in connection with raindrops, can bear a far heavier weight than air in repose. Still, there is much in the story of hailstones which we are as yet unable to explain. Hailstones as large as peas are common, and they have been known to fall in Britain fully the size of marbles. In the Orkneys, they have been picked up big enough to rival a goose egg, and even this has been exceeded elsewhere, though many stories of Brobdingnagian hailstones might be dismissed as mythical. The true individual crystallized hailstone is never very big. When great stones fall, they are merely rough masses of small stones glued together in the course of their descent by natural stickiness, probably resulting from some degree of damp. One of the heaviest falls of hail ever known in England was during the thunderstorm of August 9, 1843. It was exceedingly violent in the neighbourhood of Cambridge, and scarcely less so in Oxfordshire. An extraordinary darkness of the atmosphere, with clouds hanging so low as almost to rest upon the housetops, dazzling flashes of lightning, and one long continued unceasing roar of thunder, were enough in themselves to be impressive, but to them was added a deluge of hailstones, which lasted more than 20 minutes. The scene, wrote Mr. Glacier afterward, was positively terrific, and the fright of many of the inhabitants of the town (Cambridge) was in no small degree increased by the crash of broken windows and the inundation of their houses. During the whole of this time, it was impossible for the eye to penetrate many yards through the storm. The hail fell with such wonderful closeness, and there was such a peculiar mistiness rising from the earth, that a complete barrier was opposed to the power of vision. We are almost afraid to speak of the size of the hailstones, or rather blocks of ice, but we are certainly not exaggerating in the least degree when we say that very many of them were as large as ordinary walnuts. Some indeed far exceeded this size. One that was picked up measured 3½ inches in circumference, and several have been described to us as being about as big as a pullet's egg. 3 hours after the storm was over, unmelted hailstones lay in piles. One gentleman, finding his horse unable to pull the carriage through them, stepped out to clear a way, and sank up to his knees. In Cambridge alone, where the brunt of the storm fell, damage was done to at least the extent of £25,000. Glass was shivered, window frames were dashed in, fruit was cut up, birds were killed, crops were utterly destroyed. In a single half-hour the standing corn was stripped, laid flat, and literally cut up into little pieces. Nothing of it remained for use. Well for us that such outbursts are rare in England. While on the subject of ice, a passing mention may be made of frozen waterfalls, often seen in other countries, though not so common in England. The mere fact of a severe frost over the plains does not ensure the freezing of waterfalls upon the higher ground. They usually occupy sheltered spots where the radiation of heat from the earth is less rapid than elsewhere, and a slight or short frost has little power to chain the falling water. But if the frost is severe and lasts long enough, especially if it is accompanied by a dry and bitter wind, the stream is at length more or less mastered. First, the spray at the bottom hardens into a snow-like mass. Then the trickling water on either side becomes solid. Each straggling drop is turned to ice where it rests, and fantastic forms grow slowly into shape, including hollow icicles through which the ice-cold water still flows. Some of the great Norway waterfalls gain such a mass of frozen spray below in the course of the winter that summer cannot entirely do away with it. Even in England we see something of this. The Hordrow Force in Wensleydale, a waterfall 100 feet high, built up in 1881 a cone of ice at its base, no less than 30 feet high, the entire waterfall being that winter frozen for the first time since 1740. End of chapter 18. Chapter 19 of The Ocean of Air, Meteorology for Beginners. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Ocean of Air, Meteorology for Beginners by Agnes GIBERNE. Chapter 19 The Nature of Wind. The ocean of air in which we live is never at rest. Stagnation of our atmosphere is a thing unknown. Streams of air particles flow hither and thither, forming winds from the north and east, winds from the west and south, winds from every intervening point. Some are variable hour by hour, some are changeless for months, some are hundreds of miles in extent, some may be measured by yards. There are great rivers of air, as well as tiny brooks of air, in the air ocean, just as there are vast streams, besides little currents, in the water ocean. Our next step is to think about the various movements of air, commonly called wind, those movements which altogether make up the worldwide circulation of the atmosphere. In some parts of the south and east of England, one may almost any day note the act of wind in turning the sails of a windmill. A pyramid-shaped tower has a large light structure fastened to one side, formed of 4 huge spreading arms or sails, each some 30 or 40 feet in length. Small crossbars partly fill up the skeleton shapes of these sails, and more or less of a canvas covering overspreads the crossbars. The sails are set at such an angle or slope that when the wind blows against them, they move round under its pressure, and thus work the grinding mill within. The action of the wind upon a windmill sail is much the same as upon the sail of a boat, a kind of slanting push, sending it onward. Wind is nothing more nor less than moving air. But why should air move? Why should not the whole ocean of air remain at rest? We can picture to ourselves a great ocean of air in perpetual sublime repose, a world without winds, an atmosphere without circulation. Such a world with such a belt of air might not impossibly exist under certain conditions, but it would have to be a very different world from ours, a reposeful, not to say stagnant world, not spinning upon its axis day and night. It would have to be a world without varieties of heat and cold, of climate and weather. The moment one part of the atmosphere is warmer than another part, a disturbing element comes in, and the air begins to stir. Wind commonly springs from what is called difference of pressure. If in one place the air is warm and light, in another cold and heavy, the heavier air must always flow towards the lighter air to keep up the balance of the atmosphere. Just as water always moves to preserve a level surface, so air always moves to preserve an even balance. Moreover, one current of air always causes other currents. That is a fact worth remembering. Everything that happens in nature, as well as in our lives, is always caused by other things going before, and always helps to cause other things coming after. No one thing in nature or in life stands alone, uncaused and uncausing. A current springs from different causes, but once set going it is certain to cause other currents. So even if we had an ocean of stagnant air to start with, it could not remain stagnant so long as a single disturbing element was there to upset its balance. Each slight disturbance would draw countless other disturbances in its train. Moving bodies in the air ocean are one sort of disturbance, and a very frequent source. We are not commonly conscious of this. Not a hand can move, not a sparrow can fly, without causing air pressure and consequent little air breezes. But the fact does not become apparent to us unless the moving body is large, the compression of air tolerably great, and the wind resulting somewhat strong. We all know from experience what a wind is caused by the rush of an express train through a station when we are standing on the platform. Dust and sticks are carried along by the whirl of moving air. The same thing is seen on a much greater scale with an avalanche. Avalanches are of different kinds. Sometimes in summer, on the higher mountains, they consist of solid blocks of ice, dashing down steep slopes. In spring, they are more usually huge masses of soft coherent snow, gliding downward with frightful rapidity, and overwhelming whole villages in the valleys below. Another kind, quite as dangerous, is the drift avalanche of winter. It consists of loose, dry, powdery snow, first set going perhaps by a strong wind. In the descent it gathers volume and speed, leaping from precipice to precipice, till the tremendous compression of air caused by its downward rush sets in motion a far more violent gale than that which began its own career. The mere wind from such an avalanche has not only lifted a strong man bodily from a ledge and borne him some distance, but has levelled trees and shattered whole houses with its hurricane blast. A mighty snow mass will often break loose from some frowning snow ridge above, and will dash downward, leaping from ridge to ridge of a great precipice. At the first concussion, the whole mass is broken into fragments, and soon only a cloud of white dust is seen, to flash like lightning from point to point, roar following roar, till the last leap is taken. Woe betide any human being so unfortunate as to stand in the path of such an avalanche, or within reach of its rushing wind. But to come back to a very everyday matter, what is it that causes an ordinary draught in a room or public building? The draughts in St. Paul's Cathedral are pretty well known to Londoners. If no disturbing elements existed, the mass of air within our great cathedral might remain calm and moveless. But this is a state of things seldom, if ever possible, certainly never possible, when a crowd of human beings is gathered under the dome. The heat given out by their bodies, and the hot air pouring from their lungs, warms the atmosphere in and near the center. Then the warmed air rises, and streams of cold air pour centerwards from the side aisles to supply the place of that which passes upwards. Thus a draught is created, and old ladies draw their shawls tightly round them, and old gentlemen cast savage looks at the vergers. But neither old ladies nor old gentlemen blame themselves as being in part the physical cause. It often happens that on the sea-coast, especially in hot countries, land and sea breezes regularly alternate. All day long a fresh breeze from the sea will blow in upon the land. In the evenings that will stop, and after a pause a land breeze will for hours blow steadily out to sea. In the morning another pause is followed again by the sea breeze. The direct cause of these breezes is the rapid heating and cooling of the ground. Land grows warm much faster than water, and also loses its warmth much faster. Water heats slowly, and once heated it cools slowly. All day the ground becomes warmer and warmer under the burning sun, and helps to heat the layers of air above. The cooler and heavier sea air has to flow in upon the warm and light land air. After sundown the reverse happens. The ground cools fast, helping to cool the air above, while the sea keeps warm. The air over the land, becoming the coldest and heaviest, has to flow towards the more warm and light air over the water. Some explain this by saying that the cold air flows towards the warm air, because the latter, being light, has a tendency to rise and to leave a space which must be filled. Another explanation is as follows. The warm air is enlarged by heat, and expands or swells upward, rising like a blister on the outer surface of the air ocean. The upper layers of air, being piled too high, have to slide away to a lower level over the colder air. Then the added weight and pressure over this colder region forces the air below to flow towards the region of warm and light air. It is in fact a readjustment of the balance. All around the earth, near the equator, are hot countries, lands when the sun beats fiercely down, warming soil, sea, and atmosphere. This causes on a large scale what has just been described on a small scale. The air, being peculiarly laden with moisture in those regions, is peculiarly susceptible to the heat of the sun. Vast masses of air, already warm, are more and more heated by the sun's rays and by the burning earth below, till they are far lighter and larger than air elsewhere. Then the cooler, heavier, smaller air comes pouring in from north and south to restore the balance of the atmosphere. I use the words larger and smaller with purpose, for literally the air of lower levels does expand or grow bigger with heat, and does shrink or grow smaller with cold. A mass of heated air weighing 1 pound is as truly larger than a mass of cold air weighing 1 pound, as 1 pound of heated iron is bigger than 1 pound of cold iron. The air in the tropics near the equator grows hot, expands, gets large and light. This means that the mass of the atmosphere thereabouts occupies more space than if cold, its particles being more widely separated. The result, if we could see it, is doubtless an actual swelling upward of the outer surface of the air ocean, the rising of a huge blister or air wave pushed outward by the enlarging of the air below. Now the air ocean, like the water ocean, flows hither and thither in a perpetual struggle to keep itself even. Like the water ocean, it might surge out at its upper surface. Footnote. The word surface is of course used with a reservation. The atmosphere probably thins away so gradually that no man, if able to examine for himself, would be able to say where it ceased. But since the air-ocean does not extend through space, it must stop somewhere. End of footnote. In great waves. But those waves are sure to fall back and flatten themselves out. The superfluous air, piling itself above, has to flow away in mighty currents towards the north and south. As these streams pour off, they cause extra weight and pressure where they go, and other currents pour in below, just as we saw was the case in St. Paul's Cathedral. We may be quite sure of one thing in the matter of air circulation. Whatever quantity of air flows towards one particular place, the same quantity of air must flow away from that place. Also, whatever quantity of air flows away from one particular place, the same quantity of air must flow towards that place. No part of earth can be left with less air or more air than any other part. So a perpetual struggle to make things equal is carried on over the whole world, air rushing hither and thither in streams to restore the balance, which, as soon as it is restored, is directly upset anew. All round the earth, to the north of the equator, except where disturbed by other influences, lies a broad belt of winds, always blowing towards the equator from the northeast, known as the trade winds. The belt reaches from near the equator to about 30 degrees north latitude, and the streams of air continue day and night, night and day, with more or less intensity throughout the year. Exactly the same kind of trade wind belt is found also to the south of the equator, only as these winds too blow towards the equator, they come from the southeast. The northern belt is known as the zone of the northeast trades, and the southern belt as the zone of the southeast trades. In bygone years, the trades were a great perplexity to sailors, and often a serious difficulty. It was all very well so long as a ship wanted to sail in the direction whither the trade blew. The mariner might lash his helm and go to sleep if he chose, leaving the lookout to a girl or a child, for a long run through the open sea. He could be absolutely secure of a good fresh breeze, always from the same point, never ceasing and never growing too strong. But if we wished to sail in the teeth of the trade, that was another matter. Wishing for a change of wind was useless work, for the wind never did change. Now that men understand the extent and limits of the trades, knowing where they are constant, where they change with the season, and where land influences check or draw them aside, the sailor can make use of or avoid the trades as he will. Moreover, the widespread use of steam makes the direction of winds a less vitally important matter than of old, in a large proportion of cases. End of chapter 19.
Chapter 20 of the Ocean of Air, Meteorology for Beginners. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by John Brandon. The Ocean of Air, Meteorology for Beginners by Agnes GIBERNE. Chapter 20. The Circulation of Air. All round the world, on and near the equator, lies a remarkable band of calm air. The northern trades meet there the southern trades, and each tends to counteract the other. The belt of calms known as the doldrums has to be passed by every ship going from one hemisphere to the other. Sailing vessels have often been kept there for weeks, unable to advance, like that of the ancient mariner, as idle as a painted ship upon a painted ocean. In olden days, before steam power was known, passengers to Australia or South America were often long delayed. Though wind is scant, rain is abundant, sometimes to a tremendous extent. Old sailors tell of such deluges, combined with dead calms, that fresh water has absolutely been ladled up from the surface of the still ocean. The trade wind belts have been already described as currents of air pouring constantly from north and south towards the equator. These are on the surface of Earth, low down in the ocean of air. High up in the atmosphere, above the trades, are two exactly opposite currents of air, known as anti-trades, pouring away from the equator towards the north and south. They, too, have been mentioned earlier as the result of the heated air over the equator. As there are upper and undercurrents of water in the ocean, so there are upper and undercurrents of air in the atmosphere. The wind may blow where we stand straight from the north, but there is no proof that higher up the wind does not blow direct from the south. Careful watching of clouds shows often that the upper layers are traveling in a perfectly different direction from the lower layers. Before a thunderstorm, when attention is drawn to the sky, we often hear it remarked that the cloud has come up against the wind. The cloud has, of course, done nothing of the kind. A cloud can no more float in the air against the wind than a log of wood can float in a river against the stream. The cloud is merely borne towards us by a different current of air from that which at the moment we feel. The same fact of differing air currents, though less sharply marked than in stormy weather, may be seen on many a fine and breezy day, but people do not commonly observe. The anti-trades lie very high up, so high that no mountain climber has walked out of the lower trades into the anti-trades. Towards the outer verge of the trade belt, however, the anti-trades are found descending to lower levels, and even without this there are abundant proofs of their existence. Beyond the trade belts, to north and south, lie two more so-called calm belts. That to the south is named sometimes the calms of Capricorn, that to the north the calms of Cancer. Some know the latter as the horse latitudes. A very obvious connection exists between seahorses, mares' tails, and high winds, which is rather at variance with one's notions of calmness. The Cancer calms are, however, of a most variable nature, much broken by severe gales and heavy storms. There is a marked difference between the calm belt of the equator and the two calm belts of the tropics. The calm belt of the equator has incessant currents of air pouring in below from north and south, while incessant currents of air flow away above. So the tendency of air there must be to rise steadily upward. In the so-called calms of Cancer and Capricorn, regions really of unsettled winds and violent storms, alternating with wearisome calms, things are just the other way. Streams of air pour in above from north and south, while streams below flow out towards north and south. So the tendency of the air there must be to sink steadily downward, causing pressure from above, which indeed has been noted as markedly shown by the barometer. There is also a considerable difference in the condition of air currents flowing from the equator to north and south, and air currents flowing from north or south to the equator. The equator is the largest circle of latitude, and all other such circles from the equator to the poles grow smaller and smaller. If a current of air pours from the North Pole to the equator, it runs in an ever-widening bed. This may be seen by following the course of two longitude lines on the globe, beginning at the pole and ending at the equator. But an air current traveling the other way moves in an ever-narrowing bed. In the first case, it can spread itself out. In the second, it has less and less room. Regions north of the Cancer calm and south of the Capricorn calm are no longer characterized by such persistent winds as the trades and anti-trades. Still, the great circulation of the atmosphere goes on, only in a more irregular mode, and even there something of a rough plan may still be detected. The winds of the region between the horse latitudes and the North Pole may seem to wander here and there, without aim or rule, yet on the whole there is a general tendency of air currents below to flow towards the pole, and of air currents above to flow away from the pole. In the northern hemisphere these winds have little fair play, being constantly interfered with by the rapid heating and cooling of great continents. But in the southern hemisphere, when much ocean and little land are found, westerly winds, circling around and towards the South Pole, have full swing. Not only are they almost as persistent as the trades, but far stronger, becoming at times so violent as to have gained for that region the expressive cognomen of the Roaring Forties. These winds are westerly, not as one might expect southerly and northerly. They do not travel towards the poles from due south and due north, but rather from a westerly direction. One reason for this is not hard to find. If the whole surrounding atmosphere poured straight in upon either pole, the piling up of air above the poles would be tremendous. A general influx of air from all sides could scarcely be balanced by any amount of flowing away above. Such a state of things is not possible. The winds nearing the poles must with lessening space play round and about, must approach rather by circling than by direct lines, each air current fitting in as it can with other currents. Another reason for these westering gales of low latitudes is connected with the daily whirl of our Earth upon its axis. In an earlier chapter we saw how the atmosphere revolves with the Earth from west to east, each part of it at the same speed as the ground on which it rests. We saw how the air at the equator has a steady speed of 1,000 miles or so an hour, while at the poles it scarcely moves at all, and all the way between the poles and the equator it moves, like the ground, at different rates. Now, when air comes from the north towards the equator, it partakes of the slow northern whirl, and as the earth below rushes faster and faster, it lags behind, seeming to come not from the north, but from the northeast. When, on the contrary, air flows from the equator towards the north, it partakes of the rapid tropical whirl, and as the ground beneath moves more and more slowly, it outraces the earth, appearing to come not from the south, but from the southwest. Thus the trades blowing equatorwards, which would be northerly winds, become northeasterly, and those winds blowing polewards, which would be southerly, become westerly. We have now some idea of what may be called the rough draft or general outline of atmospheric circulation. Briefly, it is as follows. 1. A belt of calms on and near the equator, winds flowing in below and flowing out above. 2. On either side, a belt of steady winds, the trades below flowing towards the equator, the anti-trades above, flowing away from the equator. 3. Outside the trade belts, to the north a belt of Cancer calms, to the south a belt of Capricorn calms. The winds in both cases flowing in above from north and south, flowing out below towards north and south. 4. Beyond the calms of Cancer to the north and beyond the calms of Capricorn to the south, a belt of variable winds, below more or less westerly and tending towards the pole, above tending away from the pole. 5. At the North Pole and at the South Pole, a region of comparative calm, winds mainly flowing in below and flowing out above. Thus a continuous circulation of air is kept up over the whole earth. No part of the atmosphere is ever at rest, but a perpetual interchange of air currents goes on everywhere. One may in imagination follow the progress of an air particle, starting from the equator and performing the grand tour. At the equator it rises upward into higher regions of the atmosphere. As part of an anti-trade, it journeys northward, passing over the contrary blowing trade below. In the calms of Cancer, it descends to earth, plays about in a storm or two, and takes its choice between joining the stream of air which at once returns to the equator and joining the stream of air which more fitfully finds its way towards the North Pole. Having been carried away by the latter, this wandering particle is borne to and fro by many breezes, visiting divers countries, yet on the whole progressing northward. Reaching at length the neighborhood of the pole, the particle finds itself in another region of comparative calm, though by no means a region where storms are unknown. Rising upward, after a while, it joins a high-level current of air proceeding southward, an infant trade wind, in fact, though hardly yet to be recognized as such. Gaining once more the calms of Cancer, it descends anew, and this time passes out below to the southward as a part of the northeast trade. At the equator again, the particle works its way upward as before, and joins the upper current flowing southward as part of an anti-trade. Reaching the calms of Capricorn, it descends, passes thence below through the roaring forties, towards the south polar calm, finds an upward path there to the outflowing currents above, returns to Capricorn, descends afresh, joins the southeast trade, and reaches the equator, ready to begin the round anew. This circle of possible movements for a single air particle might be almost infinitely varied by permitting it to join any of the innumerable side currents and eddies of air caused by countless land influences. It should become part of a monsoon here, part of a hurricane there. It should unite itself to a cyclone in one place, to an anticyclone in another. Though the broad outlines of atmospheric circulation may be sketched with a certain regularity, the variations upon that rough plan are past counting. In the air circulation of Earth, As in the blood circulation of a man's body, there are little arteries as well as great arteries, and hundreds of tiny streams for every big stream. The wind goeth towards the south, and turneth about unto the north. It whirleth about continually, and the wind returneth again according to his circuits. What I have tried to explain in many paragraphs is given thus in 25 words of Holy Writ, the circulation of air described in a nutshell. End of chapter 20. Recording by John Brandon.
Chapter 21 of The Ocean of Air, Meteorology for Beginners. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recorded by David Bear. The Ocean of Air, Meteorology for Beginners by Agnes GIBERNE. Chapter 21. More about the wild winds. In the circulation sketch of the last chapter, showing how the air of the atmosphere flows ceaselessly to and fro over the whole face of the earth, the two halves of the earth were coupled together. Not wrongly so, for the bare outline of the general plan is the same to north and south of the equator. Still, one half of the world is very far from being the exact copy of the other half. Exact copies are common enough in human works, but not at all common in divine handiwork. There we have infinite variety, filling up systematic outlines. Since no two leaves of a tree have ever been found absolutely the same in form, it is, to say the least, improbable that one half of the world should be a slavish imitation of the other half. If the entire earth were covered by one enormous ocean of water, then indeed such a system of winds might be carried out in all of its parts, with little or no variation. The circulation of the atmosphere would be in that case less difficult to understand and less interesting to study than it is now. But our world contains much land as well as much sea, and where land exists, the rapid heating and cooling of it causes great varieties of air currents breaking through general plans to any extent. Broad belts of trade winds have been described enfolding the earth like sashes. These trade winds do exist, and they would exist all around the world throughout the whole year if not hindered, but in places they are very much hindered. Suppose, for instance, a burning desert not far from a trade wind region. The air above the desert becomes in the summer months tremendously heated, swelling in size and flowing upward. Then arises a need for heavier air to flow in from somewhere else towards the desert, to restore the lost balance of the atmosphere. The trade wind lies conveniently near, and it is of no use to protest that the said trade is wanted near the equator. Here is the most pressing need for the moment, so the busy trade is bent out of its regular course to become a sea breeze blowing inland, and the needs of the equator have to be supplied from some other quarter. Such needs are always supplied. The balance of the air must be kept. If the steady ordinary winds are not equal to their task, a hurricane or two will intervene, doing in a very short time the work required. Land influences of this kind so often divert the trades that they can only be said to hold full sway over broad reaches of ocean, not usually upon continents. Monsoons in general are merely turned or deflected trades, drawn over by overheated land from their proper route. The Indian monsoon is a familiar phrase to most English people, at least to those who have relatives in India. It is commonly applied to the soft southwest monsoon, which brings the heavy rainy season. Footnote: 2 monsoons blow regularly in India, taking turns. The southwest monsoon lasts about 5 months, from May to October. Northeast about another 5 months, between October and May, each being divided from the other by an irregular month called the breaking of the monsoon, during which violent storms and even hurricanes often take place in the struggle of the disturbed atmosphere to regain its lost balance. End footnote. Here is a little description of the rainy season, written by one on the spot, which helps bring it before our imagination. Footnote: Mrs. Murray Mitchell's In India. End footnote. I wish you could see how it rains. For 11 whole days it has come down incessantly, and the compound is like a lake. People are beginning to grumble, but I like it. The air is so much fresher and pleasanter, and one feels so much more alive than in the terrible heat which preceded this downpour. And then again in August, nearly 2 months later. The rain is most preserving. It comes down not in ordinary drops, but in sheets of water. The whole place is ankle deep, and I have just been watching the servants wading through the slush with their queer little wooden umbrellas over their heads, bringing in the dishes for breakfast. All Indian kitchens, you know, are at a little distance from the house. Everything is damp and disagreeable and mouldy. It is quite an occupation to look after one's books and clothes, and after all, no care avails to save them. The books would break your heart. Their faces, so fresh and fair when we left home, are spotted and spoiled. The very pillows smell as if they've come out of a charnel house. The gloves you wear today are white with mold tomorrow. Your boots the same, and your very hair seems mildewed. Nature, just now, is wildly luxuriant and beautiful. The effect, of course, of the bountiful monsoon. The woods are full of rich loveliness. The very ditches are turned into beds of beauty, covered thick with beautiful caladium leaves, blotched and streaked with crimson, purple, and brown. Now the southwest monsoon is nothing more or less than the northeast trade of that region, completely turned or doubled back upon itself and made to flow in steady currents over India. But what of the northeast monsoon, which flows during the winter months of the north? Why, that is only our old friend, the northeast trade, unchanged. When the influence of the desert lessens through cooler weather, the trade returns to its natural course, and flows once more towards the equator. Footnote. The world has other monsoons besides those of India. There are African monsoons, caused by the great African deserts drawing aside part of the Atlantic trade, and there are Central American monsoons, formed out of deflected Pacific trades. End footnote. Perhaps the force of moving air is shown in no more marked way than in its lashing of the ocean surface into mighty waves. Even when standing on the shore, one may gain some idea of the tremendous power of ocean waves, lifted and driven onward entirely by the pressure of the gentle transparent air, which floats so sleepily around us on a quiet summer's day. Without an ocean of air, the ocean of water would be waveless. As good a view as any of ocean billows, seen from the safe vantage of firm ground, may be obtained on the Chesil Beach, a long reach of shingle extending between Portland and the mainland, some 10 miles in length and rising up to a piled shingle height of about 60 feet. If a strong wind blows from the Atlantic straight up the ridge, a curious contrast can be seen by one standing on the summit. Within, the bay between Weymouth and Portland lies calm and blue, still as a lake, broken only by ripples. Without, beyond Chesil Beach, a boiling sea of great waves heaves wildly, and one monster billow after another, 20 feet or more in height, reaching far along the line of shingle, rolls fiercely up, curls grandly over, and falls with a deafening crash, sending forth a rush of foam and spray, grinding pebbles together and tossing them about like sand. No human being could live beneath the crushing weight of one of those waves. The noise is so deafening, even in a moderate gale, that I have tried in vain to hear words shouted in vigorous masculine tones close at my side. In a storm, so mighty is the turmoil, that a small brig has actually been lifted by the sea, carried over the top of the ridge, and landed on the shingle slope beyond, whence a way was made for it later into the quiet bay. The action of the wind upon the ocean surface varies much in different places. A greater contrast could hardly be found than between the vast majestic rollers of the Atlantic, a quarter of a mile or more apart, traveling in slow succession, and the broken chopping waves of the Channel, dashing into and over one another with impatient and undignified restlessness. Again, one may turn from the stately water hills of the sea, off the Cape of Good Hope, 40 feet or more from crown to hollow, calm in motion and deep blue in hue, to the wild perilous turmoil of the North Sea. One or two quoted descriptions of the latter will speak more forcibly than any words of mine can do, as to the awful power of the wind over the ocean, and of the ocean over aught that lies in its grasp. The grey, fitful waves roll over the Dogger, and the steady, shrill wind is lulled but seldom. The sea does not run true, and sometimes after a succession of glossy rollers has travelled westward, there comes a furious northerly drift, which is met by a swift, whirling currents from the south. The charging waves meet in thunder. The rearmost seas climb in foaming piles over the shattered bulge of those that reel back from the onset. And the wild hurly-burly lasts until the strong set of the westerly roll masters the leaping cross-drift, and then once more the grey sliding procession moves inexorably shoreward. In December 1883, there was another storm that will soon not be forgotten. To say there was a heavy sea expresses nothing. That tremendous convulsion passes the power of descriptive words. A powerful steam carrier was hit by one unlucky sea, which not only burst her, but shivered her into tiny scraps. Strong wire ropes were snapped like worsted. Wire stays which held tore up great lumps of the bulwarks, and the amazing force of the sea was shown by the fact that the wood of the torn bulwarks was cut as cleanly as if a huge knife had shorn through. Yarmouth, Lowestoft, and Grimsby harbours looked as if they'd been under heavy shell fire for many days after the gale. Hardly a boat escaped without serious damage, and the wonder is that any of the fleet got home. Footnote: J. Runciman. End footnote. And again, from the same pen. The wind met one like a solid body, and its savage storming call stunned the nerves. It piled up a sea much worse than several I have seen when a perfect hurricane was blowing. Then the run of the sea was crossed-grain, and when 2 or 3 charging currents met, they reared up into a hill that fell away like a waterspout. Finding that it was impossible to see anything save a dark flurry of tortured water, or to hear anything save the numbing thunder of the gale, I tried to snatch some sleep, but it was a hopeless attempt. The vessel was riding beautifully. Sometimes, when it seemed as if she must actually fall off the side of the sea, she sidled prettily up the flank of the gloomy, threatening mountain, topped it like a bird, and swept down the rushing slope without so much as shipping a splash of spray. Harder and harder the wind blew. The rearmost waves strove to climb over the front ranks. The blown spray cut like sharp lashes, and the ugly hills that were veiled by that cruel drift made bellowing sounds as they rushed on their sliding basins. Imagine the Brighton Downs magnified. Imagine also the surface of the downs covered by tumbling hillocks, and then imagine 2 or 3 of the bluffs of the downs terraced one above the other, and you have an image of such proportions of that sea as the eye could take it in at one view. The bright strength and speed of the torn rollers were splendid, but I felt a rage in my heart as I thought that those beautiful, awful waves might kill some of the poor fellows who had been sent out in rickety, ill-found vessels. Such word-painting as this makes even a landsman able to faintly realize what it is to be out on the North Sea when the winds are in their rougher moods. But to learn the uttermost strength of the soft air, to lift and wreathe the ocean's surface into death-dealing waves, we must go to the tropics. On the 31st of October, 1876, more than 1 million human beings, natives of India, lay quietly down to sleep on certain flat lands about the mouth of the Ganges, after it is joined by the Brahmaputra, and on certain low-lying islands at its mouth. The islands are built out of the soil which is constantly carried down by those 2 great rivers. The people counted themselves safe that night, safe as usual. No particular fears troubled them. They knew that these low, unprotected lands were subject now and then to sudden inundation from storm waves, lashed up by a circular hurricane on the ocean, and brought to their shores. But such catastrophes were only occasional. They had taken precautions. They had built their little huts on platforms or mounds of earth some 3 feet in height, and they had counted themselves fairly secure. At 10 o'clock a storm raged, but without any unusual features, one of the ordinary cyclonic storms of the tropics. But at the hour of midnight came an awful warning cry, passed on from man to man, and overtaken by the hurrying foe. "The water is upon us!" One cyclone wave after another, drawn up at sea in the whirlwind center, was launched ruthlessly by the fierce gale over the islands and the low-lying mainland. The rushing tide bore all before it. No less than 3,000 square miles of country lay soon under water from 10 to 20 feet at least in depth. Little use were the hut platforms against this mighty incursion. Thousands of inhabitants died at once, died in their sleep, or woke up to a moment's agony before they perished. Some climbed the trees near their huts, others were flung by the rough billows into the branches. Some floated on the roofs of their huts, torn away from the mud walls, and others clung to the logs of wood, but too many of these were carried hopelessly out to the sea. The flood did not last long. By morning it was subsiding, and by noon the unhappy refugees in treetops could descend. But wind and wave had done too surely their fearful work. 215,000 human beings were destroyed in 1/2 hour by a single fell swoop of the elements. End of chapter 21.
Chapter 22 of the Ocean of Air, Meteorology for Beginners. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Elizabeth Miles. The Ocean of Air, Meteorology for Beginners by Agnes GIBERNE, The Great Water Circulation. It is hardly possible to gain a clear idea of water circulation generally without a few words first on the subject of ocean circulation. These two fluids, air and water, are intimately bound together, so intimately that neither can be long viewed without some reference to the other. The two oceans, that of air and that of water, are to a very great extent governed by the same laws, far more so than we, living at the bottom of the air ocean, would naturally suppose. Water, as water, wherever it may be, always strives to keep its own level, to present a perfectly even upper surface. Whether a mass of water be large or small, it can never remain at rest with one part of its surface higher than another part. A stream immediately flows from the upper to the lower surface to restore the lost level. This is much the same as we have seen in the ocean of air. True, we do not talk of a gas or a portion of air keeping its level, since a gas can spread out equally well in all directions. But when we consider the ocean of air as a whole, we find it following almost the identical rules of an ocean of water. The manner in which it flows to and fro to preserve above what may perhaps be called a level surface, at all events to arrange that equal quantities and weights of air shall be over all parts of Earth's surface, has already been explained. Another rule is common to the two oceans. We have seen in the circulation of air how every current of air makes needful a second or countercurrent. It is the same in the circulation of ocean waters. Every current of water flowing one way makes needful a second current the other way. Just so much water as passes from the north to the south must also pass from the south to the north. Just so much water as pours towards the equator must also pour away from the equator. If not, all ocean waters would gradually collect in a vast heap upon one part of the ocean bed, while other parts would be left dry. Many causes combine to keep the ocean in ceaseless unrest. Winds blow over its surface from all quarters of the compass, bearing the surface waters with them. Unequal heating of one part and another, causing some waters to expand and grow light, while others remain cold and heavy, is a fruitful source of currents. Vast quantities of water are daily drawn up by the sun into the atmosphere from one place to be poured down in another, thus further disturbing ocean's balance. Mighty rivers rush from the land, each making fresh readjustment needful. The tides sweep to and fro day after day, stirring up the great expanse anew. Such and countless other disturbing forces render a petrified and changeless ocean impossible. He causeth his wind to blow, and the waters flow. These are words written very long ago, yet true now as then. The power of winds to produce currents in the ocean has been often questioned, but there can be no doubt that such persistent winds as the trades have great influence in causing steady and continuous surface drifts. Each of the 5 chief oceans has its own separate circulation, the entire mass of water moving slowly round in an enormous eddy before going on elsewhere. A most weighty part in the Atlantic eddy is played by the Gulf Stream. It seems strange to think of an actual river in the ocean, yet many such exist. The Gulf Stream is an actual river of warm water, flowing northward out of the tropics upon a bed of cold water with cold water banks. The distinction between the warm Gulf Stream waters and the cold ocean waters is so sharp that a ship may lie across, half in the stream, half in the ocean, the line of separation being plainly seen. The Gulf Stream waters are not only much warmer, but much salter, and therefore of a much deeper blue than the ocean waters. If water gained and lost heat as quickly as land does, the Gulf Stream would be of very little use to us in the British Isles, but happily it is not so. The thick underlying cushion of cold water keeps the Gulf Stream from the ground, which would fast steal its warmth, and so it pours onto British shores, holding still a good deal of its tropical heat. On first leaving the Gulf of Mexico, the stream is about 30 miles wide and moves at the rate of 360 feet each hour. By the time it has wandered as far north as Newfoundland, it is over 300 miles in breadth and moves much more slowly, yet it is still distinct from the ocean. We may see in the Gulf Stream a remarkable illustration of that enlarging, which was spoken of a little earlier in connection with heated air over a desert and over the tropics. The waters of the ocean river, being much warmer than the waters of the ocean around, expand or swell outwards. The central line of the Gulf Stream off Hatteras stands about 2 feet higher than the ocean level, partly indeed from rapid motion between confining banks, but partly also from the increased bulk of the heated water. In consequence of this, perpetual surface streams pour from the top to either side. Colder and heavier waters find their way in below, and the Gulf Stream is gradually forced upward, the stream flowing in a bed which steadily widens and grows more shallow. The swelling of the heated water, the 2 outflowing surface streams above, and the 2 inflowing cold currents below seem to be on a smaller scale, very much the same that we have seen to take place in the ocean of air over the equator, resulting in trades and anti-trades. So distinctly does the surface slant downward to either side that floating seaweed and driftwood are known never to find their way across the Gulf Stream. They cannot do so, for they would have to climb a hill and ridge of water. All the rivers run into the sea, yet the sea is not full. Unto the place from whence the rivers come, thither they return again. That is precisely what happens. All the rivers, speaking generally, run into the sea. With the exception of the Jordan flowing into an inland sea and a few like instances, all rivers find their way not only into the sea of any particular country, but into the sea, the great ocean. Yet the sea is not full. The ocean waters are under restraint. They do not rise up to swamp and overpower the lands, as probably they might if all the water that exists in earth and air found its way to the ocean and remained there. But from whence the rivers come, thither they return again. Where do the rivers come from? In a great measure from hilltops and mountain ranges. Water collects on high lands, falling from the clouds, draining from snowfields. It pours downward in streams, which, joined by other streams, grow into torrents and swell into rivers, running into the sea. What next? These rivers return. How and where? They become part of the ocean first. The water particles which formed the rivers on land now flow to and fro in ocean currents. For a while, perhaps, they are far down in ocean's depths, away from sunlight. Sooner or later, they find their way towards the surface. By and by, while there, exposed to the sun's heat, they pass upward into the air as invisible vapor. Then the air carries them over the land, and the heated ground warms the air, making it expand and rise upward like wood plunged in water through heavier air overhead. So, rising, it grows cold again and can no longer contain all its moisture. The once river particles are next pressed gently out of the air as a little mist, and they go to join a cloud near. The cloud is borne by air currents to and fro, till perhaps it reaches the very same mountain from which ran the river which brought these water particles down to the sea. The cold mountain peak cools still farther the air in which the cloud rests. Then heavy showers of rain fall, soaking the earth, filling the rills, and feeding the rivers which run into the sea. Or the mountain and cloud are both so high up in the air that the cloud is frozen and snow falls instead of rain. It comes to the same thing in the end. The snow drains out in a river of ice, and the river of ice becomes a river of water. Now we see how true it is that from whence the rivers come, thither they return again. Do they come from mountain ranges? Mountains receive far more plentiful supplies of rain and snow than level plains. The rain and snow combine to feed the rivers. The rivers feed the sea. The sea feeds the air. The air feeds the clouds. The clouds empty themselves upon the mountains. Do the rivers come from the clouds? That is equally true. Clouds pour down rain. Rain fills the rivers. The rivers supply the sea. The sea surface dries into the air as vapor. The vapor becomes clouds. So whether we start with mountain rivulets or with clouds, the circle is complete and we come always round to our starting point. The whole world, land and ocean and atmosphere, has been described as a vast distilling apparatus. The warm South Seas serve for its boiler. The sun is its furnace. The colder regions, north and south, are its condensers. We may talk of the atmosphere as a huge pumping engine for pumping up and showering down water. But the atmosphere does not and cannot act alone. It works in company with land and ocean under the sun's control. Tropical oceans, steadily heated by the sun's rays, send streams of vapor into the air. These streams of vapor pass upward with the steadily ascending air of the equatorial calm belt. Air, as it rises, becomes colder, not merely because the upper regions of the atmosphere are colder, but because the lessened weight of air above makes it expand, and in this act of expanding or stretching, a certain amount of heat is given out. Now, the air growing colder becomes virtually damper, not actually damper because it does not contain more vapor than before, but virtually damper because it is more nearly saturated, more nearly obliged to part with some of its hidden vapor. The next stage is that it does reach a saturation point and does lose moisture, which is poured down as heavy rain. The torrents of rain peculiar to the calm belt of the equator were described earlier. Having parted thus with a goodly amount of vapor, the air, still mounting, reaches that level in the atmosphere where the antitrades flow to north and south. It used to be supposed that the high-level currents from the equator carried away immense supplies of moisture to be poured down as rain over the temperate zones beyond Cancer and Capricorn, over the south of Europe, for example. This view is now held with more reserve. No doubt the antitrades do contain a certain amount of vapor, even after sending down abundant torrents near the equator. Great cold, however, rapidly condenses moisture into cloud and rain, and these tropical currents, before starting for the north or south, reach very high and very cold regions of the atmosphere. They can hardly, therefore, be supposed to bear away any enormous amount of tropical vapor. The cold which they encounter in temperate countries, even in winter, can hardly exceed the intense cold of those lofty air levels above the topmost mountain peaks ever climbed by man. Whatever moisture the antitrades still hold, when they come down to earth beyond the Tropic of Cancer, can hardly be distilled into cloud or rain by the cold of southern Europe. It would rather be carried away to the far north, there to feed the Arctic snowfields and glaciers. In an earlier chapter, the atmosphere was spoken of as a big invisible sponge, always resting on the ocean and becoming filled with water. Near the equator, the sponge gets well saturated. Then, passing upward, it has a very severe squeeze from the intense cold of higher regions, which sends down rain in torrents. After that violent squeeze, one would hardly suppose the sponge to be sensitive to further squeezes from the soft air of South Europe. In all these operations, as said earlier, the real working power is the sun. The atmosphere without the sun would be as the steam engine without furnace fires, a very perfect machine, no doubt, but powerless to act. Air is simply the machine or engine through which the sun acts. The task carried out by sun and air is indeed no slight one. To raise daily tons upon tons of water out of the ocean, to lift these mighty masses high, not in one convulsive heave, but calmly, gently, noiselessly, with no sign of effort or strain, to bear them to and fro lightly, as a leaf is carried by the wind, to pour them down again on land and sea, not in one death-dealing cataract, but in showers of separate drops. This is what has to be done, what is done, day after day, by the great sun and the obedient air. But for the sun we should have no drying up of moisture, no clouds, no rain. Nay, but for the sun we should have no glaciers or snowfields. For glaciers are fed by snowfields. Snowfields are fed by clouds. Clouds are fed by invisible vapor in the air. Vapor is lifted out of the sea into the air by the sun. So, without sun heat, there could be no floating vapor. Without vapor, no clouds. Without clouds, no snow. Without snow, no glaciers. A curious chain of causation, distinctly providing that the ice rivers of Switzerland and of the Arctic regions have their origin in the heat of the sun. Indeed, the greater the power of the sun in the summer of southern lands, the larger are the supplies of vapor drawn into the air. The greater the amount of vapor carried by the winds against mountain ranges or into the north, the heavier will be the snowfall. An exceptionally hot summer is often followed by an exceptionally cold winter, while a cooler summer means often a warmer winter to come. So, round and round, in and out, the water circulation continues, out of the sea into the air, out of the air into clouds, out of clouds down upon earth, from the earth into the ocean, or out of snow into water, out of water into vapor, out of vapor into a snow cloud, out of a snow cloud into snow. The course of changes, the chain of events may be differently told. Either way, it is a circular chain without apparent beginning or end. End of chapter 22.
Chapter 23 of The Ocean of Air, Meteorology for Beginners. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by John Brandon. The Ocean of Air, Meteorology for Beginners by Agnes GIBERNE. Chapter 23, Climate. Between the equator and the poles, every description of climate is to be found, from intensest heat to intensest cold, from utter dryness to utter wetness, from perpetual wind to perpetual calm. Any variety may be had. From Greenland's icy mountain to India's coral strand is a leap which the poet may make in imagination. The traveler can take no such leap in body, but must pass through stage after stage, leaping from one extreme to the other. It is only in fancy that we see side by side, sharply contrasted, hot and rainless Egypt with mild and rainy Ireland, Africa's burning plains with the vast icelands of Greenland, the awful heat of the Persian Gulf with the awful cold of Siberia, the continuous rains of the tropics with the fitful showers of temperate lands, the severe cold and heat of Canada with the moderate seasons of England. These and countless opposites, all upon one globe, come under the head of climate. Climate depends chiefly upon degrees of heat and cold, degrees of dryness and moisture, degrees of wind and calm. In other words, it depends upon the state of the air. Human beings taken generally manage to bear pretty severe extremes of heat and cold. Some of the very coldest spots inhabited by man are to be found in the Dominion of Canada and in that awful country of exile, Siberia. A hard-working Canadian bishop of the Anglican Communion, now living, has in the care of his diocese slept for 10 days at a time in open air with a temperature of 40 degrees below zero. Pretty severe for a man well on in middle life. He might indeed say, "You in England don't know what it means. We count a winter exceptionally severe if the mercury stands for any length of time at 20 degrees to 25 degrees above zero." But even the bishop's experiences are outdone by what unhappy Russian exiles have to endure at certain Siberian stations. Only his is voluntary endurance, theirs compulsory. At one of the said stations, Verkhojansk, the temperature stands habitually through December and January at 56 degrees below zero, and often sinks much lower. It sometimes descends to 81 degrees below zero. Turning to India for a glance at the opposite end of the scale, we find that at Masawa, during May, the thermometer has been known to stand as an ordinary event at about 99 degrees above zero in the shade, occasionally running up to 130 degrees. As a rough rule, further north or south from the equator means increased cold. There are successive bands of climate round the earth, zones of heat followed by zones of mildness, then of moderate cold, lastly of extreme cold. Each zone has its own peculiar plants and more or less its own range of peculiar animals. Animals have a wider range than plants, being better able to adapt themselves to varieties of climate, but perhaps man alone can live in almost all climates. It might be expected that the bands of climate round the earth would lie in regular order, so much less of heat matching so many miles further to the north. But under the modifying influences of air and sea, things are very different. Stiff lines of latitude drawn on a globe will not at all fit in with lines of climate. The latter are indeed most erratic. Instead of following the straight and even latitude lines, they run further north here and further south there, take a sudden bend, make an unexpected twist, do anything, in short, except to keep such rules as we should expect. But for every bend and twist and loop, there is a sufficient cause. Differences of climate depend first and chiefly upon the position of the sun in the sky, upon whether the sun's rays come straight down from above, or slanting from near the horizon. Within the tropics, the sun is always more or less overhead, and in polar regions he is never overhead. In the summer of temperate lands he is high up. In the winter, and also in the mornings and evenings of summer days, he is low down. Now, in the latter case, a sunbeam has to travel a much longer way through the dense, damp, lower layers of air. A great deal of heat is stolen from it by the air on its road, leaving little to reach Earth's surface. But when a ray darts downward from overhead, it travels through a far smaller amount of damp air, so it loses much less of its heat. However dazzling the sun may have been overhead, on a hot summer's day we are able commonly to look full at him without blinking when he gets near the horizon. A far thicker veil of floating moisture cuts off the chief part of his light and heat from our eyes. Another cause, besides the position of the sun in the sky, greatly affects climate. That is, the manner in which the sun's rays are received. The great sun acts with most impartial regularity, pouring down his beams alike on ground, on ocean, and on atmosphere. But there are two things to be considered in thinking about the power of a sun upon a world. One is how the sun bestows his beams. The other is how the world is affected by those beams. If Earth's whole surface were everywhere exactly the same, then the sun's rays would take effect everywhere exactly alike. Since it is made of different kinds of substance, partly solid and partly liquid, With a varying veil of more or less damp air above, this cannot be the case. Dry ground receives heat quickly and parts with it as quickly. Water receives heat slowly and parts with it as slowly. Air receives and parts with heat more or less quickly and slowly, according to its degree of dryness or dampness. We see the same thing, curiously enough, in human beings. What a man takes in with great ease, he is apt to forget with ease. And what he gains mentally with toil and effort, he does not soon lose. Water's slow gaining and long keeping of warmth modifies immensely the climates of Earth. Mighty ocean currents pouring north or south from the tropics carry tropical heat with them to colder parts, and make countries which would be frostbound for months rejoice in continuous mildness. But seriously, as oceans moving waters must and do affect climate, their influence would be far less without the help of moving air. For after all, the waters can do little more in themselves than wash the shores of a country. Their really effective work is to warm the atmosphere above, so that currents of air passing from the ocean over the land carry heat with them. 2 or 3 extracts from travelers' reports may help to bring before the mind what is meant by Earth's varieties of climate. As a variety, number 1, we find in the life of Colonel E. Warburton the following account of Australian desert heat experienced by travelers camping in a small oasis. The depot was shaded by large trees and by high cliffs, notwithstanding which the party suffered terribly from the intense heat. The mean of the thermometer for the months of December, January, and February was 101 degrees, 104 degrees, and 101 degrees, respectively, in the shade. Under its effects, every screw in their boxes had been drawn, and the horn handles of their instruments, as well as their combs, were split into fine laminae. The lead dropped out of their pencils owing to the shrinking of the wood. The signal rockets, a most valuable item in the equipment of the expedition, were entirely spoiled. Their hair, as well as the wool of the sheep, ceased to grow, and their nails became brittle as glass. Nor was personal inconvenience all the mischief wrought by this fiery atmosphere, for it was found to reduce the provisions alarmingly. The flour lost more than 8% of its original weight. The bran, in which their store of bacon was packed, became perfectly saturated, and weighed almost as heavy as the meat. They were obliged to bury their wax candles to save them from running into a shapeless mass. Even a bottle of citric acid became liquid, and escaping, burnt some linen, whilst it was with the utmost difficulty that they could either write or paint, so rapidly did the fluid dry in the pans and brushes. During the whole of this trying period, the leading members of the expedition never ceased in their attempts to find some means of escaping from this oven. To east, west, north, and south they rode, the heated stirrup irons blistering their feet, and the horses reeking with perspiration, though never put beyond a walk. Again, somewhat later, we find Captain Stewart returned to the depot, and after resting started off afresh, discovering Cooper's Creek, beyond which he encountered his old enemies, the sand ridges. He mentions the effect of the hot northeast gale. The blasts of heat were so terrific that he wondered the grass did not fire. This was nothing ideal, for everything both animate and inanimate gave way before it. The horses stood with their backs to the wind, and their noses sunk upon the ground, without the muscular strength to raise their heads. The birds sat upon the boughs, mute and terrified, and the parched leaves fell like snow, whilst the thermometer, graduated to 127 degrees, burst its tube, owing to the expansion of the mercury. Before fresh supplies reached them, the leader had lost the use of his limbs from scurvy. His skin became black, and the muscles contracted. In contrast with the above, as a specimen of climate variety number 2, let us turn to Captain Scoresby on the Arctic regions. An Arctic winter consists, he writes, of the accumulation of almost everything among atmospheric phenomena that is disagreeable to the feelings. The Greenland sailors, being well defended from external cold by a choice selection of warm clothing, generally support the lowest temperature after a few days' habitude without much inconvenience. When, however, its attacks are not gradual, as when a ship which has attained the edge of the ice under a southerly gale is exposed suddenly to a northerly breeze, the change of temperature is so great and rapid that the most hardy cannot conceal their uneasiness under its first impression. On one occasion, in the year 1814, there was between the time of my leaving the deck at night and arising the following morning an increase in the cold of about 20 degrees. This remarkable change was attended with singular effects. The circulation of the blood was accelerated, a sense of parched dryness was excited in the nose, the lips were contracted in all their dimensions, and the articulation of many words was rendered difficult. The hands, if exposed, would have been frozen in a few minutes. A piece of metal, when applied to the tongue, instantly adhered to it, and could not be removed without its retaining a portion of the skin. Iron became brittle, the ship became enveloped in ice, the bows, sides, and lower rigging were loaded. Again, with reference to some seamen who wintered in Spitzbergen, after the commencement of the new year, the frost became more intense, it raised blisters in their flesh, as if it had been burned with fire, and if they touched iron at such times it would stick to their fingers like bird lime. Mr. Ballantyne's account of winter in Hudson's Bay is to some extent an echo of the above. After that October, until the following April, the thermometer seldom rises to the freezing point. In the depth of winter it falls from 30 to 40, 45, and even 50 degrees below zero of Fahrenheit. This intense cold, however, is not so much felt as one might suppose, as during its continuance the air is perfectly calm. Were the slightest breath of wind to arise, when the thermometer stands so low, no man could show his face to it for a moment. The houses are built of wood with double windows and doors. They are heated by means of large iron stoves fed with wood, yet so intense is the cold that I have seen the stove in places red hot, and a basin of water in the room frozen nearly solid. In pleasant contrast with these violent extremes, a few words from Miss Gordon Cummings' First Impressions of Fiji may serve well for variety number 3. As regards climate, our impressions are highly favorable. We see white men who have been here for years going about without any of the ordinary precautions deemed necessary in tropical climates. White umbrellas and solar hats are alike neglected, and a white pudgery is considered ample protection in a country where sunstroke and fever are alike rare. The thermometer at 90 degrees marks an exceptionally hot day, and with the exception of occasional tropical showers, we have generally fine weather. Hot certainly in the midday hours, but almost invariably tempered by a balmy breeze and soft gray clouds. December is supposed to usher in midsummer heat and heavy rains, not incessant, but very much in earnest while they last. And for 3 months we may be liable to hurricanes, which, however, are not an invariable part of the program, nor can they possibly be as severe as those of the West Indies, or all the frail buildings which compose this little capital would inevitably have long since been leveled with the ground. The thermometer has often been spoken of in this chapter. A thermometer is a measurer of heat, and climate is largely a question of more or less heat. The little instrument consists of a glass tube ending below in a glass bulb. It contains enough mercury to fill the bulb and part of the tube, the rest of the tube being partially emptied of air. Mercury is quickly affected by heat and cold. When the surrounding air is very hot, the mercury swells in size more rapidly and to a greater extent than the glass, so the slender line of it in the tube gently rises. When the surrounding air is cold, the chilled mercury grows smaller, takes less room, and sinks lower in the tube. End of chapter 23. Recording by John Brandon. Chapter 24 of The Ocean of Air, Meteorology for Beginners. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by John Brandon. The Ocean of Air, Meteorology for Beginners by Agnes GIBERNE. Chapter 24. Weather. Climate and weather are closely related, but not identical. For questions of climate, we turn mainly to the thermometer. For questions of weather, we turn mainly to the barometer. Yet the state of the barometer has also a very intimate connection with the climate of a place, and the state of the thermometer with its weather. On the whole, weather is a word more used with reference to the temperate zone than the tropical regions. When the sun blazes day after day for months out of a blue sky with no change or sign of change, men do not say, "What beautiful weather," but rather, "What a sunny climate." Just as day and summer, night and winter merge into one at the poles, so climate and weather merge very much into one within the tropics. The very rain comes when it does come, with a regularity which speaks rather of climate than of weather. In our temperate regions, our northern belt of variable winds, while climate has certain persistent outlines which may be reasonably calculated on, weather seems to be a thing of impulses, altogether erratic. Yet our weather, like all else in nature, is governed by settled laws. Weather in England is not more really fitful than in the tropics. It is only uncertain in respect of our ignorance. The many forces which combine to bring about varying results are more complex than the broader and simpler rules which govern tropical weather, and are not so well understood by man. Nonetheless, every change of breeze, every passing shower, every cloud which forms and vanishes, has had its causes leading up to the present moment. One main foundation of climate is the heat of the air in varying degrees. A main foundation of weather is the weight or pressure of the air in varying degrees. As the warmth of the air is measured by the thermometer, so the pressure of the air is measured by the barometer. A barometer, like a thermometer, consists of a glass tube holding a column of mercury, the upper part of glass being as far as possible emptied of air. Here the resemblance ceases, for the mercury column rests in a little vessel open to the air, and the atmosphere pressing upon the exposed mercury keeps the slender column upright in the tube, just so high as to balance its own heaviness. If the pressure of the air weighs exactly the same as the column of mercury, 28 inches high, then the mercury column will stand exactly 28 inches high in the tube. If the air presses harder, it will push the mercury column higher. If less hard, it will let the mercury column sink a little lower. A barometer examined first at the sea level and then carried up a mountain will be found on the summit to tell of greatly lightened air, for the denser layers have all been left below, and the pressure is in consequence much lessened. Even at the sea level, the pressure is by no means always the same. Air there is sometimes lighter through warmth, sometimes heavier through cold. Also, currents of air, especially those which flow upward and downward, have a good deal to do with degrees of pressure. In the last chapter, we heard about certain charts on which are drawn climate curves, or curves of equal warmth in different places. Charts are made in like manner for the drawing of weather curves, or curves of equal air pressure in different places. Very often a chart is made, which is a union of the two. Upon a map of a certain district are drawn the climate lines of a certain date, as shown by thermometers, and the weather lines of the same date, as shown by barometers. The map is then filled in with symbols of rain and fine, wind and calm, occurring in different parts. Thousands of such records have been taken during the last few years. Weather curves are even more fitful and curious than climate curves. The latter do at least wave and zigzag round the earth, keeping in some sort of fashion in one chief direction. But the weather curves run fantastically all ways, and form most singular shapes. Not any and every kind of shape, however. Even here we find rules apparently laid down and carried out. Even the wild winds have method and order stamped into their very being. These weather curves, when drawn upon the map, fall commonly into one or another of 7 distinct shapes or classes, known one from another by a practiced eye. Some of them, such as cyclones and anticyclones, are familiar to us by name. Now, nothing is easier than to turn disdainfully away and say, of course, anybody may draw any lines upon a map and make what shapes he pleases. But these are not fanciful outlines. They follow strictly the actual readings of barometers all over a certain district at a certain time. Each barometer reading shows the exact pressure of the air, just when and where it is noted, and that degree of pressure always means something definite about the weather, though what it means is not always clear to us. Distinctly as the beating of your pulse shows the state of your health, the rise or fall of the barometer shows the condition of the atmosphere in respect to its pressure. Reading the barometer is feeling the pulse of the air. But not everybody with eyes can read a barometer truly, any more than everybody with fingers can feel a pulse understandingly. A man seated in a central office receives news at once from many stations. In some of these stations, the mercury stands, let us say one particular morning, at 29.6 degrees. In others at 29.8 degrees, in others at 30.0. On this map he draws lines from place to place of the first, from place to place of the second, from place to place of the third. He does not follow any private notions of his own, but simply obeys the readings of barometers. These lines, when drawn, form certain shapes, and the shapes speak of certain actual realities in the ocean of air. One can well imagine that curves so drawn, dictated, as one may say, by the freaks of the wild winds, might fall into any manner of shapes, never turning out twice the same. Yet it is far from being so. The wild winds show methods in their madness. These shapes do constantly turn out so far alike as to be easily classified. Moreover, each kind of shape has a more or less distinct kind of weather belonging to it. The air-ocean, as we have already seen, is never at rest. It is in a condition of perpetual whirl and turmoil. Circulating currents stream to and fro, winds pour this way and that way, eddies and ripples innumerable cover the face of the earth. A ceaseless conflict of forces goes on. Rivers of air to the north are balanced by rivers of air to the south. Heat strives with cold, and evaporation strives with condensation. Heavy air rushes towards light air, and light air flees from heavy air. In the flow of a great river, there is the general movement of the whole body of water from a higher to a lower level. There are also countless lesser flowings to and fro, eddyings round obstructions, silent pools, calm stretches, broken waves, and rapids. As the river runs, its surface has various risings and depressions. Its waters pour many ways, which might be indicated by shapes drawn on paper. So, too, with the atmosphere. There are the mighty main streams below and above. There are also back streams, side streams, lesser currents, cyclings to and fro, heights and depressions of the outer surface, waves and eddies innumerable. One may see baby eddies of air in the road on a windy day, tiny whirls of air carrying round dust and leaves. A cyclone is such an eddy on a large scale, varying from 50 to over 2,000 miles across, and other air disturbances are more or less of the same nature. An eddy of water may be either fixed or in motion. A river eddy is often long motionless. Water particles pour in, circle round, and pour out again, while the eddy itself is unchanged. But some river eddies and most ocean eddies travel onward from one spot to another, forming and vanishing after a fitful fashion. There are eddies of air which remain motionless, as well as eddies of air which move. Anticyclones are often stationary for hours and days, even for weeks and months. Air particles flow in and out of the stationary anticyclone, but the great eddy itself, gently circling, is fixed in one place. Some anticyclones travel like other eddies. Some form, stay for a while where they are, then break up. As a rule, air eddies are given to moving on. A cyclone, like an anti, may form anywhere and break up anywhere, but it almost always journeys, sometimes traveling straight forward, sometimes creeping round the edge of a fixed anticyclone. This drifting over us of air eddies is a fact which ought to be clearly grasped. Weather comes to us, we do not go to it. Man stands still, so to speak, and different kinds of weather sweep past. A cyclone comes to give him rain, an anti comes to give him sunshine. Each, in turn, drifts onward elsewhere, to be replaced by some other form of weather. If a man wants a change of climate, he leaves his own climate and goes across land or sea to find something different. If he wants a change of weather, he has only, at least in our variable country, to sit still, and the change will surely come to him. Every phase of weather arrives in turn, as eddy after eddy, ripple after ripple, wave after wave, journey across the land. The weather map, which is true of Europe and the Atlantic one morning, has often to be quite altered by the next morning. Nearly all the same eddies may be still in existence, but the whole has drifted on, so that each spot in the map has changed its weather. Where a cyclone was yesterday, a wedge is today. Where the wedge was yesterday, a big anti is pushing its way today. Where the anti was yesterday, a col has moved today, and so on. People are apt to associate the word cyclone with a terrific storm. Yet it does not necessarily mean a storm, particularly in temperate regions. A falling barometer ushers it in, and it does bring some wind and rain. Whether much or little depends upon what is called the intensity of the cyclone. It may be languid, or vigorous, or violent, but in each case the nature of the eddy is the same. The only real distinction between those cyclones which bring a mild, ordinary amount of wind and rain, and those which usher in mighty gales with tremendous rain or snow, lies in the intensity of either. The degree of intensity depends upon something else which is rather difficult to explain clearly in a simple sketch of this kind. A little illustration may help. Suppose you have to walk up a hill from a level plain. The hill may rise slowly or sharply. There may be a long or a short space between the spot where you stand 100 feet above the plain and the spot where you stand 200 feet above it. The long space would mean a gradual ascent, the short space a sudden ascent. In either case, the hill is said to rise so many feet in the mile. There is a slope also in a cyclone, not the slope of a solid hill, but the slope of different barometer heights. Where a cyclone exists, the barometer is always lower inside and always higher outside the eddy. The rise of the slope from a lower barometer in one place to a higher barometer in another place is reckoned not by so many feet in the mile, but by so many tenths of an inch in the mile. To illustrate this, suppose you have two barometers daily watching in two towns, 3 or 4 miles apart. One day the two barometers are the same, the mercury standing in both at precisely the same height. This means a calm. Next day, one barometer is 2/10 of an inch higher than the other. This means a little wind. Another day, one barometer stands 1/2 an inch higher than the other. Quite a steep slope. This means something of a storm. Yet another day, one barometer stands 1.5 inches or 2 inches higher than the other. A tremendously sharp ascent. This means a hurricane. Such violent differences within a few miles are seldom and never known in the British Isles. But they are by no means unheard of in tropical lands. End of chapter 24. Recording by John Brandon. Chapter 25 of The Ocean of Air, Meteorology for Beginners. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by John Brandon. The Ocean of Air, Meteorology for Beginners, by Agnes GIBERNE. Chapter 25, Eddies of Air. Weather foretellings have been popular in all ages. How popular is this fitful climate of ours is curious, when one sees how often they fail. Some signs of rain and fine, believed in from time immemorial, have foundation in truth. Unless fairly often found correct, they would hardly have obtained such a hold upon people's minds. Excessive damp on walls, springing from excessive moisture in the air, is a most natural token of coming rain. The red sky and the rainbow of early morning are about equally the shepherd's warning. Halos and mock suns belonging to the van of a cyclone are pretty sure indexes of what may be expected. A hollow, luminous circle round the moon may not mean rain the next day, inevitably, but within 2 or 3 days it is an almost certainty. The old moon in the arms of the new, and the clearness of distant hills, both arising from the transparency of the air, are marked signs of rain, not far distant. About 3 mornings of white frost are held to be equally infallible. Also, birds and flowers have a voice in the matter. Swallows fly low before rain because insects do the same, and many sensitive blossoms close their petals in anticipation of a coming downpour. The little red shepherd's glass is famous for its true predictions, and a certain pink starry mesembryanthum has shown itself almost equal to a barometer in quick understanding of the atmosphere. Signs of fine weather popularly held are not fewer in number. The opposite characteristics of dry surfaces, of a hazy horizon, of a crimson sunset, of opening flower petals, promise fairness. The flying far of rocks and seabirds, and the flying high of swallows, are counted especially hopeful. A white moon promises well, and so do gossamer webs floating in abundance. The difficulty of reading truly all such signs, as well as the barometer itself, consists in the fact that the same tokens do not precede all kinds of wet weather. Before the rain of an ordinary cyclone, the barometer falls, but before another kind of air eddy, which brings rain, the barometer rises. Besides these uncertainties, one never knows how long an eddy may last. At any time a cyclone may die out and vanish. A storm may be publicly foretold as traveling to England. Signals may be hoisted, and precautions taken, and after all it may never appear. It has either altered its course going off in a new direction, or it has quietly broken up and dispersed. The foretellings were correct so far as they went, but the new freak of the wild air could not be reckoned on. Now and then a storm strikes our shores, no warning of which has been received. This may well happen, for cyclones travel fast. People often wonder why swift steamers do not come on from mid-ocean in advance of the storm to tell us of its approach. But the cyclone which should only keep pace with a steamer would be a slow specimen of its kind. There is, of course, the telegraph. If a cyclone starts from America, instead of taking shape in mid-ocean, notice can be flashed under the ocean, and a cyclone cannot compete with electricity. This is how we often do here beforehand. But even an electric message occupies time. Time is consumed in sending it, in receiving it, in transcribing it, in dispatching it to the central office. Time there is occupied in examining a great number of telegrams, in comparing notes, in charting the information received, in sending word to British seaside stations, and all this while the big eddy of air is traveling rapidly nearer. The very most that can be done generally is to foretell a cyclone, not to say whether it will be mild or severe. Various well-known signs belong to the front part of a cyclone, such as a watery sun and a pallid moon. High hills and mountains show cloud caps. Animals are restless. Neuralgic and rheumatic patients suffer more than usual. Old soldiers are reminded afresh of their wounds. Corns become troublesome, and irritable tempers are apt to be upset. The weather is dull and oppressive, muggy and cloudy, and more or less warm rain falls when the barometer continues to sink. Near the center, something of a calm commonly exists, surrounded by the revolving winds. Patches of rain, alternating with patches of blue sky, lie within a circle of clouds. When about half the cyclone has drifted by, and the trough, or the line across the lowest depression, is passed, a change takes place. The barometer begins to rise. The sky becomes clearer with wool-packed clouds. The air is more sharp and cold, and the rain, if any falls, is colder than before. A cyclone has been described as an extremely complicated vortex, something analogous to an eddy of water, but differing from an eddy of water in that the latter sucks down, while the air vortex draws upward. It has also been spoken of as a huge, irregular funnel of rotating air. The winds, whether slight or strong, always revolving round an axis of comparative calm, spirally like a corkscrew, inward and upward. Whether the vortex of rotating air ever reaches the upper limits of the air ocean, or whether it's always confined to lower regions, seems uncertain. Much obscurity still exists with reference to its nature. As the cyclone drifts over a certain place, frequent changes of wind occur. It cannot be otherwise, since in no two parts of a cyclone do the winds blow from the same quarter. Each cyclone has two distinct motions, not unlike those of Earth. As the solid body of the earth revolves upon her axis, so the winds of a cyclone revolve round its axis. As the whole earth journeys through space, so the whole cyclone travels across Earth's surface. In our part of the world, cyclones more commonly journey from the southwest to the northeast. Now and then one arrives from the neighborhood of Norway, but by far the greater number come to us from the Atlantic and from America. The direction taken by a journeying cyclone is affected by the daily whirl of Earth, much as the direction of trade winds is affected by it. A cyclone traveling from the north comes to us from the northeast, while one traveling from the south comes to us from the southwest. Air circulation within a cyclone is always according to rule. The winds of a northern hemisphere cyclone rotate round the axis in a direction contrary to the hands of a watch, while the winds of a southern hemisphere cyclone rotate with the watch hands. If you lay a watch upon a map face upwards, you will at once see the way of the winds in a cyclone on any part of the world. These rules are reversed in the case of an anticyclone. Here again we have an eddy or vortex of winds rotating round an axis, though the rotation is sometimes so languid as to be imperceptible. But the direction of the winds is exactly the other way from that of cyclone winds, being with the watch hands in the northern hemisphere and contrary to the watch hands in the southern hemisphere. Moreover, the spiral movement, or the suck of an anticyclone, is downward, like a water eddy, instead of upward like a cyclone. This results in a piling up of the air, which helps to cause a high barometer, one of the signs of an anticyclone. Anticyclones mean generally fine weather, cold in winter, hot in summer, with hazy distances and little wind, and commonly with sunshine. On the continent, a warm anticyclone with a cloudy sky is sometimes seen. The leading feature of an anticyclone is calm, with what is called radiation weather. There is little cloud or floating moisture to check the quick pouring out of heat from the ground after sundown. So in an anticyclone we have dew or hoarfrost. In large towns this particular eddy often brings dense fogs. Persistent anticyclones are found both in the far north and in the tropics, as on the icy plains of Siberia and on the burning deserts of Africa, often continuing for months unchanged. Probably an explanation is to be found for the main distinction between the two eddies, as bringers of rain and bringers of fair weather, in their opposite modes of air currents. When air rises from below to above, as over the equator, it commonly has a squeeze from the cold above and sends down rain. When air sinks from higher to lower levels, it can not only hold all the moisture it held above, but it can take in more. So the rising air of a cyclone would naturally cause wet weather, and the sinking air of an anticyclone would suck up floating mists, clear the sky, and, as a general rule, cause sunshine. There are rains which cannot be foretold by weather curves on a map. The rains, for instance, of the Indian monsoon, of sea squalls, of thunderstorms, of tornadoes and whirlwinds. Simple squalls come at sea in sharp gusts, more or less violent, lasting generally only a few minutes. 2 or 3 such squalls may be seen at once careening over the ocean, ruffling its surface. About the most simple kind of thunderstorm known is such a squall accompanied by lightning and a clap or two of thunder. These squalls are merely little local efforts to restore the balance of the atmosphere. Thunder squalls are more common in winter than summer, while heavy thunderstorms are more common in summer than winter. The cyclones which visit the British Isles are tame compared with what other countries endure. Still, from time to time, we have a sufficiently sharp experience to learn something about the power of a mighty wind. Perhaps one of the most fearful ever known to visit our shores was the great storm of November, 1703, 1 year after Queen Anne came to the throne. France, Germany, and other countries suffered from it, and over a great part of England the damage done was excessive. In Kent alone, 800 private homes were wrecked, and 17,000 trees were blown down. Scores of churches had their leaden roofs torn off. Sheep and cattle in countless numbers died, and many human lives were lost. The Bishop of Bath and Wells and his wife were both killed in bed by the falling chimneys of the Episcopal Palace. Ely Cathedral suffered cruelly. Of Brighton, Defoe wrote, "Brighthelmstone was most miserably torn in pieces. It made the very picture of desolation, and looked as if it had been sacked by an enemy. In the Thames, no less than 500 wherries sank, and the whole mass of vessels, 4 only of which escaped, were torn from their moorings by the violence of the wind. 12 men of war, large and small, foundered in different places, and the wrecked remains of countless merchantmen strewed our coasts. The first Eddystone lighthouse was carried completely away, leaving a bare reef, and of the men within it, including the overconfident architect, not a trace could be afterwards found." Such scenes as these are happily rare in England, and the winds, even in their more furious moods, have often fought on our behalf against foreign foes. No true Englishman can fail to be thankful for the mighty gales of 1558, which scattered the invincible Armada, swept the Spanish galleons to the far north, and drove a terrible peril from our shores. Of 150 vessels which left Spain in disdainful pride, promising triumph to themselves, only 56 broken ships crept back into port. Afflavit Deus et dissipantur. The force of rushing air was direfully shown a few years ago in the Tay Bridge disaster. A terrific gale was blowing when the Edinburgh train, quitting the Fife side, passed on the long, narrow railway bridge which led across to Dundee. From 150 to 200 passengers were in the train. Stormy night though it was, no one thought of real danger. A few minutes' quick passage, and they would reach the other side. The great brick piers and iron girders were counted strong enough to stand any ordinary strain. But men had as often miscalculated, and no doubt the strain was more than ordinary. The train passed onward upon its slender pathway, and the passengers within could look down on either side straight into the wind-tossed, moonlit water. Word was flashed along the wires to the Dundee station that the train was on its way thither. Those at Dundee waited and watched expectantly, mindful of the furious storm. In the moonlit darkness of a December evening, they could see the train passing swiftly along the rails. Then suddenly a crash of sound could be heard above the howling of the gale, and a bright flash of fire was seen near the bridge's center. After that, a pause. The telegraph wires refused to act, and the train could not be seen. Its arrival was awaited in vain. Madly as the wind hurled itself against aught in its path, 2 men made their way along the exposed bridge, only to find a mighty gap in the structure. So far as they could see, 2 or 3 of the biggest spans were swept away, and with them was gone the whole train, carrying down its entire freight of human beings. Not one survived that awful plunge to tell the tale. End of chapter 25. Recording by John Brandon.
Chapter 26 of The Ocean of Air, Meteorology for Beginners. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Ocean of Air, Meteorology for Beginners by Agnes GIBERNE, Chapter 26, Whirlwinds and Tornadoes. After all, the heaviest storms ever seen in England are but a child's play, compared with the terrific outbursts of tropical lands, the whirlwinds and tornadoes, the hurricanes, typhoons, and pamperos of countries near the equator. A tropical hurricane or cyclone is much smaller in diameter and travels much more slowly than the cyclone of temperate regions, but the whirl of its eddying winds is far more violent. A cyclone in Europe will journey at various rates of speed, from 20 to 70 miles an hour, while a tropical whirlwind seldom moves faster than 10 miles an hour. It is, however, infinitely more destructive on account of its greater force of wind. The two movements of a cyclone may be illustrated by the two movements of a top. As a top spins upon its point, it also travels forward. It may spin fast or slowly, and it may travel forward fast or slowly. Each movement is independent of the other. Or again, a man may walk forward, and as he walks, he may whirl round his head a stone tied to a string. If the whirling stone strikes against anything or anybody, it may do some damage. The amount of damage depends mainly upon the force and rapidity with which the stone is whirled, not upon the speed or slowness of the man's walk. So the amount of damage done by wind is in proportion to its violence. The harder it blows, the heavier are the objects which it can lift and carry along. Footnote. An ordinary light or moderate breeze travels from about 12 to 24 miles an hour, a strong breeze about 30 miles an hour, a moderate gale about 40 miles an hour, a strong gale about 50 miles an hour, a storm about 70 miles an hour, a hurricane about 90 miles an hour. How much harder a hurricane can blow it is not possible to say. When winds reach this degree of fury, neither men nor instruments are in a state for scientific observation. End of footnote. We are now thinking about the actual motion of air particles. When we talk of a wind blowing at such a rate, we mean that the actual substantial particles of air move thus. When we talk of a cyclone or whirlwind traveling over the earth's surface at such a rate, we mean that the whole great air wave or atmospheric eddy travels thus, while in the eddy particles of air are circling round the central column at the speed before mentioned. The crowded particles of air flow in and out of each eddy, just as particles of moisture flow in and out of a cloud, just as particles of water flow in and out of a wave, while eddy, cloud, and wave has each its individual shape and its motion as a whole. When a wind blows at the rate of 80 or 90 miles an hour, the pressure of air is tremendous and great damage is done. Happily, wind, even at its worst, comes more or less in gusts, and bears with varying weight here and there. A house may be laid low with a single blast, yet the windows of another house close by may be unbroken. Such curious freaks in the action of winds are often seen. If it were not so, whole woods and forests would be levelled instead of occasional trees, and all the chimneys in a town would come down, for now only a few stacks are demolished. Tropical cyclones have usually a patch of blue sky exactly over the center called the eye of the storm. The circular storms of the tropics are known as hurricanes in the East and West Indies, as tornadoes and whirlwinds in the United States, as typhoons in China. The pamperos of South America belong strictly to the same class, though the term is often used loosely. Whirlwinds vary in size from the tiny eddies of air seen in a street on a gusty day to the terrific tornadoes of the States, which bear down everything before them, and the fearful hurricanes of both East and West Indies, which leave desolation in their track. As a rule, whirlwinds, whether large or small, probably arise from the meeting of two opposite or nearly opposite currents of air, the struggle for adjustment causing naturally an eddy. The whole history and nature of tropical whirlwinds are still full of difficulty, though marked points of resemblance exist between the hurricane of the tropics and the more gentle cyclone of temperate regions. The two are so unlike in many main particulars that it seems doubtful whether they may be classed together. Near the coast of India, hurricanes are most frequent in October and May, when monsoon changes come about. The air has many a fierce struggle then to regain its lost balance. In these storms, as in the storms of quieter lands, there are barometer disturbances, and to a much greater extent. The slope of the barometer heights is far sharper. At the center of a hurricane, the barometer has been noted as standing fully 2 inches lower than outside the storm. This tremendous difference is but a short distance, for tropical storms are of small extent, must mean a mighty atmospheric upset, only to be put right by hurricane blasts. The word cyclone, footnote, from Greek, a circle, end footnote, dates from the year 1848. Until nearly the middle of the present century, the circular shape of hurricanes was not even suspected. Many a good ship has been lost for want of this knowledge. Caught in a sudden hurricane, it would battle onward unconsciously towards the center. There it would meet with either comparative stillness in the way of wind, or with violent and changeable gusts, and in either case with a rough chopping sea. Still, the worst of the storm would seem to be over, and the sailors would be rejoicing in their escape, perhaps spreading sail more freely, when a fierce roar of renewed tempest would burst forth from just the opposite quarter to that which they had before encountered. Too often ship and sailors were lost in the fresh peril. It will readily be understood how a vessel crossing a circle of wind must necessarily meet opposite winds on the two sides of the circle. Now that the laws of cyclones are better understood, a captain, finding his vessel overtaken by one, knows in which direction to steer so as to avoid getting near the center and to escape as fast as possible. One of the most fearful of modern cyclones was that of October 1780, which started from Barbados and traveled to Bermuda. English ships off St. Lucie were destroyed, and 40 French transports off Martinique, carrying 4,000 soldiers, were lost, simply vanishing with all on board. In Martinique, 9,000 people died, and in St. Pierre, not a house remained standing. At Port Royal, 7 churches and 1,400 houses, as well as the cathedral and the hospital, were all reduced to ruins, and 1,600 sufferers perished in the latter. At St. Lucie, men and animals were lifted up and carried by the wind, and a heavy gun was swept 30 yards from where it stood. 14 houses of the 600 dwellings in St. Vincent alone remained when morning dawned, and not a leaf or twig clung to the stripped trees in the neighborhood. Footnote, from the atmosphere. End of footnote. A Chinese typhoon is much the same as an East or West Indian hurricane, equally violent and destructive. One which passed through Canton in August 1862 left between 8,000 and 9,000 dead. A gentleman living there wrote afterwards. Footnote, Leisure Hour 1862. End of footnote. The gale commenced in Canton to blow with fury at about 11 o'clock. The river was a fearful sight. A usually placid stream, no wider than the Thames, is suddenly converted into a stormy sea, the waves lashing the shores with angry fury, their dreadful aspect increased by the dull leaden hue cast of the clouds and water, and even on the very atmosphere. Air and water seem completely intermingled and undefined. Howling and roaring, they fly past with impetuous speed, carrying with them thousands of boats, many of them bottom upwards or broken to atoms by constant collisions, and human beings beyond the reach of help. Nor are disasters confined to the river. On shore, Houses are constantly falling and walls tumbling with a crash. Hundreds of families are in a moment rendered houseless. The sky is now clearing. The storm has lasted not quite 2 hours. It has been blowing from northeast. The sun begins to peep out. The wind subsides as rapidly as it rose. Not a leaf stirs. There is a death-like stillness. But what is that? Hark! Aye, and before the question is answered, more furious than ever blows the blast from the opposite quarter of the compass. Wreckers afloat and looters ashore are taken by surprise, and many pay for their temerity in their dishonest calling with their lives. The same scenes again occur, and after an hour or two the wind again, but more gradually, subsides, and eventually gives place to fine weather. A clearer illustration than this could hardly be given of the manner in which the whirling eddy of air passes over a place, bringing in succession most contrary winds. The chief characteristic of the American tornado seems to be its extraordinary funnel of dark cloud, formed and helped by the revolving winds. Masses of dust swept up from the earth are mingled with masses of moisture, making what looks like an upright spout of cloud or mud. Where the tornado passes over a lake or the sea, this becomes a veritable waterspout. The spout may be only a few yards in diameter at its thinnest, widening below and above as it reaches down to earth and up to the level of low-lying clouds. The whole area of the storm is often not more than a few hundred yards across. The entire whirlwind travels at a rate of about 30 miles an hour, or as fast as a moderate train. Within that limited space all is destruction, the great eddy leaving utter ruin in its track. Solid buildings are leveled with a single blow, or lifted and turned around before being torn to pieces. Such a tornado took place in May 1879, ushered in as usual by close heavy weather. Rain began to fall, changing rapidly to furious hail. Some of the stones were found afterwards to be 3½ inches in diameter, and one at least weighed 1/4 pound. The dark, inky, funnel-shaped cloud formed gradually, a revolving mass of moisture, dust, and mud, upheld by the weight of the revolving hurricane. Its roar could be heard 3 or 4 miles off. Whatever lay in its path was seized, whirled round and carried onward. The whole diameter of this storm was only about 43 yards, and the height of the funnel was supposed to be about 500 feet. As an instance of the ruin wrought, a huge plough, weighing 700 pounds, was caught up and borne bodily over a space of 20 yards. A woman was carried like a feather for 200 yards, then dashed against a wire fence, not only killed but stripped of all her clothing, and deluged with black mud from head to foot. When the storm had gone by, there came over its desolated track a rush of burning air, and then an ice-cold gale from the northwest. Footnote from Abercrombie's Weather. End footnote. We may be thankful that such visitors do not come to England. Wildly as the winds often howl around our shores, we have after all to do chiefly with the milder moods of the air ocean. Our countrymen in other lands, our ships in far-away ports, come in, as we have already seen, for these fearful outbursts of atmospheric fury, and a notable instance took place lately in the Samoan hurricane. Footnote early in 1889. End footnote. Some German and American vessels and His Majesty's ship Calliope were at anchor in the Bay of Apia when a tremendous cyclone burst suddenly upon them. The waters of the bay were lashed into a fury of waves, among which the ships were tossed about one against another, or flung upon beach and reef, helpless to resist. Some were wrecked, some foundered, and there seemed no way of escape from the desperate peril. 2 German vessels and 1 American sloop were lost, when the captain of the good ship Calliope came to a brave resolve. She had already been flung against the Vandalia, and a collision with the Trenton was near. Anchors and engines together were failing to save the American and German ships. But Captain Kane knew the power of his engines, the spirit of his men. He determined to slip his cables, to trust to the engines alone, and to throw the head of his ship into the very teeth of the hurricane. This done, there was a brief pause, the powerful engines at work, the Calliope remaining absolutely at rest, as the winds howled madly past. It must have been a pause, however brief, of unutterable suspense, for upon its outcome hung the fate of the ship, and probably the life or death of the crew. Then, slowly, the corvette stirred, moved onward, and crept by inches at a snail's pace out of the fatal bay, away to the safety of the open sea. As she passed the Trenton, a ringing cheer rang out from the brave Americans, able in their own deadly peril to appreciate the courageous daring of the English captain. One is glad to know that though the Trenton was lost, her crew escaped. The hearty cheer was heartily returned, and the Calliope was saved. But the powerful engines, ordinarily capable of carrying her through the water at a rate of 15 knots an hour, were able to make only about 1 knot an hour against the fury of the blast. End of chapter 26.